Hello, podcast listeners, and welcome. Rachel, how are you doing today?
I'm doing fantastic, super excited to be here.
So, what exactly is organic chemistry anyway?
It's the chemistry of carbon-containing compounds.
Carbon? Like charcoal carbon?
Exactly. But it's not just charcoal. It's carbon bonded to other elements, especially hydrogen, oxygen, nitrogen.
So, like living things?
That's where it started. Originally, organic meant compounds from living organisms.
Wait, really? Like only from plants and animals?
Precisely. People thought these compounds had a vital force that non-living things lacked.
A vital force? Sounds a bit mystical.
It was. They couldn't synthesize organic compounds in the lab back then.
So, how did that change?
In 1828, Friedrich Wöhler accidentally made urea an organic compound found in urine from inorganic salts.
No way! He made pee from rocks?
Well, not exactly rocks, but inorganic materials. That debunked the vital force theory.
So the definition changed?
Completely. Now it's about carbon compounds, regardless of origin. We can synthesize tons of them.
So basically, if it has carbon, it's organic.
Generally, yes, though there are some exceptions like carbon dioxide or carbonates.
Okay, good to know. So it's the study of carbon compounds.
Exactly. Their structure, properties, composition, reactions, and preparation.
Wow, that's a lot. So how is organic chemistry related to other fields?
Okay, so we know what's in organic molecules, but how does it all stick together? Is it just random?
No, there are very specific rules. It's about valency, how many bonds each atom likes to form.
Valency, got it. So like carbon always does the same thing?
Pretty much. Carbon almost always forms 4 bonds. That's its magic number.
4. Why 4?
It has to do with its electron configuration, but think of it like carbon having 4 arms to hold on to other atoms.
Arms. Okay, that's easy to visualize. What about nitrogen?
Nitrogen likes 3 bonds. Think ammonia, NH3.
Right, NH3, 3 hydrogens. Oxygen?
Oxygen usually forms 2 bonds, like in water, H2O.
So 2 arms for oxygen, 3 for nitrogen, 4 for carbon. What about hydrogen?
Hydrogen is simple. It only forms 1 bond. It's a terminal atom, usually at the end of a chain.
Okay, 1 bond for hydrogen. What about halogens, like chlorine?
Halogens also like 1 bond. They're similar to hydrogen in that way.
So these valency rules, they're pretty strict.
Relatively. There are exceptions, but these are the patterns you'll see over and over. They dictate the structure of almost every organic molecule.
So knowing these rules, you can almost predict how a molecule will be shaped?
Exactly. It's like Legos. Each atom only connects in certain ways, leading to specific shapes and properties.
Shapes that determine function.
Precisely. The shape dictates how it interacts, what it reacts with, and ultimately what it does.
So how do we actually draw these Lewis structures?
It's a step-by-step process. First, count the valence electrons.
Valence electrons, got it. Then what?
Next, draw the skeleton structure. Put the least electronegative atom in the center.
Okay, center atom determined. What's next?
Distribute the remaining electrons as lone pairs, starting with the surrounding atoms to fulfill their octets.
Octets fulfilled?
Yep. Then check if all atoms have a complete octet. If not, form multiple bonds.
Multiple bonds? Like double or triple bonds?
Exactly. Share electron pairs to make octets.
Okay, walk me through an example.
Let's do carbon dioxide, CO2.
Sounds good.
Carbon has 4 valence electrons, and each oxygen has 6. So that's 16 total.
16 electrons to play with, all right.
Carbon goes in the middle, bonded to each oxygen.
Because it's least electronegative, right?
Correct. That uses up 4 electrons in the 2 bonds. We have 12 left.
So far, so good.
Put those remaining 12 electrons as lone pairs on the oxygen atoms.
Each oxygen gets 3 lone pairs?
Yes, but now carbon only has 4 electrons around it, not an octet.
Aha, time for multiple bonds.
Exactly. Form a double bond between the carbon and each oxygen.
So 2 double bonds.
Yep. Now everyone has an octet.
Perfect.
That's the Lewis structure for carbon dioxide.
Got it.
So basically, count electrons, draw the skeleton, fill the octets, and make multiple bonds if needed.
You nailed it.
So let's dig into covalent bonds. What makes them different from ionic ones?
Covalent bonds share electrons, right? Ionic bonds transfer them. It's like sharing versus giving.
Okay, makes sense. Now, I've heard about sigma and pi bonds. What are those?
They're types of covalent bonds. Sigma bonds are strongest, formed by direct overlap of orbitals,
Direct overlap? What does that mean?
head on. Think of it like two people shaking hands firmly. Pi bonds are weaker and formed from sideways overlap.
Like a high five instead of a handshake?
Exactly. Pi bonds happen above and below the bonding axis, not directly between the atoms.
So sigma bonds are always first and pi bonds come after?
Yep. Single bonds are sigma. Double bonds have 1 sigma and 1 pi. Triple bonds, 1 sigma and 2 pi.
Wait, so triple bonds are stronger than double bonds, but each individual pi bond is weaker than a sigma bond? That's kind of wild.
Absolutely. The total bond strength increases with more bonds, even if the pi bonds themselves are weaker.
So basically, the more shared electrons, the stronger the connection between atoms?
Precisely. Sigma bonds give initial structure, and pi bonds add density and rigidity. That's the key.
Got it. So sigma for structure, pi for reinforcement. Like adding rebar to concrete.
Perfect analogy. It all comes down to how those orbitals interact.
Okay, so you mentioned electrons being shared, but what if they aren't shared equally?
That's bond polarity. It means one atom pulls the electrons closer.
Like a tug of war with a cheater on one side?
Exactly. That cheater is more electronegative.
Electronegative, so it attracts electrons more.
Yes. Think fluorine. It's the electron hog of the periodic table.
And if there's a big electronegativity difference, what happens?
The bond becomes polar, meaning it has a slightly positive and a slightly negative end.
How do we show that?
Several ways. Electron density maps show where electrons hang out. Partial charges use delta plus and minus symbols.
Delta, like the Greek letter?
Yep. And dipole vectors, arrows pointing towards the more negative atom.
Okay, so arrow points to the greedy atom. Got it. Any exceptions?
Carbon-hydrogen bonds. We often treat them as nonpolar, even though carbon is slightly more electronegative.
Wait, really? Why?
The difference is just so small. For most purposes, it doesn't matter.
So basically, it's close enough that we can just ignore it.
Pretty much. It simplifies things.
Okay, so molecules aren't just flat, right? They're 3D shapes?
Exactly. Molecular geometry is key. Think about carbon dioxide. It's linear.
Linear, meaning straight line?
Yep. Oxygen, carbon, oxygen. All in a line. Then there's trigonal planar, like boron trifluoride.
Trigonal planar, that's a triangle?
Yeah, a central atom with 3 atoms around it, all in one plane. Bond angles of 120 degrees.
Got it. What's next?
Tetrahedral. Methane is a classic example.
Like a pyramid shape?
Sort of. Imagine a central carbon with 4 atoms pointing towards the corners of a tetrahedron.
Tetrahedron? That's hard to visualize.
Yeah, it's 3D. Chemists use wedge and dash notation to draw them on paper.
Wedge and dash?
Solid wedges mean the bond is coming out of the page towards you, and dashed lines mean it's going behind the page.
Okay, I think I get it. So how do we predict these shapes?
That's where VSEPR theory comes in.
Vesper? Spell that out?
VHESPR. It stands for valence shell electron pair repulsion.
Repulsion, so electrons don't like each other?
Exactly. Electron pairs, both in bonds and lone pairs, repel each other and try to get as far apart as possible. And that determines the molecule's shape.
So basically, they're social distancing?
Precisely. The shape that minimizes repulsion is the shape the molecule adopts.
All right, I think that about does it.
Yeah, that was
Welcome
fun.
back to
Thanks,
the show.
Thanks
Rachel,
for
how are you doing today?
I'm doing awesome. Super excited to be here, Ben.
Okay, so let's dive into the actual bonding theories. What are the main ones we should know about?
We've got valence bond theory, or VB, and molecular orbital theory, MO.
VB and MO. Got it. What's the key difference?
VB looks at bonding as overlapping atomic orbitals forming bonds. Think of it like two puzzle pieces fitting together.
So localized bonds?
Exactly. MO, on the other hand, treats electrons as delocalized, spreading across the entire molecule.
Like one big electron cloud?
Precisely. MO theory gives us a more complete picture, especially with things like resonance, where electrons aren't stuck in one place.
Resonance. That's when you have multiple possible Lewis structures, right?
Yep, and the real molecule is a hybrid of them all. VB struggles with that. Also, hybridization is important in VB theory.
Hybridization, like sp3?
Exactly. Blending atomic orbitals to make new ones for bonding. VB uses hybridization to predict molecular shapes. MO handles shape more intrinsically.
Okay, so VB is good for simple shapes, MO for complex stuff.
Pretty much. VB is your quick and dirty tool. MO is more powerful, especially when delocalization matters.
So how do these theories compare? Like, what are the key differences?
Valence bond theory, or VB theory, treats bonds as localized between two atoms. It's like each bond has its own little electron club.
Okay, localized. What about molecular orbital theory, or MO theory?
MO theory spreads the electrons out over the whole molecule. Think of it like a communal electron pool.
So one's a club, the other's a pool. What about how these orbitals mix?
VB theory mixes atomic orbitals to form hybrid orbitals, explaining molecular shape. MO theory combines all atomic orbitals to create molecular orbitals, some bonding, some anti-bonding.
Anti-bonding. What's that?
Anti-bonding orbitals are higher in energy. If electrons fill those, the molecule becomes unstable.
So MO theory considers these destabilizing forces, while VB...
VB theory kind of ignores them. It's great for simple molecules, but MO theory handles more complex scenarios, like molecules with delocalized electrons, much better.
Delocalized electrons. That sounds important. Like in benzene, right?
Exactly. VB struggles with that while MO nails it. MO can also predict magnetic properties better.
So MO is more powerful, but VB is simpler.
Pretty much. VB gives you a quick, intuitive picture for basic molecules, while MO gives a more accurate but complex picture for everything else.
Okay, so we know atoms want to bond, but how do they actually rearrange their electrons to make it work?
That's where hybridization comes in. It's like atomic orbitals mathematically mixing to form these new hybrid orbitals.
Mixing? Like a smoothie?
Sort of. A common one is tetrahedral. Think methane. With carbon at the center, it mixes one s and 3 p orbitals.
So sp3?
Exactly. Resulting in 4 identical sp3 hybrid orbitals pointing to the corners of a tetrahedron. Bond angles of about 109.5 degrees.
Okay, so tetrahedral is one. What else?
Trigonoplanar. Boron trifluoride is a good example. That mixes one s and 2 p orbitals.
sp2?
You got it. Creating 3 sp2 hybrids in a flat triangle, 120-degree bond angles, and one unhybridized p orbital sticking out.
Unhybridized, so it doesn't mix?
Right. Then there's linear, like carbon dioxide, one s and one p orbital mix.
SP?
Yep. 2 sp hybrids pointing opposite directions for a 180-degree angle, and 2 unhybridized p orbitals.
Okay, let's make this real. Can we build a molecule using valence bond theory?
Let's do methane, CH4. Carbon in the middle with 4 hydrogens.
Sounds good. So where do we even start?
First, carbon has to rearrange its electrons. Think of it as promoting one electron.
Promoting? From where to where?
From the 2s orbital to the 2p orbital. This gives us 4 unpaired electrons.
Okay, 4 unpaired electrons on the carbon.
Exactly. Then these orbitals blend to form 4 hybrid orbitals.
Hybrid orbitals. Got it. What kind?
They become sp3 hybrids. This is key.
Why is that key?
These sp3 orbitals arrange themselves in a tetrahedron.
A tetrahedron. So that explains methane's shape.
Precisely. Each sp3 orbital overlaps with a hydrogen 1s orbital, forming a sigma bond.
Sigma bonds from each hydrogen, making 4 total.
That's right. 4 sigma bonds pointing to the corners of the tetrahedron.
And that's methane. Huh. So valence bond theory predicts its shape by looking at orbital overlap.
Yep. It's all about how those atomic orbitals combine.
So how do these orbitals explain single, double, and triple bonds?
Great question. It's all about those unhybridized p orbitals. They dictate the type of bonds we can form.
Like, how many p orbitals are we talking about?
Well, a single bond, like in methane, is a sigma bond. No unhybridized p orbitals are needed.
Okay, so what changes with a double bond?
A double bond, like in ethene, is 1 sigma bond and 1 pi bond, formed from 1 unhybridized p orbital.
Wait, sigma and pi? Break that down for me.
Sigma bonds are head-on overlaps, strong and stable. Pi bonds are sideways overlaps, weaker.
Gotcha. So triple bonds must need even more p orbitals.
Exactly. A triple bond, like in ethine, is 1 sigma bond and 2 pi bonds. So you need 2 unhybridized p orbitals.
So basically, more bonds, more p orbitals.
Precisely. Each pi bond adds another unhybridized p orbital into the mix, influencing the molecule's shape and reactivity.
That's wild. So it's like the p orbitals are the building blocks for these different kinds of connections.
Exactly. They determine the type of bond.
Okay, so we've got these structures that seem kind of incomplete.
Right. That's where resonance comes in. Think of resonance structures as different ways to draw the same molecule.
Different drawings for the same thing. How's that work?
They're different electron dot pictures, but none of them are actually the real structure.
So what is the real structure then?
It's a weighted average of all the resonance structures. We call it a resonance hybrid.
A hybrid, like a mix of all the possibilities.
Precisely. It's like saying the electrons aren't stuck in one place, they're spread out.
Spreading out the electrons, that sounds important.
It is. It's called electron delocalization, and it lowers the molecule's energy.
Wait, lower energy? Ow.
Think of it like this. The more space electrons have, the more stable they are, like having a bigger apartment.
A bigger electron apartment equals lower energy. I like that.
Exactly. Resonance and electron delocalization contribute to molecular stability.
Okay, so we've got the Lewis structure. Now, how do we figure out the hybridization of each atom?
It's like a quick checklist. First, count the regions of electron density around the atom.
Regions? What counts as a region?
Any bond or lone pair. Single, double, triple, doesn't matter. Each counts as one region.
Got it. So count the regions. Then what?
Relate the number of regions to the hybridization. 2 regions is sp, 3 is sp2, 4 is sp3.
Wait, so it's that simple? Just count and match?
Pretty much. The number of things attached determines the hybridization.
Okay, so if carbon has 4 things attached, it's sp3. Makes sense.
Exactly. Remember, multiple bonds still only count as one region of electron density.
So a carbon double bonded to oxygen and single bonded to 2 other things
Would be sp2. 1 region for the double bond, 1 for each single bond, total of 3.
Okay, I think I'm getting the hang of this hybridization thing.
Awesome. This sets the stage for predicting molecular shapes, which is the next step.
So, what are condensed structures in chemistry?
Think of them as a shorthand. We skip drawing every single bond.
Like hiding the carbon-hydrogen bonds?
Exactly. If you see CH3, it means a carbon with 3 hydrogens attached.
Okay, that makes sense. So, what about repeating groups?
Those get grouped with subscripts, like CH24 means 4 CH2 units in a row.
Wait, so you just write it once with a number?
Yup. It cleans things up a lot. It's especially useful in organic chem.
What about double and triple bonds? Do those also get simplified?
No, you still show multiple bonds explicitly. A double bond is still 2 lines, a triple bond 3.
Got it. So basically, hide the single bonds to hydrogen, group repeating units, but show multiple bonds.
Precisely. It's all about making structures easier to read quickly.
That's a great way to save space and time.
Big time saver. Now, let's chat about isomers.
Okay, so you've drawn out the molecule. Now what?
Now we use line structures. It's a simplified way to draw organic molecules.
How so?
Carbon atoms aren't explicitly drawn. They're just at the vertices, where lines meet or end.
Wait, so the corners are carbons?
Exactly. And we only explicitly show heteroatoms, atoms that aren't carbon or hydrogen, like oxygen or nitrogen.
Got it. What about hydrogens?
Hydrogens attached to carbon are usually omitted.
So you have to just know they're there.
Precisely, but hydrogens bonded to heteroatoms, like the OH in an alcohol, those we do draw.
Okay, so corners are carbons, only draw heteroatoms, hide the hydrogens on carbons, but show them on other stuff. Why, though?
It makes drawing and reading complex molecules much faster and simpler without losing any information.
Efficiency's key, huh?
Absolutely. It's like shorthand for chemists.
All right, that about wraps it up.
Welcome to
Yeah,
the
I
show.
think so.
Rachel,
Thanks,
how are you
Rachel.
doing today?
I'm doing awesome. Super excited to be here.
Okay, so molecules are built from atoms, right? What makes one molecule act so differently than another?
That's where functional groups come in. They're specific groups of atoms within a molecule.
Like little add-ons?
Exactly. And these determine almost all of a molecule's properties. Think reactivity, color, even boiling point.
Wait, so a tiny group of atoms can control all that?
Absolutely. They dictate how a molecule interacts with other molecules.
Give me an example.
Okay, take alcohols. They all have an OH group, an oxygen and a hydrogen. That OH makes them polar, like water. That polarity affects its boiling point.
So that one OH makes it an alcohol.
Yep. Ethanol, methanol, they all have it. And that small difference changes everything.
So basically, functional groups are like the control panel for a molecule's behavior.
Precisely. You change the functional group, you change the molecule.
That's wild. So are there like a ton of these groups?
Oh yeah, there are many, each with unique properties. We have things like amines, carbonyls, esters.
Okay, hold on. So how do you even start learning all these different functional groups?
Well, we can start with some of the common ones and their effects. It's like learning the alphabet of molecules.
So what exactly are hydrocarbons and why should we care?
They're organic compounds, the building blocks of many things, made of hydrogen and carbon, obviously.
Okay, but what makes them so special?
Their structure. Carbon atoms link together to form chains and rings.
And then hydrogen atoms attached to the carbon. So like the carbon is the frame and hydrogen is the decoration?
Exactly. Now, there are different types. Saturated ones, like alkanes, are pretty unreactive.
Unreactive how?
They don't easily react with other chemicals. They're stable.
Gotcha. So what about the unsaturated ones?
Those are alkenes, alkynes, and aromatics. They have double or triple bonds between carbon atoms.
And that makes them different?
Way different. The double or triple bonds make them much more reactive, so they're more prone to, participate in chemical reactions.
So saturated, boring, unsaturated, exciting.
In terms of reactivity, yes.
Also, hydrocarbons create molecular scaffolds for more complex molecules.
Scaffolds?
Yeah, like the carbon structure is the base that functional groups attach to.
Functional groups?
We'll get into those later, but basically, hydrocarbons are the basic frame on which a lot of other molecules are built.
So we keep talking about single bonds. What happens when we throw in some double or triple bonds?
Now we're talking. That's where things get interesting. We're talking about alkenes, alkynes, and aromatics.
Alkynes. Those are the double and triple bonds, right?
Exactly. Alkenes have at least one carbon-carbon double bond, and alkynes have at least one carbon-carbon triple bond.
And what does that do to the molecule?
It changes everything. Double and triple bonds are electron-rich, meaning they're more reactive.
Reactive how?
They're prone to attack by electrophiles, which are basically electron-loving species. Think of it like magnets, opposites attract.
Okay, makes sense. So more electrons, more action.
Precisely. And those pi bonds also affect the shape of the molecule. Double bonds create planar regions. Everything around that double bond wants to be flat.
Flat like a pancake.
Yes. Now, let's talk about aromatics, benzene rings.
Oh yeah, benzene. 6 carbons in a ring?
With alternating single and double bonds. But here's the trick. Those double bonds are delocalized.
Delocalized, meaning...
The electrons aren't stuck in one place. They're spread out around the entire ring. This makes benzene super stable.
Stable, but still reactive?
In a different way. It undergoes substitution reactions rather than addition reactions like alkenes and alkynes.
So it swaps things out instead of adding them on?
Exactly. That stability changes everything. This is my favorite part.
No way. Now, how about we talk about...
So let's talk about functional groups with heteroatoms. What makes them so special?
It's all about those heteroatoms. Oxygen, nitrogen, sulfur. They bring lone pairs and multiple bonds into the mix.
Lone pairs? What's the big deal about those?
Lone pairs are like little clouds of negative charge. They can act as reactive sites. They make the molecule a base or a nucleophile.
A nucleophile? Like attacking other things?
Exactly. They're electron-rich and love attacking electron-poor spots. And the multiple bonds on heteroatoms, big reactivity boost.
How so?
Think about a carbon-oxygen double bond, right? That's a carbonyl, polar and reactive. It's right for addition reactions.
Okay, so what are some of the common heteroatom groups we should know?
Alcohols with their hydroxyl groups, amines sporting nitrogen atoms, ethers with oxygen linking 2 carbons, and nitriles with carbon-nitrogen triple bonds.
So alcohols are like hydroxyl groups bonded to carbons, right?
Yep, and those hydroxyl groups can hydrogen bond, making alcohols higher boiling than similar alkanes.
And amines have nitrogen. What's special about them?
Nitrogen is basic, so amines can act as bases, grabbing protons. They can also be nucleophiles, reacting with electrophiles.
Ethers are just oxygen stuck between 2 carbons, right?
Basically, they are relatively unreactive but serve as good solvents.
And nitriles have that carbon-nitrogen triple bond you mentioned.
Exactly. The triple bond makes them prone to additions. Plus, you can hydrolysize them to carboxylic acids.
Okay, so we've talked about drawing these line structures, but how does that make identifying functional groups easier?
Great question. Line structures really shine here. They make it super clear where the action is happening in a molecule.
How so?
Well, heteroatoms like oxygen, nitrogen, sulfur, they're all explicitly drawn. You don't have to guess where they are like in a condensed formula.
Oh, right, because you only draw the carbons and hydrogens in condensed, right?
Exactly. And any hydrogen attached to a carbon. So, by showing those heteroatoms, line structures immediately highlight potential reactive sites.
Reactive sites.
Yeah, the parts of the molecule most likely to participate in a reaction. Think of an alcohol. That OH group is right there screaming, "I'm an alcohol."
So it's a visual shortcut. What about more complex functional groups?
Still helpful. Esters, amides, carboxylic acids, they all have characteristic arrangements of heteroatoms and double bonds that are instantly recognizable in a line structure.
Like a little map of reactivity.
Precisely. Plus, recognizing functional groups is key to understanding a molecule's properties and how it will behave.
Okay, makes sense. So line structures are like cheat codes for organic chemistry?
I like that. A visual cheat code that helps you quickly identify the important parts of a molecule and understand its chemistry.
Okay, but what happens when a molecule has, like, all the functional groups? Things must get crazy complicated, right?
Absolutely. When you have multiple functional groups, you have to consider how they all interact.
Interact? Like, they can affect each other's reactivity?
Exactly. Think of it as a team. Sometimes they work together. Sometimes they interfere.
So it's not just add up the properties of each group?
No way. It's much more nuanced. A classic example is how one group can activate or deactivate another.
Activate or deactivate? Like speed up or slow down a reaction?
Precisely. Or even change the reaction pathway completely.
Wait, really? So how do you even predict what's going to happen?
Systematic analysis is key. You have to consider electronic effects, steric hindrance, and the specific reagents you're using.
Steric hindrance? Big words.
Basically, how bulky the groups are. Big, bulky groups can physically block a reaction from happening.
So it's like the functional groups are fighting for space?
In a way, yes. It's all about accessibility and the overall energetic landscape of the molecule.
Energetic landscape. Sounds complicated.
It can be, but the core idea is that the molecule will prefer the most stable state. And that depends on how all the functional groups play together.
So basically what you're saying is, with multiple groups, it's not just about what they are, but how they interact to determine the molecule's overall behavior.
Exactly. It's a puzzle, but a fascinating one.
Okay, so how do you actually learn all these functional groups?
It's a strategic process, honestly. Start with memorization. Flashcards are your friend.
Good old flashcards still work?
Absolutely. Then practice. Work through problems, identify the functional groups.
Repetition is key then.
Exactly. But also understand the reactivity patterns. Each functional group has tendencies.
Like how they behave in reactions?
Yes, and it's not just rote memorization. Understand why they react that way.
Okay, that makes sense.
And here's the cool part. Recognize combinations. See how different groups interact.
Like when you have an alcohol and a carboxylic acid together?
Exactly. You can predict what might happen based on what you know about each group separately.
So it's like building blocks.
Precisely. Functional groups determine so many chemical properties and reaction pathways. Master them, and you've unlocked a huge part of organic chemistry.
That's a really helpful way to think about it.
It's all about breaking it down into manageable pieces and then building your understanding from there.
Okay, so master the functional groups, and then we can start to predict what's going to happen in a reaction, right?
You got it. Now, let's talk about something people often find tricky.
All right, that brings us to the end.
Yeah, I think we covered a lot.
Welcome to the show.
Thanks, Rachel.
Rachel, how are you today?
I'm great, Ben. So ready to jump in.
So we've been talking about molecules bonding atoms together, but what about molecules interacting with each other?
That's where intermolecular forces come in. They're the attractions between separate molecules.
Okay, so what do those forces do?
They dictate a lot. Think melting point, boiling point, how well things dissolve. It all comes down to how strongly molecules are attracted to their neighbors.
So stronger attractions mean higher melting points?
Exactly. More energy needed to pull them apart.
Got it. But where do these attractions even come from?
It's all about electron distribution. Electrons aren't always evenly spread out.
So like sometimes one side of a molecule is a little more negative?
Precisely. That creates a temporary partial charge, and opposite charges attract.
Like tiny little magnets.
Sort of, but much weaker than actual magnets. These forces are subtle but super important.
So basically, electron clouds that aren't perfectly symmetrical cause all these interactions.
That's the gist of it. And the shape of the molecule affects those electron clouds too.
Okay, so shape matters too. We're going to need to unpack that.
Okay, so we've talked about hydrogen bonds. What's even stronger than that?
That would be electrostatic interactions. These are the big guns.
Electrostatic? Like static electricity?
Similar idea, but on a molecular level. Think fully charged functional groups.
Fully charged? What does that even mean?
Like ions, where one molecule has a full positive charge and another has a full negative charge.
Oh, like ionic bonds?
Exactly. That's what creates ionic structures.
Give me an example, something I know.
Table salts, sodium chloride. The sodium ion is positive, the chloride ion is negative.
So the positive and negative attract super strongly.
Yep. It's the attraction between those full charges that makes electrostatic interactions so powerful.
Are there other examples besides table salt?
Tons. Any interaction between a carboxylate ion and an ammonium ion, for instance. These pop up all over in biological systems.
So electrostatic interactions basically glue molecules together with super strong charges.
Precisely. They're crucial for holding things like proteins and DNA together. It is kind of amazing.
Okay, so we talked about London dispersion forces. What's next?
Dipole-dipole interactions. Think of them as London forces, but with training wheels.
Training wheels?
Yeah, they're stronger because they come from permanent differences in electronegativity.
Electronegativity?
How much an atom wants to hog electrons in a bond. Like oxygen pulling harder than carbon.
So oxygen gets a little negative.
Exactly, a partial negative charge. And the carbon, a partial positive.
And that's a dipole?
Yep, a positive and a negative end. These stick together.
Like magnets?
A little bit, yeah. A great example is ketones. You know, with the C double bond O.
Yeah, those.
That oxygen is way more electronegative. Big dipole. These interactions are key for how ketones behave.
So basically, unequal sharing creates stickiness.
Exactly. Stronger stickiness than just temporary fluctuations.
Got it. What's even stickier?
Hydrogen bonds.
Okay, so we've covered the basics of intermolecular forces. What's next?
Let's talk about hydrogen bonding. It's super important.
Hydrogen bonding? Sounds intense.
It is. It's a special type of dipole-dipole interaction. Think of it as the VIP of intermolecular forces.
Why is it so special?
It requires a hydrogen atom bonded to a small electronegative atom.
Electronegative? Like what?
Oxygen, nitrogen, or fluorine. These are the usual suspects.
Okay, so hydrogen bonded to O, N, or F. Then what?
Then you need an acceptor atom, another O, N, or F with a lone pair of electrons.
So they kind of stick together.
Exactly. It's a strong attraction.
How strong are we talking?
Stronger than typical dipole-dipole forces. It really impacts properties.
Like what properties?
Boiling points, solubility. Think about water. Hydrogen bonding is why it's liquid at room temperature.
Wait, really? Just hydrogen bonds?
Absolutely. It's that important. Also consider alcohol molecules.
Alcohol? How do they fit in?
They have that OH group, perfect for hydrogen bonding.
Ah, got it. So the OH is the key.
Yup. It influences how alcohol molecules interact with each other and with water.
So are there forces between molecules that aren't polar?
Absolutely. London dispersion forces, or LDFs. They're the weakest, but they're universal.
Universal?
Present in all molecules, polar or not. Even noble gases have them.
Wow, really? How do they work?
Think of electron clouds constantly fluctuating. It creates temporary dipoles.
Temporary dipoles, so not permanent like in polar molecules.
Exactly. These temporary dipoles induce dipoles in neighboring molecules.
And that's what causes attraction.
Precisely. Larger molecules generally have stronger LDFs.
Because they have more electrons?
Yes. And here's a key point. Shape matters too.
How so?
Molecules with larger surface areas have more contact and stronger attractions.
So like long and skinny molecules versus compact ones?
Precisely. Think of it like Velcro. More surface area, stronger grip.
Got it. So LDFs are all about temporary dipoles and surface area.
Exactly. They're weak, but they're always there.
So how does this attraction between molecules affect stuff we can observe, like melting or boiling?
Great question. It's all about energy. To melt or boil something, you've got to give the molecules enough energy to overcome those intermolecular forces.
So stronger the force, more energy needed.
Exactly. Higher melting and boiling points. Think of water versus methane. Water has hydrogen bonds. Methane just has weak London dispersion forces, big difference in boiling points.
Got it. So basically, stronger stickiness equals more heat to pull apart.
Precisely. And it's not just about the type of force. Size matters too. Larger molecules have more surface area, more places for those London dispersion forces to act.
So bigger molecules boil at higher temps?
Usually, yes. But shape also plays a role.
Shape?
Branched hydrocarbons, for example. They can't pack as tightly, so the intermolecular forces are weaker, thus lower boiling points than their straight-chain cousins.
Okay, so branching decreases boiling point.
Right. And cyclic hydrocarbons, rings, tend to have higher melting points than similar straight-chain ones.
Because they're more rigid?
Exactly. They pack better.
Okay, so what makes something dissolve in something else?
It's all about like dissolves like.
Like dissolves like. What does that even mean?
Polar things dissolve in polar solvents, nonpolar in nonpolar. Think oil and water.
Okay, that makes sense. So what are the different kinds of solvents?
We have polar protic, polar aprotic, and nonpolar. Polar protic, like water, can donate hydrogen bonds.
And aprotic?
Polar aprotic can't donate hydrogen bonds, but they're still polar. Then you have nonpolar solvents, like hexane.
Got it. What about hydrophobic and hydrophilic interactions?
Hydrophilic things love water. Hydrophobic things hate it. Fats are hydrophobic. Salt is hydrophilic.
So how does this all play out? Give me an example.
Ethanol, with its small carbon chain, is pretty soluble in water. But as you make the alcohol chain longer, it becomes less soluble because the nonpolar part dominates.
So bigger alcohols are less soluble. What about acids?
Carboxylic acids can form hydrogen bonds, but again, it depends on the size of the carbon chain. Smaller ones are more soluble.
Okay, so size really matters then.
Absolutely. The balance between polar and nonpolar parts determines solubility.
Okay, so what about branching? How does that mess with solubility?
Branching totally changes things. Think of it like trying to pack neatly in a suitcase.
Suitcase Tetris, got it.
Exactly. Linear molecules pack nice and tight. Branched ones, not so much.
So more gaps?
Way more gaps. Those gaps are what allow water molecules to sneak in and surround the branched molecule.
Making it more soluble, right?
Bingo. Branched molecules generally dissolve better in water than linear ones of the same size.
That's wild. So a perfectly straight molecule is less soluble?
In water, yes. The key is packing efficiency. Branching disrupts that. Think about it like this. If you have a bunch of perfectly stacked blocks, it's hard to get anything in between, right?
Sure.
But if you have a bunch of oddly shaped, wobbly ones, it's easy to disrupt and move around.
So basically, being less organized makes you more soluble?
In a nutshell, the more branching, the less it wants to stick with itself, and the more it wants to mingle with the water.
Gotcha. So packing is everything.
Absolutely. It all comes down to how well molecules can pack together.
Well, that was a lot to chew on.
Hey everyone,
Yeah,
welcome
sure.
to the show.
Thanks, Rachel.
Rachel, how are you doing today?
I'm doing great, Ben. Super excited to be here.
Okay, so we've talked about why these organic compounds are so important, but how do scientists even keep track of them all? There are millions, right?
Exactly. That's where organic nomenclature comes in. It's the system we use to name them precisely.
Nomenclature. Sounds fancy. What happens if you don't name them right?
Chaos. Imagine ordering the wrong chemical for an experiment because the names got mixed up. Or worse, medicine with the incorrect ingredients.
Yikes. So this naming system is critical for accuracy, right?
Absolutely. And the gold standard is the IUPAC system.
IUPAC? What does that stand for?
The International Union of Pure and Applied Chemistry. They set the rules for naming compounds. It's a standardized approach, so everyone speaks the same language, chemically speaking.
Okay, that makes sense. So IUPAC is like the grammar guide for chemistry.
Perfect analogy. Now, every IUPAC name has 4 main parts. Think of it like building with Lego bricks.
Ooh, I like Lego.
First, we have the substituents. These are the little side chains hanging off the main structure.
Like decorations on a Christmas tree?
Sort of. Then comes the root, which tells you how many carbon atoms are in the main chain.
The backbone of the molecule?
Exactly. Next is the saturation. Is it all single bonds, or are there double or triple bonds?
So saturation indicates single, double, or triple bonds.
Precisely. Finally, we have the principal functional group.
And that tells you...
It tells you what kind of chemical family it belongs to, like an alcohol or an acid.
So substituents, root, saturation, and functional group. Got it. Is there a particular order to these?
There is. It's like a specific recipe. You put the ingredients together in the right order.
So let's get into the nitty-gritty of naming these compounds. What's the first step in the IUPAC naming process?
First, you've got to identify the principal functional group.
Principal? As in the most important one?
Exactly. It's like figuring out who the lead singer is in a band.
Okay, but how do you decide which group is the lead singer?
That's where the priority table comes in handy. It's basically a ranking system.
A ranking system for functional groups? Interesting.
Yep. Carboxylic acids are usually at the top, then esters, amides, aldehydes, ketones, alcohols, amines, alkenes, alkynes, and so on.
So if a molecule has both an alcohol and a ketone, the ketone gets the spotlight?
Precisely. The ketone becomes the suffix of the name, while the alcohol gets named as a substituent with a prefix like hydroxy.
Got it. What's next after figuring out the main functional group?
You have to find the longest continuous carbon chain that contains the principal functional group.
The root chain, right?
Right. The number of carbons in that chain determines the base name. Methane for 1, ethane for 2, propane for 3.
And so on, like octane for 8?
You got it. Then you need to look at saturation. Are there single, double, or triple bonds?
How do you figure that out?
That's where the saturation index comes in. It tells you how many rings or pi bonds are in the molecule.
Pi bonds meaning double or triple bonds.
Exactly. A saturated molecule has the maximum number of hydrogens and only single bonds.
So a higher saturation index means more unsaturation, like double or triple bonds or rings.
That's right. You'll use ane for single bonds, ene for double, and wine for triple.
Okay, so functional group, longest chain, saturation. What then?
Next, you have to specify the location of substituents and double, triple bonds using numbers to give each molecule a unique name.
Okay, so let's put these rules into action. Got any examples we can run through?
Definitely. Let's start simple. Say we have a molecule with an alcohol and a double bond. Which gets priority when numbering?
The alcohol, right? It's the principal functional group.
Exactly. So you'd number the chain to give the alcohol the lowest possible number, even if the double bond gets a higher number.
Got it. What if we have, just a double bond and a methyl group?
Then the double bond takes precedence. You want to give it the lowest number. The methyl group is just a substituent.
Okay, makes sense. So principal functional group beats multiple bonds, which beats substituents. What about naming the substituents themselves?
That's all about alphabetical order. So a bromo group comes before a chloro group, which comes before an ethyl group, even if the ethyl group is on carbon number 2.
Even with the numbers all messed up?
Right. You ignore prefixes like di, tri, or tert when alphabetizing. Just look at the root name of the substituent, like methyl or ethyl.
Okay, alphabetize the substituents. What about when there's stereochemistry involved?
Stereochemistry. So you'll often see cis-trans for alkenes or cyclic compounds.
Cis and trans, like same side, opposite side, right?
Precisely. And then there's the R and S notation for chiral centers. That's a whole other can of worms determining the absolute configuration.
Wait, can you break that down? What does R and S mean?
R and S refer to the spatial arrangement of atoms around a chiral carbon. You assign priorities to the groups attached to the carbon based on atomic number.
Atomic number?
Yeah, the higher the atomic number, the higher the priority. Then you visualize the molecule so the lowest priority group points away from you. If the remaining groups decrease in priority clockwise, it's R. Counterclockwise, it's S.
Okay, that sounds intense.
So, like if bromine is attached, it automatically gets super high priority?
Pretty much. Bromine has a high atomic number, so it usually outranks carbon or hydrogen. But we are really getting into the weeds now.
Yeah, maybe we save the full stereochemistry deep dive for another time. So, high level, prioritize principal functional groups, then multiple bonds, then substituents alphabetically. Add stereochemistry notation if needed. Am I getting it?
You've got the gist of it. Now, ready for a crazy twist? What if you have multiple identical functional groups, like 2 alcohols?
Okay, so what happens when we have like multiple functional groups all fighting for attention?
That's when things get interesting. You've got to identify the principal functional group. It's the boss.
The boss? How do I know who's in charge?
There's a priority order. Carboxylic acids usually outrank aldehydes, which beat ketones, and so on.
Okay, so the boss gets the lowest number, right?
Exactly. And the rest are treated as substituents. So instead of naming them with a suffix, you use a prefix.
Substituents. Like methyl or ethyl groups?
Exactly. Those are alkyl groups. They're carbon-based chains that branch off the main one.
And what about rings, like benzene?
Those are aromatic substituents. Phenyl is a benzene ring directly attached, and benzyl has an extra carbon in between.
Okay, phenyl and benzyl. Got it. So what are some common mistakes people make when naming these complex molecules?
Alphabetical order is a big one. People mess that up all the time. And remember, prefixes like di or tri don't count for alphabetizing.
Wait, really? So dimethyl comes before ethyl even though D comes before E?
Exactly. It's the M in methyl versus the E in ethyl that matters. Also, people often forget to prioritize the principal functional group when numbering.
So even if it would give other substituents lower numbers, the boss comes first.
Yes, the principal functional group dictates the numbering, period. Think of it like the prime directive of IUPAC naming.
So basically, what you're saying is respect the boss, get your alphabet right, and don't forget the numbers.
Precisely. And practice, practice, practice. The more molecules you name, the easier it becomes.
Okay, so we've covered a lot of ground. Any quick tips for people trying to actually learn this stuff?
Practice, practice, practice. Seriously, that's the key. Start with simple molecules and work your way up.
Yeah, like flashcards or something?
Flashcards are great for memorizing prefixes and suffixes, but also just draw molecules and try to name them.
And then check your work?
Absolutely. There are tons of online resources, practice quizzes, even apps. Look for ones that give you immediate feedback.
Any particular resources you recommend?
Khan Academy has a good organic chemistry section, and most organic chemistry textbooks have tons of practice problems.
Okay, so textbooks plus Khan Academy. Got it. What are the trickiest parts where people usually mess up?
Stereochemistry is a big one. Remembering E and Z, R and S configurations it gets confusing.
Yeah, all those letters.
Exactly. And prioritizing substituents when you have multiple functional groups, knowing what gets the highest priority number.
Right, because you have to number the parent chain and all that.
Precisely. And cyclic compounds can be tricky too, especially when you have multiple substituents on the ring.
So basically, lots of ways to go wrong.
But with practice, you'll start to see the patterns. And don't be afraid to ask for help. Organic chemistry professors are usually happy to explain things.
Good point. Office hours exist for a reason. Okay, so practice, know your priorities, and stereochemistry can be a beast. Anything else?
Pay attention to detail. A single missed number or a misplaced substituent can completely change the name.
True. It's not like close counts in organic chemistry naming.
Nope. But honestly, once you get the hang of it, it's kind of like a puzzle. A really satisfying puzzle.
I can see that. The satisfaction of cracking the code.
Exactly.
And it's so important because it's the foundation for understanding organic reactions and mechanisms. So master the naming, master the chemistry? Pretty much. It's like learning the alphabet before you can write a sentence. That's a great analogy. Thanks. I feel like I could almost name something now.
Well, that about wraps it up.
Welcome back to the show.
Thanks,
Rachel, how are you today?
I'm fantastic. Ready to jump in.
So, we're talking about how molecules jiggle around and change shape.
Exactly. It's like they're constantly dancing. Even at standard temperature and pressure, they're in motion.
Dancing? What kind of dance are we talking about?
Think of it as a mix of rotations and vibrations. Atoms are always moving.
Okay, so they're not static structures. How do we even visualize these different shapes?
That's where Newman projections come in. They let you visualize rotation around a single bond.
Newman projections? Sounds complicated.
Not really. You're looking straight down one carbon-carbon bond and seeing the groups attached to each carbon.
Ah, I see. So it shows the different arrangements possible.
Precisely. And some arrangements are more stable than others because of torsional strain.
Torsional strain? What's that?
It's the resistance to twisting. Big groups bumping into each other as they rotate.
So less bumping is better.
Definitely. That's why staggered conformations are generally more stable than eclipsed ones.
Okay, got it. What about rings? Do they do the same thing?
Cycloalkanes are interesting because they also have ring strain. The rings aren't always flat.
Ring strain? So it's like they're trying to be something they're not?
Exactly. The angles are forced into non-ideal positions, causing strain and affecting their reactivity.
So everything we've been talking about is constantly in motion, right?
Absolutely. At standard temperature and pressure, molecules are always jiggling around.
Like even solids?
Even solids. The atoms are vibrating, just not moving from place to place.
Okay, so what does that have to do with conformations?
Conformations are basically different 3D arrangements of the same molecule.
How does a molecule rearrange itself?
Sigma bond rotation. Think of a single bond like an axle.
And things can spin around that axle?
Exactly. That rotation changes the molecule's shape. It's still the same molecule, just a different conformation.
So it's like wiggling a bendy straw.
Perfect analogy. Different shapes, same straw.
Are some conformations more stable than others?
Definitely. It all comes down to energy. Lower energy conformations are more stable.
And that affects how they interact?
Absolutely. A more stable conformation will be more prevalent. Think about it like this.
Yeah.
Molecules will naturally settle into their lowest energy state.
So we've talked about how flexible molecules are. How do we even visualize these different shapes?
That's where Newman projections come in. They're a way to represent a molecule by looking down a specific carbon-carbon bond.
Like I'm staring down the barrel of a carbon-carbon bond?
Exactly. You imagine your eye aligned along that bond. The front carbon is a dot, and the back carbon is a circle behind it.
Okay, I think I get the setup. So what do the lines coming out of the dot and circle represent?
Those are the bonds attached to each carbon. For the front carbon, they come straight out of the dot. For the back, they come out of the circle, slightly offset so you can see them.
So it's like a top-down view of the molecule?
Yep.
It shows the spatial arrangement of the substituents, those atoms or groups attached on those two carbons.
Let's do an example like with ethane. It has 2 carbons, each with 3 hydrogens attached.
Perfect. If you look down the carbon-carbon bond of ethane, you'll see the front carbon with 3 lines showing the attached hydrogens. Same for the back carbon.
And the angle between those hydrogens shows the conformation, right? Like, are they lined up or staggered?
Precisely. Newman projections make it easy to visualize the angle between the substituents. This is called the dihedral angle.
So basically, Newman projections are a visual shortcut to understanding a molecule's 3D shape.
Absolutely. They simplify things. You can quickly compare different conformations like eclipse versus staggered and see which are more stable.
So we're talking about these different shapes molecules can take. But why do they prefer some over others?
Energy. Molecules want to be in the lowest energy state possible. Different conformations have different energies.
Okay, so like some positions are more comfortable.
Exactly. And one factor that affects energy is torsional strain.
Torsional strain? What's that?
It's the resistance to twisting around a bond. Think of it like trying to force 2 magnets together when they're repelling.
Oh, I get it. So some arrangements are more strained than others.
Precisely. We talk about eclipsed and staggered conformations.
Eclipsed and staggered? What's the difference?
Imagine looking down a carbon-carbon bond. If the atoms on the front carbon are directly in front of the atoms on the back carbon, that's eclipsed. High energy.
So everything's lined up?
Yep, maximum repulsion. Staggered is when they're as far apart as possible. Lower energy.
Ah, so staggered is more stable.
Exactly. And we measured the angle between those atoms with something called the dihedral angle.
Dihedral angle?
It's the angle between 2 sets of 3 atoms, kind of measuring that twist. 0 degrees is eclipsed, 60 is staggered.
Got it. So basically, molecules want to avoid being eclipsed because it's like energetically awkward.
You nailed it.
So let's zoom in. What happens when we rotate around a single bond?
You get different conformations, and they're not all equal in energy.
Why not?
Strain, specifically torsional strain.
Torsional strain.
Yeah, when bonds eclipse each other. Think of ethane. The eclipse conformation is higher in energy than the staggered.
Eclipsed meaning they're lined up?
Exactly, more repulsion. Staggered is lower energy.
Got it. So it's all about electron repulsion.
Partly. And there's steric strain too.
Which is?
When atoms bump into each other. Crowding. Like in butane, the methyl groups can clash.
So bigger groups, more strain.
Yep. Now, special conformations have names. Anti, where the big groups are opposite each other.
And that's favored.
Usually. Then there's gauche, where they're next to each other. Less stable. Think 1,2-dichloroethane. The 2 chlorines want to be anti.
Okay, so anti is generally best. Less strain, lower energy.
Precisely.
Okay, cyclic molecules. What makes them so special?
It's all about ring strain. These molecules are forced into shapes that their bonds don't love.
Ring strain. Got it. What causes that?
3 things: angle strain, torsional strain, and steric strain.
Okay, break this down for me.
Angle strain is when bond angles deviate from the ideal. Torsional strain comes from eclipsing bonds. Steric strain is crowding.
Crowding of atoms, right?
Exactly. Cyclopropane is the poster child for ring strain. It's this tiny triangle.
I can picture it.
Its bond angles are squished to 60 degrees. That's way off from the preferred 109.5.
Ouch.
Massive angle strain. Plus, all those bonds are eclipsing, maximizing torsional strain. It's a strange little molecule.
So how does cyclopropene even exist?
It forms banana bonds. Instead of straight bonds, they're bent.
Banana bonds?
Yeah, they look like bananas connecting the carbons. This reduces the angle strain, kinda.
Wait, so the bonds themselves are bent to relieve stress?
Precisely. It's a fascinating adaptation to a geometrically challenging situation.
So we've talked about cyclohexane, but what about other cyclic alkanes? Do they always stay perfectly flat?
Great question. They definitely do not.
It's all about finding the most comfortable position for the molecule.
Molecular comfort? Is that a real thing?
Totally. It's all about minimizing strain. Think of cyclobutane.
Okay, 4 carbons in a ring.
If it were flat, you'd have these huge eclipsing interactions. So it puckers.
Puckers how?
It adopts a whispering butterfly conformation. One carbon flips up a bit.
Like wings?
Exactly. Reduces the eclipsing. Cyclopentane does something similar, not flat either.
What shape does that take?
The whispering envelope conformation. One carbon sticks out like the flap of an envelope.
So basically, these molecules wiggle around to avoid being strained?
Precisely. They're always looking for that sweet spot where they're most relaxed.
Interesting. So it is all about comfort. Okay, so we have cyclohexane, cyclobutane, and cyclopentane all trying to get comfy. What about thicker rings?
Larger rings have even more options for conformations.
So how do these rings actually deal with all that strain?
They contort. They adopt non-planar conformations.
Like they bend and twist?
Exactly. They're trying to minimize angle strain, torsional strain, and steric strain.
Okay, so which ring is the most stable?
5-membered rings are happiest, then 6.
What about the smaller ones?
4-membered rings are next, and then, yikes, 3-membered rings.
3-membered rings are super strained, right?
Oh yeah, think cyclopropane. Huge angle strain because the angles are forced to be 60 degrees instead of the preferred 109.5.
Ouch. So they're just trying to rip themselves apart.
Pretty much. Plus, there's torsional strain since all of the CH bonds are eclipsed.
Eclipsed bonds add even more strain?
Big time. 4-membered rings are a bit better. They can pucker to relieve some torsional strain.
So basically, more puckering equals less strain.
Exactly. They're all trying to find the sweet spot, the conformation that minimizes all these strains.
All right, that about wraps it up.
Everyone,
Yeah,
welcome
for
to
sure.
the show.
Thanks,
Rachel, how are you
Rachel.
today?
Thanks for
I'm fantastic. So excited to be here, Ben.
Okay, so we've been dancing around some bigger molecules, but what about the most basic cyclic structure, like cyclohexane?
Cyclohexane. Super important. It's like the gateway to understanding so much of organic chemistry.
Why is that?
It can adopt different shapes called conformations, and that really affects how it reacts.
Conformations? What are the options?
Well, the most famous is the chair conformation. It's the most stable.
Why is it so stable?
It minimizes strain. All the bonds are perfectly staggered.
Staggered is good. Got it. So it just sits there as a chair then?
Not quite. It's actually constantly flipping between 2 chair forms. We call it a ring flip.
Like it's doing gymnastics?
Kind of. And that ring flip becomes super important when you start adding things to the cyclohexane ring.
Like substituents?
Exactly. Dull substituents prefer certain positions, axial or equatorial, and it affects the molecule's properties.
Axial and equatorial. Okay, so basically the shape it likes to be in affects everything it does.
100%. Conformation dictates function, and cyclohexane is the perfect model to understand it.
Okay, so we know what it is and how it moves. Now, how do we actually draw it?
That's a great question. It all starts with understanding the chair conformation itself. Think of cyclohexane, that 6-membered ring, right?
Got it. 6 carbons.
Exactly. Now, each carbon in that ring has 2 types of bonds sticking off of it, axial and equatorial.
Axial and equatorial. What's the difference?
Axial bonds point straight up or straight down, like an axis through the ring. Equatorial bonds point out towards the equator of the ring, more or less horizontally.
Okay, so up and down versus sideways, and each carbon has one of each?
Precisely. 1 axial and 1 equatorial bond. Now, when you're drawing the chair, the trick is getting those angles right.
Angles, huh?
Yep. Now, the lines in the ring shouldn't be perfectly horizontal or vertical. Think of them angled slightly up or down, creating a sort of zigzag pattern.
Zigzag.
Got it. Like a mountain range.
Exactly. Now, when you draw the axial bonds, make sure they're perfectly vertical, pointing straight up or down from each carbon.
Easy enough.
And the equatorial bonds should be angled slightly away from the axial bonds, kind of like they're branching off.
So practice makes perfect, I guess.
Absolutely. And watch out for the common mistakes, like making the ring too flat or drawing axial bonds that aren't perfectly vertical. And remember, every carbon has one axial and one equatorial bond. Keeping that in mind will help you avoid a lot of confusion.
Okay, so molecules are always moving, right? What about cyclohexane?
Oh, cyclohexane does this super cool thing called a ring flip or a chair flip.
Chair flip? Sounds like gymnastics.
Kind of. It's when the cyclohexane ring rapidly converts between two chair conformations.
And why does it do that?
It's all about energy. There's an energy barrier to overcome, but at room temperature, it happens constantly.
So it's like flexing?
Totally. But here's the important part. During the ring flip, axial and equatorial positions get interconverted.
Wait, axial and equatorial? I'm gonna need a refresher.
Axial positions are like sticks pointing straight up and down, while equatorial positions are more angled, sticking out to the sides.
Got it. So they swap places.
Exactly. If you have a cyclohexane with a substituent on it, that substituent will switch from axial to equatorial or vice versa during the ring flip.
So a bigger group would prefer to be in the equatorial position, right?
Yes, that minimizes steric strain, so the molecule spends more time with the bulkier group in the less crowded equatorial spot.
So basically, it's all about avoiding the molecular equivalent of a crowded elevator.
Exactly. And for plain cyclohexane, it doesn't matter. The molecule is symmetrical.
So let's talk about cyclohexanes. Specifically, if you only have one thing stuck to it.
Monosubstituted cyclohexanes. They're not flat.
Right. They're chair-shaped, right?
Exactly. And that one substituent, it really wants to be equatorial if it can.
Equatorial, meaning sticking out to the side?
Yes. Think of it as pointing outwards from the equator of the ring.
Why does it prefer that?
It's about space. Axial, sticking up or down, creates these 1,3 diaxial interactions.
Wait, 1,3 diaxial? Break that down.
It means the substituent is on carbon 1 and it bumps into the axial hydrogens on carbons 3 and 5.
Oh, so it's like steric crowding.
Precisely. The bigger the substituent, the worse the crowding.
So there's got to be a way to measure this preference, right?
Yes. It's called the A value. It tells you how much a substituent wants to be equatorial.
Is there like a chart of these?
Absolutely. Hydrogen has an A value of 0, obviously, because it doesn't really prefer to be anywhere.
Makes sense. What about something bigger, like methyl?
Methyl's around 1.7. A tert-butyl group? Huge. It's over 5. Basically locked equatorial.
Wow. Okay, so basically A values tell you how much a group hates being axial due to these 1,3 interactions.
Exactly. And that has major consequences for reaction outcomes and the shapes of molecules.
Okay, so let's look at di-substituted cyclohexanes, specifically cis and trans 1,4-dimethyl cyclohexane. What's the deal with those?
These are great for understanding conformation. Remember, a cyclohexane wants to minimize steric strain.
Right, like the chair conformation we talked about earlier.
Exactly. So with the dimethyl cyclohexanes, we have to consider which conformation is preferred. It all boils down to diaxial interactions.
Diaxial? What are those exactly?
They're steric clashes that happen when substituents are in the axial position on the cyclohexane ring.
Okay, so how does that affect the cis versus trans?
For the cis isomer, one methyl group will be axial and one will be equatorial.
And the trans?
Trans has both methyl groups equatorial or both axial. but diaquatorial is much more stable due to fewer diaxial interactions.
So trans is more stable?
Generally, yes. The trans isomer is more stable than the cis isomer in 1,4-dimethyl-cyclohexane.
Got it. So basically it all comes down to minimizing those diaxial interactions, right?
That's the key takeaway. Think about which conformation puts the bulkier groups in the less crowded equatorial positions.
Okay, so basically what you're saying is that we need to minimize those flag-pull interactions.
Exactly. You want to look at which conformer will essentially have less bumping into each other.
Perfect. Okay, so we've got these chairs and things sticking out, but what about those weird dash and wedge notations? What do they even mean?
Those are super important. They tell you if something's pointing up or down relative to the ring.
Up or down, like on the z-axis?
Exactly. A wedge means it's coming out towards you, above the plane of the ring.
Okay, so it's popping out.
Yep. And a dash means it's going away from you, below the plane.
Got it. So wedge is up, dash is down. Pretty simple.
But here's the crucial thing. Dash and wedge is not the same as axial or equatorial. They're totally independent.
Wait, really? I thought they were connected somehow.
Nope. Dash, axial, and equatorial tell you if it's sticking straight up, down, or out to the side.
And dash and wedge tells you if it's generally above or below the ring. So you could have an axial group pointing up with a wedge or pointing down with a dash.
Exactly. Think of it like this. Axial equatorial is the street address. Dash and wedge is the floor number in the building.
Okay, I like that analogy. So it's all about spatial orientation, right? Up versus down?
Precisely. Dash and wedge just says which direction is generally pointing in space. Don't mix it up with axial or equatorial.
Okay, so let's recap. What's the main thing we need to remember about cyclohexane conformations?
It's all about the equatorial positions. The more substituents in those spots, the more stable the molecule. Period.
Even if there are tons of substituents, like quantity over identity?
Exactly. It doesn't matter what the substituents are or how many there are. Equatorial wins.
So it's just about minimizing that steric clash, that 1,3-dioxyl interaction we talked about earlier?
Yep, that's the driving force. Think of it like everyone wanting their own elbow room at a crowded table.
And this impacts more than just stability, right?
Big time. It affects reaction rates, what products you get, basically everything. If you have a bulky group locked in an axial position, it can block a reaction from happening.
So like a molecular traffic jam?
Precisely. Understanding these conformations lets you predict how a molecule will behave.
Okay, got it. So basically, cyclohexene conformations aren't just some academic exercise. They really matter in the real world.
Absolutely. It's fundamental to understanding organic chemistry and how molecules interact.
Awesome. Thanks for breaking it down for us.
All right, that about wraps it up.
Yeah,
welcome
think
to the
so.
show.
Thanks, Rachel.
Ben, how are you doing today?
I'm doing great, Rachel. Really excited to be here.
So we've been talking about molecules, but what happens when the same atoms arrange themselves in different ways?
That's where stereochemistry comes in. It's the study of how molecules are arranged in 3D space. And it matters a lot.
How so?
Because the arrangement affects a molecule's properties, how it interacts with other molecules, everything.
Wait, so same atoms, different arrangement, totally different behavior?
Exactly. Think of it like Legos. You can have the same Lego bricks, but build completely different things depending on how you put them together.
Okay, I'm picturing it. So a Lego car versus a Lego spaceship. What's the molecule version of that?
Those are called isomers. They have the same chemical formula, same atoms, but different arrangements.
Isomers. Got it. So they're like molecular twins, but not really twins.
A good way to put it. And these differences, they can be subtle or dramatic.
Give me an example of dramatic.
Well, there's limonene. One isomer smells like lemons, the other like oranges.
No way. Same molecule, different smell.
Yep. That's stereochemistry in action. A slight change in arrangement, a completely different sensory experience.
Okay, that's a great example. So basically what you're saying is
Arrangement is everything.
Pretty much. It dictates how a molecule interacts with the world. And that has huge implications, especially in biology and medicine.
So, isomers. They're like molecules with the same formula but act totally different, right?
Exactly. Think of it like rearranging Lego bricks. You still have the same pieces, but different structures.
Okay, so what types are there?
Constitutional and stereoisomers. Constitutional isomers are connected differently.
Different connections? Give me an example.
An ether versus an alcohol. Same atoms, different linkages.
So, like ethanol and dimethyl ether?
Precisely. Same formula, wildly different properties. Stereoisomers, on the other hand.
Same connections?
Yep, but different 3D arrangements. Like your hands, mirror images, but not superimposable.
Ah, like chiral molecules.
Exactly. We use dashes and wedges to show that 3D configuration.
Dashes and wedges? What's the difference?
Wedges come out of the page, dashes go back. It's key for visualizing those spatial differences.
Got it. So basically, constitutional isomers, different connections. Stereoisomers, same connections, different shapes.
Boom. You nailed it. It all comes down to how those atoms are arranged.
So let's talk enantiomers now. What exactly are we talking about?
They're basically molecules that are mirror images of each other.
Okay, like a left and right hand?
Exactly. Except they can't be superimposed.
Non-superimposable? What does that even mean?
It means you can't rotate them and make them look identical.
So, like, I can't just flip it around?
Nope. Think about your hands. No matter how you turn them, they won't perfectly align.
Got it. So how do I figure out if two molecules are enantiomers?
Try to visualize rotating one to match the other. If you can't, they're enantiomers.
Is there a more scientific way?
Well, you can build models or use software to rotate them in 3D.
Okay, that makes sense. Now, what's chirality?
Chirality is the property of a molecule being non-superimposable on its mirror image.
So enantiomers are chiral.
Yes, a chiral molecule is one that exists as enantiomers.
And what makes a molecule chiral versus achiral?
Symmetry. Achiral molecules have a plane of symmetry. Think of it like cutting something in half and both halves are mirror images.
Okay, like a sphere.
Exactly. Cut it anywhere and you'll get two identical halves. Chiral molecules lack that symmetry.
So basically, if it's symmetrical, it's achiral, otherwise chiral.
Precisely. And that chirality can have huge implications.
Okay, so we've talked about identifying enantiomers. How do we figure out what's actually chiral in a molecule?
That usually comes down to finding a chirality center, also called a stereocenter.
Okay, what's the rule?
An atom, usually carbon, bonded to 4 different groups.
4 different things attached.
Exactly. That's the key. It has to be 4 different groups. If even 2 are the same, it's not a chirality center.
Got it. So find a carbon with 4 unique attachments.
Yep, and that's the most common case, but chirality can arise in other ways too.
Like what?
Think about molecules where rotation is restricted.
Restricted how?
Like alkenes. They have these double bonds that are oriented in such a way that the substituents are forced to be on opposite sides.
And that creates chirality?
If the groups on each end are different, then yes. Or biaryls. Think of 2 benzene rings connected by a single bond, but with bulky groups preventing them from rotating freely.
So the rings can't spin.
Right. And that restriction creates a chiral axis.
Okay, so chirality isn't just about that carbon atom thing.
Not always. It's about the overall 3D arrangement and whether the mirror image is superimposable. Chirality centers are just the most common cause.
Okay, so we can tell if a molecule is chiral, but how do we actually name these different forms?
That's where the CIP system, or Kohn-Engel prelog, comes in. It's how we assign absolute configurations, R or S, to chiral centers.
R and S? Like
right and left?
Sort of. Think of it more like clockwise and counterclockwise.
Okay, so how does this CIP thing work?
First, you assign priorities to the 4 groups attached to the chiral center.
Priorities? Like, based on what?
Atomic number. Higher atomic number gets higher priority. So bromine beats chlorine, chlorine beats oxygen, and so on.
Got it. Bigger atom, bigger priority.
Exactly. If 2 atoms are the same, you look at what they're bonded to, and so on until you find a difference.
Okay, that makes sense. What's next?
Then you orient the molecule so the lowest priority group is pointing away from you.
Like, imagine it's going into the page?
Yes. Now trace a path from the highest priority group to the second highest, then to the third.
And if that path is clockwise?
Then it's R. If it's counterclockwise, it's S.
Okay, so R versus S is all about spatial arrangement and this CIP priority system.
Precisely.
Okay, so we've got the basic idea of the CIP rules down. But what happens when 2 atoms directly attached to the chiral center are the same?
That's where things get interesting. You look at the atoms attached to those atoms. It's like following a chain.
A chain? So keep going until you find a difference?
Exactly. You compare the chains of atoms bonded to each substituent, atom by atom, until you find the first point of difference.
Okay, so you're not just looking at what's directly attached. It's the whole group that matters.
Precisely. And the higher atomic number at that first point of difference wins.
Got it. What about isotopes? Do those affect priority?
Absolutely. Isotopes have different atomic masses. Deuterium, which is hydrogen 2, outranks regular hydrogen.
Oh, interesting. What else messes with this? What about lone pairs?
Lone pairs are treated as having an atomic number of 0. They always lose.
So they're like the ultimate tiebreaker.
Yep. And multiple bonds? Those get special treatment too.
How so?
A double bond is treated as if that atom is bonded to 2 of the atoms it's double bonded to. A triple bond? 3.
Wait, really? So you're artificially inflating the number of connections.
Exactly. It's to account for the higher electron density.
Okay, that makes sense. So basically, what you're saying is go down the chain, find the first difference, isotopes matter, lone pairs lose, and multiple bonds get extra credit.
You nailed it. It's all about systematically comparing the groups attached to that chiral center.
Okay, but what if the lowest priority group isn't conveniently pointing away from us? Are we just stuck?
No way. You can reorient the molecule in your mind or on paper. It's like rotating a Rubik's Cube until you get the view you need.
Okay, I can picture that, sort of. Got an example?
Sure. Let's say you have a chiral center with hydrogen, deuterium, methyl, and ethyl groups. If the deuterium is pointing towards you, mentally swap it with the group pointing away.
Deuterium, as in heavy hydrogen?
Exactly. It's hydrogen with an extra neutron, so it's heavier. That makes it higher priority than regular hydrogen.
So swap deuterium and the group pointing back, then assign priorities and determine R or S configuration like before.
Precisely. Just remember, since you swapped, the configuration you get is actually the opposite of the true configuration.
Wait, really? You have to reverse it?
Yep. Since you swapped, if you get R, it's actually S, and vice versa. Always double check.
Got it. So, any other super important reminders before we wrap this up?
Definitely. Always examine the atoms directly attached to the chiral center first. That's key.
Right. And then keep going outward if you need to until you find a difference.
Exactly. And remember the general priority order. Higher atomic number usually wins. So like oxygen beats carbon, chlorine beats oxygen, and so on.
Okay. Periodic table knowledge is key. Got it.
You got it. Just remember those basics, practice a bunch, and you'll be assigning R and S configurations like a pro in no time.
Well, that's probably a good place to stop for today.
Yeah, I think so.
Welcome to the
Thanks,
show. Ben, how are you doing today?
I'm doing awesome, Rachel. Thanks for having me.
Okay, so before we dive into the challenging stuff, let's make sure we're all on the same page with the basics of stereochemistry. What are the key things we need to remember?
Absolutely. We need to be solid on assigning priorities, especially when multiple bonds are involved.
Right, priority assignments. That's the CIP rules, right?
Exactly. And remember, a double bond counts as 2 single bonds to that atom. A triple bond counts as 3.
Okay, got it. Multiple bonds get duplicated. What else?
Knowing the difference between enantiomers and diastereomers is crucial.
Enantiomers are mirror images, right? And diastereomers are...
stereoisomers that aren't mirror images. And finally, calculating the maximum number of stereoisomers.
which is 2 to the power of n, where n is the number of stereocenters.
Precisely. So if we have a molecule with 2 stereocenters,
Then the maximum number of stereoisomers is 4.
you nailed it. Now that we've recapped the basics, we can get into the more interesting stuff.
Okay, so we know how to assign priorities to single bonds, but what happens when we have double or triple bonds?
Good question. Multiple bonds get special treatment. We treat them as if they're bonded to multiple single atoms.
Wait, what does that even mean?
Okay, think of a carbon double bonded to oxygen, a carbonyl. We treat that carbon as if it's bonded to 2 oxygens.
2 oxygens? Really?
Yep, and the oxygen is also considered bonded to 2 carbons. We create these phantom atoms to account for the pi bond.
Phantom atoms. I like that. So triple bonds would have even more?
Exactly. A carbon triple bonded to nitrogen would be treated as bonded to 3 nitrogens and vice versa.
Okay, so basically we're converting those pi bonds into sigma bonds for priority assignment.
You got it. It's like temporarily rewriting the molecule to make the Kahn-Ingold prelog system work with multiple bonds.
That makes sense. So we look at these phantom atoms to determine priority, right?
Yes, and it's crucial to remember that these are just for assigning priority. They don't change the actual molecule.
Okay, so what happens when we have a tie? Like 2 groups are the same.
That's where the fun begins. We use tie-breaking rules.
Tie-breaking rules. Got it. Lay it on me.
Imagine 2 groups tied at the first atom. We look at what's directly attached to each of those atoms.
Okay, so we're going a level deeper.
Exactly. We compare those attached atoms by atomic number again.
And if those are tied too?
Keep moving along the chain, atom by atom, until you find a difference.
So it's like tracing each branch until one is heavier than the other.
Yes, the group with the heavier atom at the first point of difference gets higher priority.
Okay, that makes sense. So basically, keep going until something is different.
Precisely. It might take a few steps, but you'll eventually break the tie.
What if the chain ends before the tie breaks?
If one chain is shorter, we treat the missing atoms as having an atomic number of 0.
0, as in lower than anything else.
Exactly. So the longer chain wins the tie.
Okay, so how do we actually draw these enantiomers?
There are a couple ways. The first is the mirror image method. Just draw the molecule and then draw its reflection.
Like holding it up to a mirror?
Exactly. The other is configuration inversion.
Inversion? What's that mean?
You flip the configuration at every chiral center. So if it's R, it becomes S and vice versa.
Wait, every chiral center?
Yeah.
What if there's like 5?
You gotta flip them all. That's key for getting the true enantiomer. If you only flip some, it's a diastereomar, which is a whole other thing.
Gotcha. So mirror image or flip everything. Which is easier?
Mirror image is usually more intuitive, especially for beginners, but inversion is useful for complex molecules when visualizing the mirror image gets tricky.
Good to know there are options. Any tips for getting better at this?
Practice, practice, practice. And use models. Build the molecule and its mirror image. It really helps solidify the concept.
Okay, so how do we actually use stereocenters in like a practical way?
That's where switching rules come in. They're super handy for predicting configuration changes.
Switching rules? What's that?
Imagine you have a chiral center. If you swap two groups attached to it, the configuration inverts.
Inverts, meaning R becomes S and vice versa?
Exactly. That's the one-switch rule.
Okay, one switch flips the configuration. Makes sense. What about the two-switch rule?
If you make two switches, you're back to the original configuration. R stays R, S stays S.
So it's like doing a 180-degree turn, then another 180. You end up facing the same way.
Precisely. These rules make assigning configurations much easier, especially with complex molecules. You can move things around to simplify the view.
So switching helps us see the molecule in a way that's easier to assign R or S.
Yep. Think of it as a shortcut. It's so easy.
Cool. So basically, switch once, flip the stereocenter. Switch twice, it stays the same.
Okay, so let's look at something a little more complex. How do we handle a nitro group, a C triple bond N?
Yes, nitriles. That triple bond makes things interesting. We have to unpack it.
Unpack it? What does that mean?
Think of it like this. That carbon is bonded to 3 nitrogens, and the nitrogen to 3 carbons for priority purposes. We treat it as if those bonds are actually there.
Wait, so it's not really bonded to 3, but we pretend it is for assigning priority?
Exactly. Then you just compare atoms directly attached. Is nitrogen higher priority than, say, a carbon that's part of an ethyl group?
Got it. So we're comparing nitrogen against carbon in that case, and nitrogen wins because it has a higher atomic number.
You've nailed it. It's all about that first point of difference. Unpack those multiple bonds and compare.
Okay, unpacking bonds. I like that. So the key is not to be intimidated, but break it down step by step.
Precisely. A lot of organic chemistry is just that. One careful step at a time.
So what about diastereomers and enantiomers? I always mix them up.
They're both stereoisomers, but they differ in their mirror image properties.
Mirror image? Like one reflects the other?
Exactly. Enantiomers are non-superimposable mirror images. Think of your hands.
Got it. And diastereomers?
They are stereoisomers that are not mirror images.
Okay, so how do their chiral centers play into this?
Enantiomers have inverted configurations at all chiral centers. Every single one flips.
And diastereomers don't?
Only some are inverted. Not all of them change configuration.
Does this difference affect their properties?
Big time. Enantiomers share most physical properties except how they interact with polarized light.
Oh yeah, optical activity.
Exactly. Diastereomers, because they are different molecules, have different physical properties.
So different melting points, different solubilities, everything.
Precisely. That's how you can tell them apart. For example, if one chiral center is inverted in a molecule with 2 chiral centers, it is a diastereomer, leading to distinct properties.
So how can we easily tell if 2 stereoisomers are related without figuring out the R and S configurations?
That's where the one-switch rule is handy. It lets you determine the relationship by just looking at the patterns.
Okay, how does this one switch thing work?
Basically, you compare how the substituents are arranged around each chiral center. If only one switch is needed to match them, they're enantiomers.
Wait, only one switch? What if it takes more?
If it takes more than one, but they're not identical, they're diastereomers. If no switches are needed, they are identical.
So basically, it's like a shortcut to see if they are mirror images or not.
Exactly. It skips the whole R and S naming, focusing on the relative arrangement.
Got it. So enantiomers are one switch away, diastereomers are more than one, and identical needs no switch. Makes sense. I love that.
Yes, and it's super useful for quick analysis, especially when dealing with complex molecules.
Okay, so if we want to figure out the number of possible isomers, how do we do that?
There's a handy rule, 2 to the power of m.
2 to the what now?
2 to the power of n.
Where n is the number of stereocenters in the molecule?
Stereocenters.
Is that like chirocenters?
Exactly. Each stereocenter can have 2 possible arrangements.
Got it. So 2 options for each stereocenter.
Right. So if you have 2 stereocenters, it's 2 squared.
Which is 4. So a max of 4 stereoisomers?
Yep. But, and this is important, that's just the maximum number.
Oh, there's a catch.
Yeah, meso compounds. They have stereocenters, but are achiral.
Wait, how does that work?
They have a plane of symmetry that cancels out the chirality.
So the 2 to the n rule is a good starting point, but not perfect.
Exactly. Always check for meso compounds.
Okay, let's wrap things up. So basically, we've covered how Google's AI found that ancient vulnerability. It was in FFmpeg, right?
Exactly. An old codec. Google found it.
And even though it was an ancient vulnerability, Google still reported it.
Yes.
Well, that about wraps things up here.
Yeah, for sure.
Thanks, Ben.
Ben,
Thanks for having me.
how are you doing today?
I'm doing fantastic, Rachel. Thrilled to be here.
Okay, so we've talked about all kinds of molecules, but what about how they're arranged in 3D space?
That's stereochemistry. It's all about the spatial arrangement of atoms and molecules and how that affects their properties.
So, does it really matter?
Absolutely. The 3D structure can dramatically change how a molecule interacts with other molecules, especially in biological systems.
Wait, give me an example.
Think about drug design. 2 stereoisomers of a drug might have completely different effects. One might cure a disease, the other could be toxic or inactive.
No way! So it's that important?
Critical. And stereochemistry explains differences in physical properties too, like melting point or boiling point.
Okay, so what are some key things we need to know about it?
Well, we can talk about mesocompounds. They're molecules with chiral centers that are actually achiral overall.
Whoa, how does that work?
They have an internal plane of symmetry that cancels out the chirality. Then there are cis-trans isomers, or EZ isomers.
Okay, I've heard of those, but remind me.
Cis-trans applies to substituted rings or alkenes, where substituents are either on the same side or opposite sides. EZ is a more general system for alkenes. And we already mentioned physical properties, how stereoisomers can differ.
So basically, the 3D shape of a molecule is just as important as its formula.
Exactly. Shape determines function, especially in biological systems. Messing with the shape means messing with the function.
Okay, so what about molecules that have stereocenters but aren't chiral? Is that even possible?
It is. We call them meso compounds. They have stereocenters, but also have an internal plane of symmetry.
Wait, a plane of symmetry inside the molecule itself?
Exactly. Think of tartaric acid. It can have two chiral centers, but a specific form of it has a mirror plane running right through the middle.
So that makes it not chiral?
Yep. The two halves are mirror images, canceling each other's optical activity.
It's like the two chiral centers are fighting each other and nobody wins?
That's a great way to think about it. The rotation caused by one stereocenter is exactly opposed by the other.
So how do you spot a meso compound?
Look for stereocenters, then see if the molecule can be sliced in half so each side looks like the mirror image of the other.
Okay, so stereocenters plus internal symmetry equals meso. Medium pause. Got it.
Precisely. It's like carbon dioxide, actually.
Carbon dioxide. How so?
The two oxygen atoms pull equally in opposite directions. They cancel each other's dipole moments, making the molecule nonpolar overall.
Oh, I see. Medium pause. Symmetry canceling polarity. Medium pause. It's the same idea.
Exactly. Symmetry has powerful consequences, whether we're talking about polarity or chirality. It's all interconnected.
So double bonds can also have stereoisomers, right?
Exactly. That's where cis-trans and EZ nomenclature comes in.
Okay, but what's the difference? When do I use which one?
Cis-trans is for simple alkenes. Think of it like this. If the two biggest groups are on the same side, it's cis. Opposite sides, it's trans.
Got it. So like two methyl groups on the same side of the double bond.
Precisely. But when you have more complex molecules, that's where EZ comes in.
And EZ is?
It's based on the CIP priority rules.
CIP? What are those?
Can encode prelock. It's a system for assigning priority based on atomic number.
Okay, so heavier atoms get higher priority.
Yes, the higher the atomic number, the higher the priority. If the higher priority groups are on the same side, it's Z. If they're on opposite sides, it's E.
Z and E, why those letters?
From German, zusammen means together for Z, and entgegen means opposite for E.
Ah, that makes sense. Can we do an example?
Sure. Imagine a double bond with a chlorine on one side and a methyl group on the same carbon. On the other side of the double bond, we have a bromine and an ethyl group.
Okay, I'm picturing it.
Chlorine beats methyl because chlorine has a higher atomic number. And bromine beats ethyl for the same reason. So bromine and chlorine are on the same side.
So that's the Z isomer.
Exactly. Higher priority groups on the same side, therefore Z.
Okay, so we know stereoisomers have the same connectivity, but different arrangements. How different are they, really? Like, do they act the same in the real world?
Great question. It really depends on which type of stereoisomers we're talking about. Enantiomers, diastereomers, they have distinct physical properties.
Okay, break it down. What's different?
Melting point is a big one. Diastereomers can have drastically different melting points. Enantiomers, not so much. Their melting points are usually identical.
Wait, really? Why?
Because melting point is affected by intermolecular forces. Diastereomers have different shapes, therefore different forces. Enantiomers, mirror images, identical forces.
Got it. What about something like, I don't know, how they interact with light?
Optical rotation. This is where enantiomers shine, literally. Enantiomers rotate plane polarized light in equal but opposite directions. Diastereomers, they can rotate light, but the amount and direction are completely unrelated.
So enantiomers rotate light. Diastereomers maybe do, maybe don't. What happens if you have a 50-50 mix of enantiomers?
That's a racemic mixture, and it's optically inactive. The rotations cancel each other out.
So, like zero rotation.
Exactly zero. Now, here's where it gets interesting. Separability. Diastereomers have different physical properties, like we said, so you can use normal techniques to separate them. Enantiomers, trickier.
Because they're so similar?
Precisely. You need special techniques like chiral chromatography to separate enantiomers.
Chiral chromatography. Sounds expensive.
It can be.
Okay, so how do we actually draw these chiral molecules? I mean, on paper.
That's where Fisher projections come in. They are a simplified way to represent 3D stereocenters in 2D.
Simplified how?
Well, imagine a carbon atom as a cross. The horizontal lines are coming out towards you, and the vertical lines are going back, away from you.
So, like popping out and receding?
Exactly. Now, the intersection of the lines is the carbon.
Got it. Cross equals carbon, horizontal is forward, vertical is back.
You got it. And each end of the line is a different atom or group attached to that carbon.
Okay, so I can just draw any molecule like that?
If it has a chiral center, yes. The projection clearly shows the spatial arrangement.
Can we do an example?
Sure. Let's say we have a carbon connected to a hydrogen, a hydroxyl group, a methyl group, and a chlorine.
Okay, I'm picturing it.
We can draw that as a Fisher projection, with the carbon at the center, the hydrogen and hydroxyl on the horizontal, and the methyl and chlorine on the vertical.
And that tells us the stereochemistry?
It does. We can use this to determine if it's R or S.
How does that work?
You assign priorities to the groups based on atomic number. Then, if the priorities are going clockwise, it's R. Counterclockwise, it's S.
So, Fisher projections make it easy to see the 3D arrangement and figure out R and S.
That's the idea. They're super useful for visualizing stereochemistry.
Okay, so how do we actually figure out these relationships? I always get mixed up.
That's where the flow chart comes in handy. It breaks it down step by step.
A flow chart? I like the sound of that.
First, check if the molecular formulas are the same. If not, they're constitutional isomers.
Easy enough.
Next, if the formulas are the same, see if they're superimposable.
Superimposable, meaning?
Exactly the same molecule, just rotated. If they are, you're done.
Got it.
If they're not superimposable, check for a plane of symmetry. This is key for identifying mesocompounds.
Mesocompounds? What are those again?
Mesocompounds are molecules with chiral centers, but they're achiral overall due to that internal plane of symmetry.
Ah, sneaky.
Super sneaky. If there's a plane of symmetry, it's a mesocompound. If not, they're enantiomers or diastereomers.
Okay, almost there.
Finally, if they're non-superimposable and lack a plane of symmetry, check if they're mirror images. If yes, they're enantiomers. If no, they're diastereomers.
Mirror images equals enantiomers. Anything else is diastereomers. I think I got it.
Precisely. The flowchart just organizes the steps to avoid confusion. It works like a charm.
So basically, the flowchart is a foolproof way to classify these molecules, right?
Absolutely. It's a systematic approach that eliminates guesswork.
Well, that's a lot to think about.
Yeah, for sure.
Welcome.
Thanks,
Ben, how are you doing today?
I'm doing awesome, Rachel. Thanks for having me.
Okay, so how do chemists actually show these reactions happening?
That's where curved arrow notation comes in. Think of it like the language of electron movement.
Electron movement. Got it. So arrows show where electrons are going.
Exactly. The tail of the arrow shows where the electrons are coming from.
And the head shows where they're going?
Precisely. It's all about tracking that electron flow.
So it's like a little electron roadmap.
You got it. And there are a few canonical arrow patterns you really need to master. Think of them like grammar rules.
Grammar rules for chemistry. That sounds intense.
It's not so bad, really. They just help you keep track of everything. And following the electron flow template is crucial.
Electron flow template. What's that?
It's the overall pattern of electron movement in the reaction. Mess that up and you'll get the wrong product every time.
So accuracy is key?
Absolutely. Mastering these arrows is essential for understanding organic chemistry.
Okay, so arrows show electron movement, master the patterns, and follow the electron flow template. Got it. So what are some of these canonical arrow patterns? Okay, so how do we actually use these structures to predict reactivity?
That's where curved arrows come in. They show electron movement.
Like a little electron roadmap?
Exactly. And there are three main patterns: lone pair to bond, bond to lone pair, and bond to bond.
Okay, let's break those down. Lone pair to bond first?
That's where a lone pair of electrons forms a new bond. Think of it like two people holding hands. They were separate. Now they're connected.
Got it. What's next?
Bond to lone pair. The opposite of that. A bond breaks, and those electrons become a lone pair on an atom.
So, like, two people stop holding hands and walk away from each other?
Perfect analogy. And the last one is bond to bond.
Which is?
A bond breaks, and those electrons form a new bond somewhere else.
So, a bond shifting positions.
Precisely. Think of it like musical chairs with electrons.
Okay. So, basically, electrons are either making new bonds, breaking old bonds to become lone pairs, or reshuffling bonds to make new connections.
Yep. Master those three arrow patterns and you're well on your way.
Okay, so how do we actually draw these mechanisms correctly? Like, what are the key things to keep in mind?
Great question. First, show all lone pairs. They're crucial for seeing where electrons are coming from. Don't hide them.
So, literally draw every single lone pair on every atom.
Yes, absolutely. Second, show explicit hydrogens. I know it's tempting to leave them off, but they participate in reactions all the time.
Even the ones bonded to carbon.
Especially those. Third, conserve charge. The overall charge at the beginning of your mechanism must equal the overall charge at the end.
Okay, makes sense. So, like, if I start with a neutral molecule, I better end with the neutral molecule or the appropriate ion.
Exactly. And keep track of your electron count. Make sure you're not creating or destroying electrons out of nowhere.
How do you even keep track of that?
Count them as you draw the arrows. Each arrow represents 2 electrons moving. So if you break a bond, that's 2 electrons going somewhere.
Okay, so lone pairs, explicit hydrogens, conserve charge, and track electrons. Got it. Is there anything else that trips people up?
Arrow direction. Arrows always go from electron rich to electron poor, never the other way around. It's like saying the rich give to the poor.
Okay, that's a good way to remember it. Rich to poor, like electron Robin Hood.
Perfect. And don't forget to draw the resulting product of each step, even if it's just an intermediate. It shows the progression.
Okay, so walk us through this arrow pushing template. What's step 1?
First, find where the change is actually happening. Which bonds are breaking or forming?
Got it. So focus on the action.
Exactly. Step 2, add in any missing lone pairs and hydrogens. People forget this constantly.
Why is that so important?
Because you need to see all the electrons to track them properly.
Makes sense. What's next?
Figure out the electron source and sink. Where are the electrons coming from and where are they going?
How do you determine that?
Electrons flow from areas of high electron density, like lone pairs or pi bonds, to areas of low density.
So negative to positive, basically?
In a simplified way, yes. The arrow starts at the source, ends at the sink.
And the final step?
Recalculate formal charges. Electrons have moved, so charges likely changed.
Okay, so basically track the electrons, update the charges. Got it.
Yep, and that's it. Follow those steps and mechanism arrows become way less scary.
So, can you give me some examples of these micro mechanisms in action?
Absolutely. Let's start with methoxide interacting with magnesium 2+.
Okay, walk me through it.
The methoxide oxygen, which is negatively charged, donates electrons to the positively charged magnesium ion.
Makes sense. What happens then?
The methoxide forms a coordinate bond with the magnesium, neutralizing some of its positive charge.
Got it. Another one?
Alkoxide reacting with BH3.
Boron, right?
Exactly. The alkoxide oxygen donates electrons to the boron, forming a new bond.
And the charge changes?
Yes, the boron becomes negatively charged. Here's another. Tert-butyl bromide heterolysis.
Hetero what?
Breaking a bond where both electrons go to one atom. The bromine takes both electrons, becoming negatively charged.
And the butyl becomes positive?
Correct. One last quick one. Sulfur attacking a carbonyl.
Like an SN2 reaction?
Similar electron flow,
the sulfur's lone pair attacks the carbonyl carbon.
Shifting electrons to the oxygen.
Exactly, giving the oxygen a negative charge.
What are some typical mistakes people make when drawing these arrows?
Octet violations are super common. Forgetting that atoms can't have more than 8 electrons.
Right, the octet rule.
Yeah, I see it all the time. Like, say we have a sulfur atom with a lone pair attacking a carbon-bromine bond.
Okay.
People will draw the sulfur lone pair attacking the carbon directly, kicking off the bromine.
And what's wrong with that?
The carbon ends up with 10 electrons. It breaks the octet rule.
Ouch. Okay, so how should we draw it instead?
The sulfur lone pair attacks the back of the carbon, pushing the bromine off in a concerted step.
So the arrow has to start at the lone pair and go to the back of the carbon.
Exactly. It's all about showing the electrons moving in a way that doesn't violate the octet rule.
Got it. Any other common mistakes to watch out for?
Forgetting formal charges can be a big one. Also, not using arrows to show the actual electron movement.
Okay, so how do we keep track of formal charges when we're drawing these arrows?
Great question. Curved arrows show electron movement, right? So formal charges shift based on where the arrow starts and ends relative to an atom.
Explain that a bit more.
If an arrow points toward an atom, it gains negative charge. Away, it loses negative, which means it becomes more positive.
Got it. So give me an example.
All right, alkoxide plus lithium. Oxygen starts negative, lithium is positive, arrow goes from O to Li.
And what happens?
The oxygen's negative charge neutralizes the lithium's positive charge. They're now neutral formally.
Simple enough. Another?
CBr bond heterolysis. The arrow starts on the bond and points to the bromine.
Bromine gets the electron.
Yep. Bromine goes from neutral to negative. The carbon bonded to it becomes positive.
Okay, one more.
Chloride ion attacking dimethyl ether. Chlorine's negative, attacks a carbon on the ether.
What's the charge change?
Chlorine becomes neutral as it forms a bond. The oxygen in the ether, it gains a positive charge. Charge conservation.
So basically track where the electrons go and the formal charges shift accordingly. Okay, so drawing these mechanisms, it's all about showing where the electrons are actually going, right?
Exactly. You have to show electron flow, source to sink. It's a story.
A story? Like a tiny electron novel?
Totally. And a good mechanism drawing is clear. You can follow where they're going.
What are some things people mess up?
Oh, tons. Like arrows pointing the wrong way.
Or forgetting charges. So basically chaos.
Mechanism anarchy. But here are some quick checks to prevent that.
Okay, I'm ready.
First, octet rule. Does everyone have their happy number of electrons? No one breaking the rules.
Got it. Electron accounting.
Next, source and sink. Is it clear where those arrows start and end? Like a specific atom and bond?
No vague arrows.
Precisely. Finally, charge shifts. If you move electrons, charge must change.
Okay, so arrows show electrons. Electrons dictate charge. Okay, got it.
You can almost derive the full mechanism from the charge changes alone.
Wait, really?
Yeah, it's like the story's skeleton.
That's a crazy way to think about it.
All right, that was a lot.
Yeah, for sure.
Back to the show.
Thanks, Ben.
Ben, how are you doing today?
I'm doing fantastic, Rachel. Super excited to be here.
Okay, so we're talking about organic chemistry. What exactly is a reaction mechanism?
It's basically a step-by-step breakdown of how a chemical reaction happens.
Like every single little movement of electrons?
Exactly. It shows which bonds break, which bonds form, and the order it all happens in.
So it's like a recipe for a chemical reaction.
That's a great analogy. And knowing the mechanism helps us predict what products we'll get.
Okay, makes sense. What are some of the key things we need to understand about mechanisms?
Well, first, we need to distinguish between intermolecular and intramolecular reactions.
Inter versus intra. Remind me.
Intermolecular means between two different molecules. Intramolecular is within the same molecule.
Got it. So like two cars crashing versus a car falling apart.
Perfect. We also need to understand curved arrows.
Curved arrows? Is that like some secret code?
Kind of. They show how electrons move during the reaction. The arrow starts where the electrons are and points to where they're going.
So it's like a little electron traffic controller?
Precisely. And we also need to remember resonance.
Oh, man, resonance structures. Those always confused me.
Think of it like this. Sometimes a single Lewis structure can't fully describe a molecule. So, resonance shows all the possible ways to draw it.
So it's like the molecule is a hybrid of all those different structures?
Exactly. And recognizing resonance helps us understand where electrons are more likely to be.
Okay, curved arrows show electron movement during the reaction, and resonance helps us know where the electrons are generally. Am I getting this?
You've got it. Understanding these concepts is key to unlocking the secrets of organic reactions.
Okay, so we've talked about reaction mechanisms and catalysts, but how do we determine if a reaction will even happen in the first place?
That's where considering inter versus intramolecular reactions comes in. It's all about whether the reaction happens between two separate molecules or within the same molecule.
Wait, two different molecules versus one single molecule.
Exactly. Intermolecular reactions involve two or more separate molecules reacting together. Think of it like two people meeting for the first time and forming a connection.
Okay. And intramolecular is...
Intramolecular is when the reaction happens within a single molecule. It's like a person finding a new hobby. The change happens within them.
So what difference does it actually make?
A huge difference in the product formed. Intramolecular reactions often lead to ring formations. The molecule sort of folds in on itself.
Like making a tiny molecular bracelet.
Yes, exactly. Intermolecular reactions, on the other hand, usually link molecules together to create larger chains or networks.
So basically, intramolecular is fold. Intermolecular is link.
A great way to think about it. The concentration of the reactants also plays a big role. Intramolecular reactions are often favored at low concentrations.
Why is that?
Because the reactive parts of the molecule are already close to each other. They don't have to find each other in a sea of other molecules.
That makes sense.
Understanding these distinctions is critical for predicting what products you'll get from a reaction. It's like knowing whether you're inviting people to a party or just planning a solo night in.
Whispering. Okay, so inter versus intramolecular is all about who's reacting with whom. Got it. Now, what if we want a specific product?
Okay, so we can see where the electrons are moving, but how do we show that on paper?
That's where curved arrows come in. They show electron flow during reactions.
Like a little GPS for electrons?
Exactly. There are two ways to draw them, though. The atom-atom convention and the bond-target convention.
Okay, break that down.
Atom-atom means the arrow starts at an atom and points to another atom. Bond-target starts at a bond and points towards an atom or another bond.
Which one is better?
Bond-target is usually better. It more accurately shows where the electrons are actually going.
How so?
Well, electrons in pi bonds aren't really on a single atom. They're shared between atoms. So the arrow should start at the bond.
So basically, bond target shows the bond breaking and electrons moving to form a new bond.
Precisely. It makes the mechanism clearer, especially when forming new bonds.
Got it. So when you see a curved arrow, think of it as a pi bond morphing into something new.
Exactly. The arrow's tail is where the electrons are coming from, and the head is where they're going.
So what are the rules for drawing these resonance structures?
Okay. A big one is that only electrons move. Atoms don't. It's all about the electrons.
So the skeleton stays the same.
Exactly. Just rearrange the pi electrons and lone pairs. Also, you can't break a single bond. That would change the connectivity and we would have a totally different structure.
Okay, makes sense.
Formal charges must be correct too. The overall charge of the molecule must remain the same in all resonance structures.
Got it. So how do we know which resonance structure is the best or most important?
That's where evaluation comes in. The one with the most filled octets is usually the most important.
Filled octets are key.
Yep. Also, the structure with fewer formal charges. Separating charges requires energy, and a molecule will be more stable if it doesn't have that separation.
So the most stable resonance structure minimizes charge separation.
Right. And if you have to have charge separation, put negative charges on more electronegative atoms like oxygen or nitrogen.
Okay, electronegativity wins.
Always. Now, here's the cool part. Certain structural features are practically begging for resonance.
Oh, like what?
Carbonyls, for example. Like in ketones, esters, amides, the carbon-oxygen double bond is a prime spot for resonance.
How so?
You can draw a resonance structure where the pi electrons move onto the oxygen. Now it becomes O- and the carbon is plus.
Ah, shifting the double bond onto the oxygen. That's pretty common.
Super common. Amides are another great example. The nitrogen lone pair can be delocalized into the carbonyl.
So basically, if I see a carbonyl next to a lone pair, I should immediately think resonance.
Absolutely. It's like a neon sign saying, draw resonance structures here.
Okay, so what are some common mistakes people make when drawing these resonance structures?
Oh, there are tons. One big one is breaking the octet rule.
The octet rule?
Yeah, elements like carbon really want, 8 electrons around them. People sometimes draw structures where carbon has 10.
Oops.
Exactly. Another mistake is messing up formal charges.
Formal charges, right. Those can get confusing.
They do. You have to make sure the sum of the formal charges equals the overall charge of the molecule. And watch out for putting too much charge on one atom.
Too much charge?
Yeah, like don't put a +2 charge on a carbon atom unless you absolutely have to. Nature usually avoids that.
Gotcha. So keep charges minimal.
Minimize charges, obey the octet rule, and make sure your formal charges add up. Oh, and only move electrons, not atoms.
Only move electrons. That makes sense. Any other big gotchas?
Make sure the resonance structures are actually valid Lewis structures in the first place. People sometimes try to create resonance structures from something that isn't even a real molecule.
So start with something legit.
Yes. If you avoid those common pitfalls, your resonance drawings will be much more accurate.
Okay, that's super helpful. Avoiding those errors seems key to actually understanding what's going on with electron delocalization.
Absolutely. It all comes down to practice and careful attention to detail.
Okay, so we've talked a lot about structure. But how do we predict what happens next? Like, where do reactions even start?
Great question. It all boils down to electron flow. Reactions happen because electrons are moving from areas of high electron density to areas of low electron density.
High to low. Got it. Like water flowing downhill?
Exactly, and we use arrows to show that movement. There are 3 mean types, but the most important is the curved arrow.
Curved arrows. I've seen those.
They show where electrons are originating from and where they are going. The tail starts at the electron source. The head points to where they're going.
Okay, so how do I figure out where the electrons want to go?
That's the fun part. Look for electron-rich areas, lone pairs, pi bonds, places with a lot of negative charge. Those are your nucleophiles.
Nucleophiles. Got it. And the other side?
Electrophiles. Look for electron-deficient areas, partial positive charges, atoms that can accept more electrons.
So negative goes to positive, basically.
Yes, but it's not always that obvious. Sometimes you need to look at resonance structures.
Resonance. Uh-oh.
Relax. Resonance structures show how electrons are delocalized, and they can reveal electron-deficient centers that aren't obvious at first glance.
So they show where the positive charge is most concentrated.
Precisely. If you draw all the resonance forms, you can see where the electron density is lowest. That's your attack site.
Okay, so basically what you're saying is draw all the structures, see where the electrons aren't, and that's where the reaction happens.
Exactly. It's like finding the weak spot.
So how does this electron spreading actually affect things?
It massively stabilizes molecules.
How so?
Think of it like spreading out stress.
Delocalized electrons lower the overall energy.
So more stable, less reactive?
Generally, yes. But there's a cool trick.
Oh, tell me.
Even less stable resonance structures can be useful. The second best ones.
Wait, how?
They can highlight where a molecule is most likely to react.
So they're predictive?
Exactly. If a structure shows a positive charge on a carbon, that's a likely spot for a nucleophile to attack.
Okay, I see the connection.
And these patterns repeat. There are common motifs in organic chemistry.
Like what?
Like carbonyl groups or aromatic rings with electron withdrawing groups, recognizable patterns.
So it is like pattern recognition.
Absolutely. Once you spot those, you can predict reactivity more easily.
That's awesome. So is it like a visual shortcut?
Precisely. It makes complex reactions less intimidating.
Well, that's a lot to think about.
Yeah, for sure.
Welcome.
Thanks,
Ben, how are you doing today?
I'm doing fantastic, Rachel. So glad to be here.
Okay, so we're talking about acids and bases, but specifically Bronsted acids and bases. What makes them special?
It's all about protons. Bronsted acids are proton donors, and Bronsted bases are proton acceptors.
Proton donors and acceptors. Got it. So it's the exchange of a proton that defines the reaction?
Exactly. The key is this proton transfer. Think of it as a molecular handoff.
Like a tiny charged baton? So how do we actually show this happening in a reaction?
That's where reaction mechanisms come in, specifically the curved arrows.
Curved arrows? I remember those from chemistry class. What do they show?
Electron movement. They show how electrons rearrange during the proton transfer.
Okay, so the arrow starts where the electrons are and goes to where they're going?
Precisely. And a huge thing is to never show a naked proton. It's always attached to a molecule.
Naked proton? That sounds dangerous. So you always need a carrier molecule.
Always show the proton is transferred from one molecule to another, never floating free.
So basically, Bronsted acids and bases are defined by their ability to donate or accept protons, and we use curved arrows to show the electron movement in the proton transfer, making sure that the proton is always being carried by a molecule.
You nailed it. That's the essence of Bronsted acid-base reactions.
So how does an acid strength relate to where equilibrium lies in a reaction?
Stronger acids want to dissociate. They really favor forming products.
So if an acid dissociates more, the reaction is pushed toward the products.
Exactly. We can use reaction coordinate diagrams to visualize this.
Reaction coordinate diagrams sounds complicated.
Not really. It's just an energy profile. Strong acids have lower energy barriers to product formation.
Okay, so lower barrier means faster reaction and more products.
Precisely, and it's important to consider conjugate acids and bases.
Conjugate acids and bases. How do they fit in?
They're inversely related in strength. Stronger acids form weaker conjugate bases, and vice versa.
Wait, so a strong acids partner is a weak base?
Yes, that's right. It's all about stability after the proton is donated.
So basically, a strong acid easily gives away its proton, resulting in a stable, weak conjugate base.
Exactly. And that equilibrium will heavily favor the side with the weaker acid and base.
Okay, that makes sense. Strength dictates equilibrium position, favoring weaker conjugates. Okay, so how do we actually figure out which acid is stronger without just memorizing a list?
That's where conjugate base stability comes in. The more stable the conjugate base, the stronger the acid.
Explain that like I'm 5.
Think of it this way. An acid wants to get rid of a proton. If the resulting negative charge on the conjugate base is happy and stable, the acid is more likely to donate that proton.
So it's all about how well the conjugate base can handle being negative?
Exactly. There are 5 key factors that stabilize negative charge. We call them the Fantastic Five.
Oh, dramatic. Okay, what are they?
electronegativity, atom size, inductive effects, hybridization, and resonance.
Okay, that's a lot. Let's start with electronegativity. How does that affect stability?
The more electronegative the atom bearing the negative charge, the more stable it is. Electronegativity is how much an atom wants electrons. Oxygen is more electronegative than carbon. So if you're comparing two molecules with a negative charge, the one on oxygen will be more stable.
Got it. So oxygen handles the negative charge better than carbon. What's next?
Atom size. So atom size show larger atoms can spread the negative charge over a greater volume, which stabilizes it.
Size matters, huh?
Absolutely. Especially as you go down the periodic table.
Okay, so let's actually use these rules. Give me some examples.
All right, first, compare a thiol and an alcohol. Which is more acidic?
So, induction effects, how do those play into acidity?
Okay, think of it like this. Electron withdrawing groups pull electron density through sigma bonds.
So they're like, give me your electrons.
Exactly! Stabilizing the negative charge on the conjugate base.
And that makes it a stronger acid, right?
Yep. The more stable the conjugate base, the stronger the acid. There are three key factors.
Okay, lammo me.
Electronegativity, number of electron withdrawing groups, and distance.
Electronegativity makes sense. The more electronegative, the stronger the pull.
Precisely. Fluorine is a classic example. It really sucks those electrons towards itself. The more fluorine atoms, the stronger the effect.
Okay, so more fluorines equal stronger acid.
Bingo! But distance matters too. The closer the electron withdrawing group is to the charge, the bigger the effect.
Like the signal degrades over distance.
Yes, the inductive effect weakens rapidly with distance. It's all about stabilizing that negative charge.
So basically, you want lots of highly electronegative atoms super close to the action.
You nailed it. That's induction in a nutshell.
Okay, so let's dive into how the type of orbital affects acidity. I'm thinking specifically about hybridization.
Ah, yes, hybridization. The S character is key. More S character means the electrons are held closer to the nucleus.
Closer to the nucleus, why does that matter?
Think about stability. A carbanion, which is a carbon with a negative charge, becomes more stable if that negative charge is closer to the positive nucleus.
So more S character, more stable carbon anion, more acidic.
Exactly.
Got it.
Let's compare a terminal alkyne to an alkane.
What's a terminal alkyne again?
It's a carbon-carbon triple bond at the end of a chain. That carbon uses an sp hybrid orbital.
Okay, sp hybrid versus an alkane, which is sp3, right?
Precisely. sp has 50% S character. sp3 only has 25%. So the alkyne's hydrogen is way more acidic.
Huge difference. It all boils down to how tightly those electrons are held.
Absolutely. The more S character, the more tightly they are held, the more stable the resulting anion.
Making it easier to lose that proton in the first place. Wild.
So what other tricks stabilize negative charges?
Resonance.
Oh.
It's all about spreading the charge out.
Like when you have pi systems?
Exactly. Imagine a carboxylate ion. It's way more stable than, say, an alkoxide.
Why is that?
Because the negative charge on the carboxylate can bounce back and forth between the two oxygen atoms. Delocalization for the win.
So the more places it can hang out, the happier it is?
Precisely. That's why carboxylic acids are way more acidic than alcohols. Think about the conjugate base that forms.
Okay, so resonance spreads out electron density,
making the conjugate base far more stable, which means the original acid is more willing to give up that proton. Makes sense, right?
Totally. Does this come up in other places?
Definitely, like when you're pulling a proton off of a ketone. The resulting enolate is resonance stabilized.
So basically, what you're saying is resonance equals stability, which equals increased acidity.
You got it. The more you can delocalize that negative charge, the stronger the acid.
Okay, so if you had to boil it all down, what are the absolute must-remember things about acids and bases?
First, draw your mechanisms correctly. Seriously.
You mentioned that. Why is it so important?
Because the arrow pushing shows electron flow, and that highlights where the charges are. Mess that up and you're lost.
Got it. What else?
Acid strength is directly linked to conjugate base stability. If the conjugate base is stable, that acid is going to be strong.
Makes sense. So stabilize that base.
Exactly. And to figure out the base stability, use those 5 factors.
Okay, size, electronegativity, resonance,
Induction and hybridization. And the order matters.
right, size first, then electronegativity.
Then resonance, then induction, then hybridization. That order will save you.
So basically, nail the mechanism, understand the conjugate base connection, and follow that stability factor order.
That's it. Master those and acid-base chemistry becomes way easier.
All right, that about
welcome
wraps
to the
it up.
show.
Yeah.
Ben, how are you doing today?
I'm doing great, Rachel. So happy to be here.
Okay, so let's move on to something maybe a bit more familiar. Acids and bases. What exactly are they?
Well, at a basic level, acids donate protons and bases accept them. It's all about proton transfer.
Protons. As in, like, hydrogen ions?
Exactly. A hydrogen atom without its electron.
Got it. But I always think of acids as being charged, like hydrochloric acid. Are they all charged?
That's a common misconception. Some acids are neutral, like acetic acid, which is in vinegar.
Wait, really? Vinegar is an acid?
Yep, it's a weak acid. The key is that it can still donate a proton even though it's neutral overall.
Okay, so it's not about the overall charge, but about the ability to donate that proton. Makes sense. What makes some acids stronger than others?
That's all about their structure. The more stable the acid is after it loses a proton, the stronger it is.
Stable how? Like less reactive?
Exactly. Think about it like this. If the resulting structure can handle that negative charge well, it's going to be a happy, stable structure.
So stronger acids want to donate their protons more readily. Is that right?
Precisely. And that tendency is directly related to that stability.
Okay, this connects back to electronegativity, right? Because if an atom is more electronegative,
It can better handle that negative charge, stabilizing the acid after deprotonation. You got it.
So, how do we actually judge how acidic something is? Like, what are the key things to look for?
There are 4 main factors. First, electronegativity.
Electronegativity? Remind me what that is.
It's how strongly an atom attracts electrons to itself in a bond. More electronegative, more acidic.
Got it. What's next?
Atomic size. Bigger atoms handle negative charge better.
Because the charge is spread out?
Exactly. Think iodine versus fluorine. Iodine's way more acidic.
Okay, size matters. What else?
Inductive effects. This is where nearby electronegative atoms pull electron density away, stabilizing the conjugate base.
So, like, if you have a bunch of chlorines.
Right next to the acidic proton, they'll pull electron density and make it more acidic.
Okay, that makes sense. What's the 4th thing?
Charge delocalization, also known as resonance. If the negative charge can be spread out over multiple atoms, it's more stable and therefore more acidic.
Like in a carboxylic iron?
Precisely. The negative charge is shared between the 2 oxygen atoms, making carboxylic acids more acidic than alcohols.
So basically, electronegativity, size, inductive effects, and resonance, all about stabilizing that negative charge.
That's the key. Anything that stabilizes the conjugate base increases acidity.
This is like a cheat sheet for acid strength.
Essentially, yeah.
Okay, so we've talked about identifying acids and bases, but how do we measure their strength?
That's where the pKa value comes in.
pKa? What is that?
It's a number that tells you how acidic a compound is. The lower the pKa, the stronger the acid.
So, like, battery acid would have a super low pKa?
Exactly, and something like baking soda would have a much higher pKa.
Okay, that makes sense. But how do you actually find the pKa of a molecule?
Experimentally is best, but you can estimate by comparing it to known functional groups. Like if you have an alcohol, its pKa will be around 16 to 18.
So I can just look up the pKa of similar compounds and get a ballpark figure?
Precisely. And there are tables of pKa values for common functional groups.
That's super useful. Can you use pKa values to predict base strength too?
You absolutely can. A strong acid has a weak conjugate base and vice versa. So the higher the pKa of the acid, the weaker it is, which means its conjugate base is stronger.
Wait, so high acid pKa means strong base? That's kind of backwards.
I know, it's a bit confusing at first. Just remember that pKa is all about acid strength. The conjugate base strength is just the inverse relationship.
Okay, so basically what you're saying is learn your pKa tables.
Yes, knowing those trends will make your life so much easier when predicting acidity and basicity.
So now we get to predict whether these reactions will actually happen, right?
Exactly. That's where things get really useful. We can use pKa values for quantitative predictions.
Okay, so pKa, remind me.
It's essentially a measure of acid strength. Lower pKa means a stronger acid. We use it to predict equilibrium.
How so?
Acid-base reactions favor forming the weaker acid and base. So if you compare the pKa's of the acid and conjugate acid, you can tell which way the reaction will go.
Gotcha. So lower pKa on the product side means the reaction is favored.
Precisely. But what if we don't have pKa values memorized?
I definitely don't.
Then we can make qualitative predictions. The same principle applies. Reactions still favor forming weaker acids and bases, even if we can't put a number on it.
So basically what you're saying is look at the relative stabilities.
Yes, stability is key. Think about what makes an acid weak: delocalized charge, inductive effects, resonance.
Right, those stabilizing factors. So if the products are more stable, the reaction moves forward.
Exactly. And also, a quick note, pKa is related to pH, but they aren't the same.
How are they related?
pH tells you the acidity of a solution. The pKa tells you about a specific molecule's tendency to donate protons. The Henderson-Hasselbalch equation directly links them.
Okay, good to know they're connected but different things. So acids and bases combining creates water. But is that the whole story?
Not even close. There's a much broader view called Lewis acids and bases.
Lewis, as in like the dot diagram Lewis?
The very same. Gilbert Lewis said acids are electron pair acceptors and bases are electron pair donors.
Okay, so it's about electrons, not just protons.
Exactly. Bronsted-Lowry is all about proton transfer, but Lewis acids and bases can react without transferring any protons.
Wait, how does that work?
Think of ammonia, NH3, reacting with boron trifluoride, BF3.
Okay, I remember those molecules.
Ammonia has a lone pair of electrons. It donates them to the boron, which is electron deficient.
So the ammonia is the Lewis base?
Yep, and the boron trifluoride is the Lewis acid, accepting those electrons. No protons involved.
That's wild. So what are some other common Lewis acids?
Metal ions are big ones, like iron 3+ or aluminum 3+. They're always looking for electrons to bond with.
Because they're positively charged.
Exactly. And molecules with incomplete octets, like boron trifluoride or aluminum chloride, AlCl3.
So basically, anything that wants electrons can be a Lewis acid?
Pretty much. It opens up a whole new world of acid-base chemistry beyond just H+ and OH-.
Okay, I'm starting to see how this is much bigger than just H+ and OH-.
Okay, so you've walked us through the definitions. Now, how do we actually do acid-base analysis?
It's a strategic approach. First, draw a balanced reaction.
Like, actually draw it out every time?
Yes. See the electron movement. Then identify any charged components. That's key.
Why is that so important?
Charges dictate behavior. Next, think about periodic trends, electronegativity, atomic size.
Old faithful periodic table.
Exactly. And that leads to understanding stability of the conjugate base.
Conjugate base stability. Got it. So it's all connected.
Completely. Now we prioritize effects. Resonance is usually first.
Resonance trumps all?
Almost always. Then comes electronegativity. How much does that atom want electrons?
Okay.
Makes sense. Then what?
Atomic size. Bigger atoms handle negative charge better. Think about it.
Wait, why does bigger mean more stable with the negative charge?
The charge is more spread out, less concentrated, more stable.
Ah, like spreading peanut butter thinly.
Precisely. Next is inductive effects.
Inductive? What's that?
Electron withdrawing through sigma bonds. Think fluorine pulling electron density.
Fluorine. Always greedy. And last?
Hybridization. More S character means more stable with negative charge.
So basically, resonance, electronegativity, size, induction, hybridization. Got it.
Yes, remember RESIH. Makes it easier to remember.
That's a good mnemonic device. I'll have to remember that.
Well, that's quite a bit to digest.
Yeah,
podcast
for sure.
Listeners,
Thanks,
and welcome.
Thanks for having
Ben, how are you doing today?
I'm fantastic, Rachel. Ready to go.
So, pi bonds as electrophiles. Where do we even start with that?
Think about carbonyl groups. C double bond O. That carbon is ripe for nucleophilic attack.
Like a magnet for electrons?
Exactly. Carbonyl carbons are electrophilic because of resonance.
Resonance? Explain that.
You can draw a resonance structure where the double bond breaks and the oxygen gets the electrons. That makes the carbon partially positive.
Ah, so it's like a sneaky positive charge.
Totally. And that's why nucleophiles add to it. It's a two-step dance.
2 steps?
First, the nucleophile attacks the carbonyl carbon. Then a proton is added to the oxygen.
Simple enough. Any examples of this in action?
Hydride reductions, like using sodium borohydride to reduce a ketone to an alcohol.
So the hydride is the nucleophile in that case.
Bingo. Attacks the carbonyl carbon, and solvent matters a ton here.
Solvent?
So, protic solvents can protonate your nucleophile, which is bad. You want aprotic.
Got it. Keep the nucleophile nice and reactive.
Precisely. So key takeaways, carbonyls are electrophilic, resonance makes them so, and solvent choice is crucial.
Okay, so basically what you're saying is carbonyls are electron deficient because of oxygen hogging all the electrons. So nucleophiles are attracted, and the solvent has to be right.
You nailed it. That's nucleophilic addition in a nutshell.
Okay, so what makes this carbonyl group so reactive?
It's all about that carbon-oxygen double bond, making it a perfect electrophilic center.
Electrophilic? What does that even mean?
Think of it as electron-loving. Electrophiles are species that are attracted to electrons.
Like a moth to a flame?
Exactly. Chemically speaking, they're Lewis acids.
Lewis acids. Right. So where do the electrons come in?
That carbonyl group has 2 resonance forms. Think of it like 2 different ways to draw the same structure.
Okay. I'm picturing it. And?
One form is more stable, but the less stable one is key. It shows the carbon atom with a partial positive charge.
Ah, so it's electron deficient.
Bingo! That carbon is begging for electrons, making it the perfect target for nucleophiles.
So basically, what you're saying is that less stable form is basically showing us where the reaction is going to happen.
Precisely. It's like a roadmap for chemical reactions. This is my favorite part.
Wait, so knowing this, we can predict the reaction?
Absolutely. We know the nucleophile will attack right there at the carbon.
That's wild. So it's like the carbonyl group is waving a flag saying, react here.
You got it. And that's why it's so fundamental in organic chemistry.
Okay, so you mentioned nucleophilic addition. What exactly happens there?
It's a 2-step process. First, the nucleophile attacks
Attacks what exactly?
the electrophilic carbon. Think of it like a tiny negatively charged particle hitting a positively charged target.
And then?
Then, protonation. A proton attaches to the oxygen.
Protonation. Got it. So what are the arrow pushing rules you mentioned?
They're crucial. Arrows show electron movement, always from electron rich to electron poor, never the other way around.
Okay, so it's all about tracking electrons.
Exactly, and the geometry changes too. It shifts from trigonal planar to tetrahedral.
Trigonal planar to tetrahedral.
Explain that.
The carbon starts flat with 3 groups around it. After the nucleophile adds, it becomes 3-dimensional, like a pyramid.
So basically, electrons rearrange and the molecule changes shape.
Precisely. It's a dance of electrons and atoms seeking stability.
So it goes from flat to sort of a pyramid shape by adding to it. Got it.
And that shape change is key to understanding its properties.
Because the shape determines how it interacts with other molecules.
Absolutely. Shape dictates function in chemistry.
So we've been talking a lot about carbonyls. What about other molecules?
Great question. The reactivity we've discussed isn't unique to carbonyls.
Oh, really?
Absolutely. It extends to any molecule with a polar pi bond.
Like what?
Imines, nitriles, thiocarbonyls, they all share similar reactivity patterns.
So it's the polar pi bond that matters?
Exactly. Think of the resonance structures we talked about earlier.
Yeah, that makes sense.
The same principles apply. The more electronegative atom hogs electron density.
Creating partial charges.
Precisely. That charge distribution dictates where a nucleophile will attack.
So the slightly positive carbon is still the target?
In most cases, yes. But it depends on the specific molecule and conditions.
Okay. So what changes with, say, an imine versus a carbonyl?
The nitrogen in an imine is less electronegative than the oxygen in a carbonyl.
Got it. What does that mean?
The carbon in the imine is slightly less positive. It changes the reactivity a bit.
Less attractive to nucleophiles?
Potentially. It can also affect the stability of the intermediate.
So it's all interconnected.
Totally. Understanding these fundamental principles lets you predict reactivity.
That's so useful. What about nitriles?
Nitriles have a carbon triple bonded to a nitrogen.
Triple bond?
Yeah, 1 sigma and 2 pi bonds. Still polarized, still reactive.
Okay, I'm starting to see the pattern.
Exactly. Polar pi bonds are a recurring theme in organic chemistry.
This is way simpler than I thought it was.
I know, right? It all comes down to charge distribution.
Okay, so we're dealing with hydrides now, right? But hydrides can act as nucleophiles?
Exactly. A hydride is basically a proton with 2 electrons, giving it a negative charge.
So it's not just a proton.
Oh, definitely not. Protons are positively charged and hydrides are negatively charged, opposite reactivities.
Okay, that makes sense. So where do these hydrides come from?
We typically use compounds like sodium borohydride, that's NaBH4, or lithium aluminum hydride, LiAlH4. Those are common sources.
Those sound intense.
Lithium aluminum hydride definitely is. It's a really strong reducing agent. Sodium borohydride is a bit milder, more selective.
Okay, so when a hydride attacks, what happens next?
The hydride delivers its 2 electrons to, say, a carbonyl carbon, and then you need a proton source to neutralize the charge on the oxygen.
Like an acid workup?
Precisely. Often the solvent itself, like water or alcohol, can provide that proton. It's a crucial step to get to the final alcohol product.
So hydride attacks, oxygen gets a negative charge, solvent donates a proton. Got it.
Exactly. And the choice of hydride reagent affects what functional groups you can reduce. That's the key takeaway.
So basically what you're saying is hydrides can be nucleophiles, but you have to be careful which one you choose.
Precisely. It depends on the reaction.
So how do solvents play into all of this?
Solvents are critical. You need to pick one that won't react with your hydride. It's all about compatibility.
Makes sense. So, like, water would be a bad choice, right?
Absolutely. Hydrides react violently with protic solvents like water or alcohols. Think explosion.
Yikes. Okay, noted. So what are good options then?
Ethers are commonly used, like diethyl ether or tetrahydrofuran, which is THF. But even then...
There's a catch?
Always. Lithium aluminum hydride, or LAH, forms complexes with ether solvents. It's a Lewis acid-base interaction.
Wait, walk me through that. Lewis acid-base?
The aluminum in LAH is electron deficient. The ether oxygen has lone pairs. They coordinate.
So it's like they're holding hands.
Exactly. This affects the hydride's reactivity. It can make it more selective, for example.
Okay, solvent matters. Got it. What about how reactions are written out? I always see those weird arrows.
Oh, reaction notation. Organic chemists love their shortcuts. Things written over the arrow, those are reagents and conditions.
So like LAH and ether would go over the arrow?
Precisely. And sometimes you'll see multiple steps written sequentially.
Like a recipe.
Exactly. You might see step 1, add reagent A. Step 2, add reagent B. It's a concise way to show a multi-step synthesis.
That makes way more sense now.
Well, that's a lot to think about.
Yeah, for sure.
Welcome
Thanks,
to the
Ben.
show.
Thanks for
Rachel, how are you doing today?
I'm doing awesome. So excited to be here.
So what exactly are redox reactions in the organic chemistry world?
That's a great question. Redox, or reduction-oxidation reactions, are basically reactions where electrons are transferred between molecules.
Okay, electron transfer, but how does that differ from, say, regular chemistry?
Well, in general chemistry, we focus on oxidation states, like if an atom gains or loses electrons directly. In organic chemistry, it's a bit more nuanced.
Nuanced how?
We look at the gain or loss of oxygen and hydrogen atoms. If a molecule gains oxygen or loses hydrogen, it's considered oxidized.
And the opposite?
Exactly. If it loses oxygen or gains hydrogen, it's reduced.
So it's less about tracking electrons directly and more about the change in oxygen and hydrogen content.
Precisely. Think of it as a convenient shortcut for organic chemists.
That makes it so much easier. Okay, so now that we know what it is, what are some common examples?
Oh, there are tons. Combustion, metabolism in our bodies, even bleaching your hair.
Wait, really? Bleaching your hair is redox?
Totally. The bleaching agent oxidizes the melanin in your hair, breaking it down.
Okay, so we've got a handle on oxidation numbers, but how does that apply to like actual organic molecules?
Great question. There's this concept called the oxidation state hierarchy.
Ooh, sounds fancy.
It's just a way to organize organic compounds by their oxidation level. Think of it like a ladder. At the bottom, you have alkanes.
Like methane, ethane.
Exactly. All those CH bonds are very reduced. As you go up the ladder, each step is essentially an oxidation.
Okay, so what's the next rung?
Alcohols. You're adding an oxygen, right? Replacing a CH bond with a COH.
Makes sense. Then what?
Aldehydes. Replacing another CH bond on that carbon with a C double bond O.
And that's even more oxidized.
Yep, and at the very top, you've got carboxylic acids. That carbon has 2 bonds to oxygen.
So alkane to alcohol is oxidation, alcohol to aldehyde is oxidation, aldehyde to carboxylic acid also oxidation?
Exactly. You're increasing the oxidation state of that carbon atom each time.
Okay, I think I'm getting it. So reduction would be the opposite.
Precisely. Carboxylic acid to aldehyde is reduction, and so on.
Okay, so let's shift gears and talk about Grignard reagents. What exactly makes them so special in organic chemistry?
They're basically carbon nucleophiles, really reactive ones. You mate them by reacting an organic halide, like a bromide or chloride, with magnesium metal.
Magnesium just inserts itself in there?
Exactly. It wedges itself between the carbon and the halogen to create a carbon-magnesium bond.
And that makes the carbon nucleophilic?
Yes. The carbon bonded to the magnesium has a partial negative charge. It acts like a carbanion, super eager to attack electron-poor atoms.
Wait, why is everything always done in anhydrous ether?
Water is the enemy. Grignards react violently with water. Even trace amounts can destroy your reagent.
No way.
Absolutely. Think of it as a controlled explosion. So anhydrous conditions are critical to keep the Grignard around long enough to actually use it.
So basically water makes the Grignard reagent useless.
Correct. Because the Grignard abstracts a proton from water, turning it into an alkane and messing up your whole reaction.
Okay, so Grignard reagents are super reactive, right?
Extremely. That carbon-magnesium bond, very polar.
Polar how?
Carbon gets a big negative charge, makes it a strong base.
Like steal a proton strong?
Oh, yeah. Any hint of water, alcohols, Grignard will grab that proton first.
So you have to keep everything bone dry.
Absolutely. Or you just end up with a useless hydrocarbon.
Got it. But when it works, it attacks carbonyls, right?
That's where the magic happens. The Grignard carbon attacks the carbonyl carbon.
Nucleophilic attack?
Exactly. Breaks the pi bond.
Then what?
You get this tetrahedral intermediate with a negative oxygen, protonated with dilute acid.
And boom, alcohol?
Yep, a new carbon-carbon bond and an alcohol. Super useful reaction.
So, organolithium reagents, how do they stock up against Grignards?
They're like Grignards, but on steroids. Way more reactive.
Oh, really? How so?
It's all about electronegativity. Lithium is way more electropositive than magnesium.
So what does that mean, practically?
The carbon-lithium bond is much more polar, creating a carbanion that's super reactive.
Got it. So, what are they used for that Grignards can't do?
Tons of carbon-carbon bond formations. They're awesome for adding carbons onto molecules.
Carbon-carbon bonds, that's like building the backbone of a molecule, right?
Exactly. They're fantastic for constructing complex organic structures.
So basically, organolithiums are the go-to when you need some serious carbon-carbon bond forming power.
Precisely. They open up a whole world of synthetic possibilities.
That's wild. All right, so now we know organolithiums are the heavy hitters for carbon-carbon bonds.
Okay, so walk me through the universal mechanism. What's the big idea?
It's all about adding organometallics to polar pi bonds. Think carbon and oxygen double bonds.
Like in ketones and aldehydes?
Exactly. First, you have nucleophilic attack.
Meaning what?
The carbon in your organometallic, which has a partial negative charge, attacks the partially positive carbon in the carbonyl.
Okay, then what happens?
The pi bond electrons shift to the oxygen, making it negatively charged. Think of it like a domino effect.
Got it. So attack, shift, then what?
Protonation. You add acid, the negatively charged oxygen grabs a proton and becomes an alcohol.
And that's it? That's the whole mechanism?
Yeah. It's universal because it works for hydrides, Grignards, or organolithiums, anything that can act as a carbon nucleophile.
So basically what you're saying is it's the same 3 steps, no matter what the organometallic is.
Precisely. Attack, shift, protonate.
Okay, so now we know about electrophiles. What about nucleophiles?
Time for acetylides. They're carbon nucleophiles, which are derived from terminal alkynes.
Terminal alkynes? What makes them special?
The hydrogen on the end is slightly acidic, not like a strong acid, but enough that we can pull it off with a strong base.
And then what?
You get an acetylide anion. That carbon now has a negative charge, making it a great nucleophile.
So it attacks positive things?
Exactly. They love to attack carbonyls, like aldehydes and ketones.
Okay, how does that work?
The acetylide carbon attacks the partially positive carbonyl carbon. The pi bond electrons from the carbonyl then move on to the oxygen, giving it a negative charge.
Then what happens to that negative oxygen?
It gets protonated, usually in a separate step with dilute acid. That gives you an alcohol.
So basically we're adding an alkyne to a carbonyl to make an alcohol.
You got it. And that new carbon-carbon bond is super useful for building more complex molecules.
Okay, so back to organic chem then. What's a pattern that makes everything easier?
It's the universal mechanism for carbon nucleophiles attacking polar pi bonds. Super common.
Okay, break that down.
Think Grignard reagents, organolithiums, acetylides. They all do the same thing.
Wait, really? I always thought they were totally different.
Nope. Carbon with a negative charge attacks a positive part of a pi bond. Always.
So basically, if I see that pattern, I know what's going to happen.
Exactly. Focus on the mechanism, not memorizing individual reactions. You will save so much time.
That's actually really helpful. So it's like find the slightly positive bit.
Yeah, the electrophilic carbon and the carbon nucleophile attacks. Boom, bond formed.
Okay, that makes way more sense than just trying to memorize a million reactions.
Memorization is the enemy. Understanding is your friend.
So, what's the slightly positive bit usually?
Carbonyls are classic, C double bond O. The carbon's always partially positive.
Okay, so to wrap things up, what are the main takeaways here?
It's all about understanding that universal mechanism. These carbon nucleophiles all convert carbonyls to alcohols. That's the big picture.
So basically, what you're saying is focus on the nucleophile?
Exactly. The nature of the nucleophiles is the key. Is it Grignard, organolithium, cyanide?
Not the mechanism itself?
Right. The mechanism is always the same. Nucleophilic attack, protonation, it's the carbon nucleophile that dictates the product.
That makes it so much easier to understand.
I hope so, because organic chemistry doesn't have to be scary. It can be fascinating.
Totally agree. Any final thoughts for students tackling these reactions?
Practice, practice, practice. Draw the mechanisms yourself, and don't be afraid to ask for help.
Great advice. Thanks so much for breaking this down for us.
My pleasure. It was fun.
Well, that about wraps it up.
Yeah.
Hey, everybody. Welcome to the show.
Thanks, Rachel.
Rachel, how are you doing today?
I'm doing fantastic. So happy to be here.
Okay, so we've talked about resonance. Now let's get into pi bonds acting as electrophiles. What's that all about?
Think of pi bonds, especially in carbonyls, as electron poor. They're looking for electrons.
So like magnets, but for electrons?
Exactly. That's why they're electrophiles, electron-loving. Nucleophiles, like cyanide, can attack them.
Cyanide? As in the poison?
Yep. But in a controlled setting, of course. It's a great nucleophile. It adds to the carbonyl carbon.
Okay, so the cyanide attacks. What happens next?
Well, sometimes a leaving group gets kicked out.
Leaving group. Like what?
Something stable that can take electrons, like a halogen or even water.
Gotcha. So attack, then leaving group leaves?
Sometimes. Other times you need acid-base catalysis to help things along.
Acid-base catalysis. How does that work here?
Acids can protonate the carbonyl, making it an even better electrophile. Bases can deprotonate the nucleophile, making it a stronger attacker.
So basically, they're like chemical hype men?
Precisely. They speed up the reaction, and it often goes back to orbital interactions.
Back to the orbitals. Okay, I think I'm starting to get it. Pi bonds can be electron hungry, and things like cyanide can attack them, sometimes with a little help from acids or bases.
Okay, but what's actually happening at the orbital level when a nucleophile attacks a carbonyl?
It's all about the frontier molecular orbitals, specifically the HOMO and LUMO.
HOMO and LUMO?
Highest occupied molecular orbital and lowest unoccupied molecular orbital. The nucleophile's HOMO interacts with the carbonyl's LUMO.
So the nucleophile is donating electrons into the carbonyl's LUMO.
Exactly. The carbonyl's LUMO is centered on the carbon atom because of the electronegativity difference.
Oxygen hogs the electron density, making the carbon more positive and a better target.
Bingo. Plus, resonance plays a role.
Resonance? How so?
You can draw a resonance structure where the carbonyl has a positive charge on the carbon.
Okay, makes sense.
That stabilizes its developing charge as the nucleophile attacks, lowering the activation energy.
So it's a combination of electronegativity and resonance that directs the nucleophile to the carbon.
So
that's really cool.
Yes, it's a beautiful interplay of electronic effects. So what happens after the nucleophile attack?
So another cool reaction involves cyanide, right?
Exactly. Cyanide, or CN- acts as a nucleophile.
Wait, like in the movies?
Well, yes, it's highly toxic, but also a really useful reagent in organic chemistry.
Okay, useful how?
It attacks carbonyl carbons, like in aldehydes or ketones, to form cyanohydrins.
Cyanohydrins. Sounds intimidating.
It's just a molecule with both a cyano group and a hydroxyl group attached to the same carbon.
Okay, so how does this reaction actually work?
CN- attacks the partially positive carbonyl carbon. Then the oxygen gets protonated, usually by HCN, to give you the cyanohydrin.
Simple enough. Is there anything special about this reaction?
It's reversible, especially under basic conditions. The cyanide can actually be kicked off.
Wait, so you can undo it?
Yes, this reversibility is super useful for certain synthetic strategies.
Interesting. So it's not just about making cyanohydrins, but also potentially breaking them apart.
Absolutely. Think of it as a protecting group strategy in some cases.
Okay, so what exactly is a leaving group anyway?
It's an atom or a group of atoms that departs from a molecule with a pair of electrons.
So it just leaves?
Basically, yeah. And here's a key rule. Good leaving groups are weak bases.
Weak bases? Why is that?
Because weak bases are stable when they're on their own with that negative charge. They don't want to react further.
Ah, okay, they're happy being alone. Give me some examples.
Iodide, bromide, and chloride are classic examples. I-, Br-, and Cl-.
Got it. What makes them good?
Their conjugate acids are strong acids. That means they're very stable as anions. Think about Hi, HBr, HCl.
Right, strong acids easily donate their proton. What about something like water?
Water can be a leaving group too. When it leaves as H2O, it's neutral.
So basically, a good leaving group wants to leave and not come back.
Exactly. And the weaker the base, the better the leaving group. It all comes down to stability after departure.
That makes perfect sense. So we've talked acid catalysis. What about using a base?
Base catalysis is fascinating, especially with carbonyl additions. Think about hydration.
Hydration, like adding water?
Exactly. But instead of acid, we use hydroxide, OH- as our catalyst.
How does that even work?
OH- makes water a better nucleophile. It pulls off a proton and it makes it OH negative.
So it's more reactive?
Much more. It attacks a carbonyl carbon. Then the catalyst is regenerated.
Regenerated how?
Proton transfer. OH- deals a proton and goes away.
Makes sense. Does changing conditions affect this?
Absolutely. Changing the pH alters the effective nucleophile concentration.
Meaning what exactly?
More OH-, faster reaction, generally.
So more base, more boom?
Kind of. There are practical limits, but yeah, more base usually equals faster hydration.
Interesting. So basically, base catalysis uses OH- to make water a superpowered nucleophile for carbonyl additions.
Precisely. It changes the whole game.
Okay, so catalysts make the reaction go, but they aren't used up, right?
Exactly. Catalysts are conserved. Think of it like a reusable tool.
Got it. So acid versus base catalysis, what's the difference?
It's all about charge. Acid catalysis uses pronation. Base catalysis uses deprotonation.
So in acid, we add protons first?
Typically, yes. You protonate the electrophile, mix it more reactive.
Electrophile gets a positive charge boost?
Precisely. And in base catalysis,
you grab a proton from the nucleophile.
That's the idea. You deprotonate it to make it more nucleophilic, more reactive.
So positive charge versus negative charge as the starting point.
Bingo. The global charge pattern dictates the mechanistic first step.
Can you give a super simple example just to make it click?
Sure. Think of carbonyl chemistry. Acid protonate the carbonyl oxygen. Base deprotonate the attacking alcohol.
Okay, makes sense. Deprotonate to activate the nucleophile, protonate to activate the electrophile.
You nailed it. That's the core difference.
So, how does acid catalysis change things?
Great question. First, the carbonyl oxygen gets protonated.
Protonated, so it gains a hydrogen.
Exactly. This makes the carbonyl carbon even more electrophilic.
More reactive. Got it.
Then water attacks that carbon.
As a nucleophile, right?
Bingo. The oxygen on the water forms a bond.
And now it has 3 bonds, so it's positively charged.
Precisely. Another water molecule then removes a proton
to neutralize the charge.
Correct. And this gives us the same hydrate product.
Same product, different route. So in base catalysis, we removed a proton first.
And in acid catalysis, we add one first.
Essentially a swapped order. But it still gets us there.
Exactly. Both acid and base catalysis work.
Interesting. But which one is preferred?
It depends on the specific reaction conditions. Sometimes one is faster or more efficient.
Okay. So can we summarize the key differences in acid and base catalysis using a comparison?
Absolutely. In acid catalysis, protonation usually happens first.
Before the rate determining step.
Yes. While in base catalysis, deprotonation tends to come first.
Got it. So it's all about the order.
Exactly. And that order dictates the reaction pathway.
Okay, how can we recognize these mechanisms just by looking at them?
Look for hydronium, H3O+. That indicates acid catalysis. Hydroxide, HO-, indicates base catalysis.
Simple enough.
Right? The presence of those ions is a big clue.
So if I see H3O+ floating around, I'm probably dealing with an acidic mechanism where protonation happens early.
Precisely. And if you spot HO-, think base catalysis with initial deprotonation.
Perfect. So, any other key patterns to watch for?
Just remember, acid catalysis often involves electron-rich species getting protonated to become even more reactive.
And base catalysis?
It involves electron-poor species getting deprotonated and more reactive.
Okay, so acids activate electron-rich things, and bases active electron-poor things.
Yes, that's the gist of it.
Well, I think we've covered quite a bit.
Yeah, that was a good
Welcome to
overview.
the show.
Thanks,
Ben, how
Rachel.
you doing today?
I'm doing fantastic, Cam. Really glad to be here.
Okay, so now let's talk about pi bonds acting as electrophiles. What's the basic idea here?
Think of a pi bond as a target. It's electron-rich, making the carbon atom electron deficient and vulnerable to attack.
So nucleophiles are like drawn to it.
Exactly. They attack that partially positive carbon. We see it in hydrate equilibrium, for instance.
Hydrate equilibrium? What's that?
It's where a carbonyl reacts with water, forming a geminal diol. The oxygen from water attacks the carbonyl carbon.
Okay, and what about hemiacetyl formation?
Similar idea. An alcohol attacks the carbonyl, creating a hemiacetal. Again, the oxygen acts as the nucleophile.
So it's not just oxygen attacking, right?
Right. Nucleophiles can be diverse: nitrogen, sulfur, even carbon. It really opens up the possibilities for reactions.
And catalysis? How does that fit in?
Catalysts can enhance the electrophilicity of the pi bond. For example, acids can protonate a carbonyl, making it even more attractive to nucleophiles.
So basically, pi bonds act as electrophilic targets, inviting nucleophiles for reactions, and catalysts can help things along. That's wild. So these mechanisms you're talking about, are they all just different versions of the same basic steps?
Exactly. We can break them down into 4 core patterns. Think of them as the Lego bricks of organic chemistry: nucleophilic attack, leaving group loss, proton transfer, and rearrangement.
Okay, 4 patterns. What's the most important one?
Definitely nucleophilic attack. It's where a nucleophile, an electron-rich species, attacks an electron-poor center.
Electron-rich attacks electron-poor. Makes sense. Give me an example.
Think of hydroxide, OH-, attacking a carbonyl carbon in a ketone.
Hydroxide attacking a ketone. What happens next?
The hydroxide donates its electrons to form a new bond with the carbon, breaking the carbon-oxygen pi bond of the ketone.
So the electrons flow from the hydroxide to the carbonyl carbon.
Precisely. That's the essence of nucleophilic attack. Electron-rich attacking electron-poor, leading to bond formation.
Got it. So this is like the fundamental move of organic chemistry.
Absolutely. Mastering nucleophilic attack unlocks understanding a huge number of reactions. It really is at the heart of organic chemistry.
So what makes some carbonyls want to form hydrates more than others?
Great question. It's all about steric and electronic factors.
Steric? Like how bulky the groups are?
Exactly. Bulky groups around the carbonyl make it harder for water to attack. It's like trying to squeeze into a crowded room.
Makes sense.
And that's why aldehydes generally form hydrates more readily than ketones. Ketones have two bulky groups.
Two crowds blocking the door.
Precisely. Now, electronic effects are about how electron withdrawing or electron donating groups affect the carbonyl.
So electron withdrawing groups pull electron density away.
Yes, and that makes the carbonyl carbon more electrophilic, more positive. Water attacks more easily.
So electron withdrawing groups favor hydrate formation.
Big time. They stabilize the hydrate, which has two electron withdrawing oxygen atoms attached.
Okay, so less steric hindrance and more electron withdrawing groups equals more hydrate.
Spot on. That's the key to understanding carbonyl hydrate equilibria.
So what's a hemiacetal anyway?
Think of it like a hydrate, but with an alcohol instead of water attacking the carbonyl.
Okay, so it's similar mechanism.
Exactly. The alcohol's oxygen attacks the carbonyl carbon.
Then you get a proton transfer, right?
You got it. Results in a carbon bonded to both an alcohol and an ether.
And that's a hemiacetal?
Yep. Now here's the cool part. You can get cyclic hemiacetals.
Cyclic? How?
If you have an alcohol group and a carbonyl in the same molecule.
Oh, they react with themselves.
Precisely. This is super important in sugar chemistry. Glucose, for example, exists mostly as a cyclic hemiacetal.
Wait, really? So like the ring form is a hemiacetal?
Yes, that carbon in the ring is bonded to both an alcohol and an ether oxygen.
No way. That's so cool. Okay, so we've talked about electrophiles. What are some different kinds of nucleophiles that are out there?
Oh, there's a ton. We've got hydrides, nitriles, acetylides.
So how can we strategically speed up these reactions?
Catalysis, specifically activating electrophiles or nucleophiles.
How does that work?
Acidic conditions enhance electrophiles by protonating them, making them more receptive to nucleophilic attack.
So it's like giving the electrophile a little boost.
Exactly. Basic conditions do the opposite. They activate nucleophiles, making them more aggressive towards electrophiles.
So it's like choosing the right tool for the job.
Precisely. But you have to be careful. You need to match the electrophile activation with nucleophiles that can withstand the conditions.
Makes sense. You can't use a delicate nucleophile in super acidic conditions.
Right. It would just get destroyed. You need to consider stability under those catalytic conditions.
Okay, so it's all about creating the optimal environment for the reaction to proceed quickly and efficiently.
You got it. Strategic activation through carefully chosen conditions.
Okay, so we've talked about carbonyls. What about imines? Are they similar?
Very similar. Imines also undergo nucleophilic attack.
But there's a catch, right?
Exactly. Imines are less reactive than carbonyls.
Why is that?
Nitrogen is less electronegative than oxygen, meaning the carbon isn't as positive.
So, less susceptible to attack?
Precisely. We need to use tricks.
Tricks? Like what?
Stronger nucleophiles, like Grignard reagents, or acid catalysis.
Acid catalysis? How does that help?
It protonates the nitrogen, makes the carbon even more positive.
So you're making it more attractive to nucleophiles.
Bingo. And the reaction becomes much faster.
So basically, it's like a carbonyl reaction, but needs a little extra oomph to get going.
You got it. It's all about making that carbon more electrophilic.
So when we add something to, say, a carbonyl, what happens with the stereochemistry?
It's cool. If the carbonyl carbon is attached to 3 different groups, the nucleophile can attack from the top or bottom face.
top or bottom, like a pancake.
Exactly. And if it's a trigonal planar carbon, then this creates a new chiral center.
And that means?
2 possible stereoisomers are formed, a pair of enantiomers.
Okay, easy enough. But what if there's already a chiral center nearby?
That's where it gets interesting. The top and bottom faces are no longer equivalent.
Why not?
The existing chiral center influences the approach of the nucleophile.
So it's like the chiral center is a bouncer at a club, favoring one side over the other.
Precisely. This leads to the formation of diastereomers instead of enantiomers.
Diastereomers. Got it. So different properties.
Exactly. Different physical properties and different biological activities sometimes. It's a big deal in drug design.
Okay, so we keep seeing these patterns over and over again. What's the core idea here?
It's nucleophilic attack on a polarized pi bond. Nu attacks an electrophilic atom.
Okay. Nu meaning?
Nucleophile. An electron-rich species, then electron flow goes to a heteroatom like oxygen or nitrogen.
And what's next?
Finally, there's an acid-base step to finish things off. It's a 3-part play.
Like a universal mechanism?
Exactly. And it shows up in acid-catalyzed and base-catalyzed flavors.
How does that change things?
Well, acid catalysis protonates first. Base catalysis deprotonates.
So different starting moves. What about drawing these mechanisms?
Curly arrows are key. They show electron movement. Start at the electron source and at the destination.
Always following the electrons.
Precisely. And remember formal charges. They're crucial. Keep track of them.
Got it. Anything else we should keep in mind?
Just practice. The more you draw these, the more natural it becomes.
Well, Ben, that about wraps things up.
Yeah, I think that's a good overview.
So, Cam, how are you doing today?
I'm doing great, Ben. So excited to be here.
Okay, so we know that atoms with lone pairs can be nucleophiles, but pi bonds can be too, right?
Exactly. Think about alkenes and alkynes. Those pi bonds are electron-rich.
So they're just looking to share those electrons with something that's electron-poor?
Bingo. They act as nucleophiles attacking electrophiles.
But I thought some pi bonds were electrophilic, like polarized ones.
Good catch. If you have a polar pi bond, say between carbon and oxygen, the carbon becomes electrophilic. The oxygen hugs the electrons.
Okay, so it depends on the specific molecule.
Totally. Now, when a pi bond acts as a nucleophile, we often see something called electrophilic addition.
Electrophilic addition, got it. What's added?
An electrophile, of course. It attacks the pi bond, forming a carbocation intermediate.
Carbocation. Aren't those unstable?
Super unstable. That's why it's just an intermediate. Then something else comes along and stabilizes it.
And what determines where the electrophile adds to the alkene?
That's where Markovnikov's rule comes in. The electrophile adds to the carbon that already has more hydrogens.
The rich get richer. Makes sense. So it's all about the most stable carbocation.
Exactly. And this preference for one product over another is called regioselectivity.
Regioselectivity. So pi bonds can be nucleophilic, they undergo electrophilic addition, and Markovnikov's rule tells us where things attach.
Cool.
Okay, so alkenes and alkynes, what makes them so different structurally?
It's all about the double and triple bonds, which changes their shape and electron behavior.
Shape how?
Well, alkenes have a double bond, right? That carbon is sp2 hybridized.
sp2, got it. And that means?
Trigonal planar geometry. Think flat, like a triangle around the carbon.
Okay, a flat triangle. And alkynes?
They have a triple bond. That carbon is sp hybridized.
Which makes it?
Linear, straight line. Big difference from the alkene.
Huge difference. So it's the number of bonds that dictates shape. Got it. What about these pi electrons you mentioned?
Those are key. Double and triple bonds have pi electrons above and below the sigma bond axis.
Above and below?
Exactly. Think of it like a cloud of electrons. Alkenes have one pi bond, one cloud. Alkynes, two pi bonds, two clouds.
So more electron density.
Way more. This affects how these molecules react. More electrons available to interact.
So basically, double and triple bonds change the shape and electron clouds, which then changes how they react with other molecules?
Spot on. And that reactivity is what makes them useful in organic chemistry.
Okay, so we know alkenes react, but how does it actually happen?
Electrophilic addition. It's a two-step ionic mechanism.
Ionic meaning?
Charges are involved. The double bond, that pi bond we talked about earlier, is electron-rich.
Okay, so it attracts electrophiles.
Exactly. The electrophile attacks, and that pi bond breaks.
Only the pi bond?
Just the pi bond. The carbon-carbon sigma bond stays intact.
Got it. So what happens next?
A carbocation intermediate forms.
A carbocation? What's that?
A carbon atom with a positive charge. It's super unstable.
Unstable how?
It wants to react immediately to become stable again. The carbocation gets attacked by a nucleophile in the second step.
And that gives us the final product.
Precisely. The electrophile and nucleophile have added across the double bond.
So pi bond breaks, carbocation forms, then boom, new bonds.
That's electrophilic addition in a nutshell.
Okay, so walk me through a real example. Like, what happens if we react HBr with an alkene?
Sure. Let's say we have propene. The first step is the alkene grabbing the hydrogen from HBr. This forms a carbocation.
And that's the slow step, right?
Exactly. The carbocation is unstable, so it takes energy to form. That's our rate-determining step. The slower of the two is the rate-determining step.
Okay, got it. So what happens after the carbocation forms?
That's when the bromide ion, the Br negative, swoops in and attacks the carbocation. They're oppositely charged. That's super fast.
So the carbocation gets neutralized and we end up with our final product?
Yep. In this case, 2-bromopropane. The bromine ends up on the middle carbon because that's where the more stable carbocation formed.
Wait, so why does the more stable carbocation form there?
Because that carbon is bonded to more carbons already. It can handle the positive charge better. It's more substituted.
Okay, that makes sense. So basically, the HBr adds across the double bond, but the hydrogen goes to the carbon with more hydrogens, and the bromine goes to the more substituted carbon.
Precisely. That's Markovnikov's rule in action. And the speed of the whole reaction is determined by how fast that carbocation forms. The first step dominates.
So it's all about that slow, unstable carbocation. I see. It is like real estate.
Yes. I love that analogy.
Okay, so we've got this carbocation. What happens next in terms of energy?
Time to map out the energy profile. And it's basically a graph showing energy changes during the reaction.
Okay, energy on one axis, reaction progress on the other?
Exactly. We start with the reactants, then a peak representing the first transition state.
That initial hurdle.
Yep. Then we dip down to the carbocation intermediate. It's kind of stable, but not the end.
So it's like a little valley on the graph.
Precisely. Another peak represents the second transition state.
Another energy barrier.
And then finally, we drop down to the energy level of the products, the final state.
Gotcha. Reactants, first transition state, carbocation, second transition state, then products.
And the highest peak? That's the rate-determining step.
The slowest part of the whole process.
Because it requires the most energy. It dictates the reaction's speed.
So a bigger peak, a slower reaction.
Exactly. Lower activation energy means faster reaction.
So basically, we can visualize the entire reaction's energy changes.
Totally. Energy profiles make it easy to see which step controls the overall rate.
Okay, so these reactions sometimes produce multiple products, right?
Exactly. And that's where regioselectivity comes in.
What now?
Regioselectivity. It just means that a reaction favors one particular region of a molecule over others.
Okay, makes sense. So like one side of the molecule is preferred.
Precisely. A classic example is when you react an unsymmetrical alkene with something like HCl.
So not symmetrical, like uneven.
Right. Markovnikov's rule predicts which product will be the major one.
Markovnikov sounds intense. What's the rule?
Basically, the hydrogen from the HCl attaches to the carbon with more hydrogens already attached.
Wait, the hydrogen goes where there are more hydrogens? That's kind of backwards.
It is, but the reason for that is carbocation stability.
Carbocation, what now? Is that like a positively charged carbon?
Exactly. The reaction forms a carbocation intermediate, and more substituted carbocations are more stable.
More substituted, like bonded to more stuff?
Exactly. So the reaction favors forming the more stable carbocation, which leads to Markovnikov's product.
Okay, so basically the major product comes from the most stable carbocation intermediate. Got it.
You nailed it. Regioselectivity is all about predicting which region reacts based on stability and other factors.
So it's not random. There's a reason for it.
Definitely not random. It's all about following the rules of chemistry.
Okay, so we covered a lot. Can we recap the key things to remember?
Absolutely. First, alkenes and alkynes, those are your carbon-carbon double and triple bonds, always act as nucleophiles.
So they're donating electrons.
Exactly. They're attracted to positive charges.
Got it. What's next?
The mechanism always, and I mean always, involves a carbocation intermediate.
That unstable, positively charged carbon.
Yep, super reactive. And only the pi bond, that weaker bond in the double or triple bond, is the one that breaks.
Not the sigma bond?
Never the sigma bond in these reactions.
Good to know. One less thing to worry about.
And lastly, the energy diagram. Remember those?
Vaguely. Lots of hills and valleys.
2 humps. 2 transition states. The first hump, forming that carbocation, is always higher.
Meaning it needs more energy.
Right. It's the rate-determining step. So nucleophilic attack, carbocation intermediate, pi bond breaks, and 2 humps on the energy diagram where the first one is higher.
Okay, that's actually pretty straightforward when you lay it all out like that. Makes a lot of sense.
Everybody,
All right,
welcome
I
to
think
the
that
show.
about does it.
Ben, how are you doing today?
I'm doing great, Rachel. Super excited to be here.
Okay, so we understand basic nucleophiles. What about pi bonds? Can they be nucleophiles too?
Absolutely. Pi bonds are electron-rich. Think of them as a cloud of negative charge, just waiting to react with something positive.
So, like, they attack positive things?
Exactly. They're particularly good at attacking carbocations, which are carbon atoms with a positive charge. Very unstable.
Unstable how?
They desperately want to grab electrons. So a pi bond will happily donate electrons to stabilize them.
Okay, so what happens after the pi bond attacks?
Well, that's where it gets interesting. It often leads to addition reactions, where atoms or groups of atoms add to the molecule.
Addition, like A plus B becomes AB?
Precisely. But with pi bonds, it's often regioselective.
Regio what now?
Regioselective means that the addition happens preferentially at one specific location on the molecule over others, usually because one carbocation is more stable than the others.
So carbocation stability determines where the reaction goes?
Precisely. The more stable carbocation will be favored, leading to a specific product. Here's the cool part.
Yeah?
You can predict the major product by figuring out which carbocation would be the most stable.
So what's the deal with these carbocations?
They are these positively charged carbon ions. Super unstable.
Unstable how?
High energy. They really want to react with something to become stable.
So they don't just hang out.
Exactly. They're intermediates, fleeting moments in a reaction.
Okay, so what kind of reaction?
Electrophilic addition usually happens in 2 steps because of them.
2 steps?
Yeah. Pi bond attacks, forming the carbocation.
Pi bond like the double bond?
Exactly. That's step 1. The carbocation forms. Then it gets attacked.
Attacked by what?
A nucleophile. Something with electrons to donate.
Okay, so attack, then another attack.
Pretty much. The first step, carbocation formation, is usually slower. Rate determining, you know?
The bottleneck.
Yep. The stability of that carbocation is key, though.
Why is that?
More stable carbocation, faster the reaction.
It's easier to form.
So why are some carbocations more stable than others?
It's all about electron donation.
Electron donation.
Exactly. Alkyl groups, like methyl or ethyl, are electron donating. The more alkyl groups attached to the carbocation, the more stable it is.
So a carbocation with 3 alkyl groups is more stable than one with just 1?
Precisely. That's why tertiary carbocations are more stable than secondary, which are more stable than primary, and so on.
Okay, that makes sense. But how exactly do these alkyl groups donate electrons?
2 main ways: inductive effects and hyperconjugation.
Inductive effects.
It's the donation of electron density through sigma bonds.
Sigma bonds.
Yes, just regular single bonds. Alkyl groups pull electrons towards themselves, slightly reducing the positive charge on the carbocation.
Okay, so it's like they're sharing the positive charge a bit.
Exactly. And then there's hyperconjugation,
which is
overlap of sigma bonds with the empty p orbital on the carbocation.
Empty p orbital.
The carbocation carbon has an empty p orbital. Short pause. Sigma bonds on neighboring carbons can align and donate electron density into that empty orbital, stabilizing the carbocation.
So it's like another way of spreading out the positive charge?
You got it! More alkyl groups mean more sigma bonds available for hyperconjugation, leading to greater stability.
Okay, so what other factors stabilize carbocations besides induction?
Resonance is huge, especially with pi systems or lone pairs.
Resonance. So like electron delocalization?
Exactly. It's all about spreading that positive charge out.
So the more it spreads, the more stable it is?
Bingo. Think of a carbocation next to a double bond.
The electrons and the double bond can kind of help out?
Precisely. It creates a resonance structure, stabilizing the positive charge.
And what about lone pairs? How do those work?
Lone pairs can donate electron density, stabilizing that positive charge.
So like an oxygen with its 2 pairs of electrons.
Perfect. It can form a double bond, shifting the positive charge.
Okay, I see. But does this ever cause problems?
It can, because charge delocalization creates multiple reactive sites.
Meaning?
You can end up with a mixture of products from different reaction locations.
Oh, that makes things complicated.
Totally. Predicting the major product becomes trickier.
So basically, resonance, while stabilizing, can also create more possible outcomes. Is that right?
You nailed it.
So how does this carbocation stability thing actually affect reactions?
That's where the Hammond postulate comes in.
Hammond what?
It basically says that the transition state of a reaction resembles the species it's closest to in energy.
Okay, so?
If forming a carbocation is the slow step, the transition state will look a lot like a carbocation.
And a more stable carbocation means a more stable transition state, which means a faster reaction.
It affects where the reaction happens and how fast.
So it's all about which carbocation is happier.
Exactly. Think about adding HCl to isobutylene.
Okay, isobutylene.
The hydrogen's going to add to one of the carbons, right?
Right.
But which one? It adds to the carbon that gives you the more stable carbocation.
So the more substituted one with more carbons attached?
Yep, you get mostly tert-butyl chloride. That's regioselectivity. The reaction selects a specific region of the molecule.
Because that path is faster because of the Hammond postulate.
Nailed it. Carbocation stability dictates the major product.
So what actually happens during carbocation formation? Like step by step?
It's a concerted process. Everything happens at once.
So not a series of distinct steps.
Exactly. Think of it as one smooth, continuous transformation.
Okay, walk me through it.
As the leaving group starts to depart, the pi bond is breaking.
Breaking to form what?
Breaking to accommodate the positive charge that's developing.
And at the same time?
At the same time, a new sigma bond begins to form.
The sigma bond forming as the pi bond breaks?
Yes, there is a partial positive charge building on the carbon.
partial positive.
Before the carbocation is fully formed, it carries only a fraction of the positive charge.
And this all happens in one fluid motion?
Precisely. It's a transition state, not a stable intermediate.
So basically, everything shifts at once. Pi bond breaks, sigma bond forms, and positive charge develops simultaneously.
That's a good way to put it.
So once you have that carbocation, what happens next?
That carbocation is super reactive, right? It's just begging for electrons.
Like a moth to a flame.
Exactly. It gets captured almost instantly by any nearby nucleophile.
Nucleophile meaning?
Any molecular ion with a lone pair of electrons ready to share. Water, alcohols, halides, anything like that.
Gotcha. So what kind of products are we talking about?
That's the fun part. It depends on the carbocation itself. Is it primary, secondary, tertiary?
Right. Stability matters.
Big time. More stable carbocations can sometimes rearrange before capture.
Rearrange? How so?
A hydrogen or a methyl group might shift over to create a more stable carbocation.
So you can get unexpected products.
Definitely. You can end up with a mix of products, depending on which carbocation gets captured and where.
Complicating things even further. Oh.
That's organic chemistry for you.
So when a carbocation forms, what does that do to the shape of the molecule?
It goes planar. Think of it going from sp3 hybridized to sp2.
Oh, like a flat triangle?
Exactly, a trigonal planar shape. And that's key for stereochemistry.
Why is that?
Because the incoming nucleophile can attack from either side of that plane.
So it's not selective?
Not at all. It's equally likely to attack from the top or the bottom.
And what does that create?
A racemic mixture, if the carbon becomes a stereocenter. Equal amounts of both enantiomers.
Wait, so the reaction isn't stereospecific?
Precisely, because the carbocation intermediate loses all stereochemical information. The planar shape allows attack from either face with equal probability.
So basically, if you make a carbocation next to a chiral center, you're screwed.
You'll lose stereochemical purity, yeah, unless something else influences the attack, like steric hindrance.
Steric hindrance.
Bulty groups blocking one side, but normally planar carbocations lead to racemization.
All right, that about wraps it up then.
Yeah, for sure.
Thanks,
Welcome
Ben.
to the show.
Ben, how are you doing today?
I'm doing great, Rachel. Thrilled to be on.
So we're diving into alkene addition reactions now. What makes these reactions so important in organic chemistry?
They're fundamental. Alkenes are reactive because of that double bond, right?
Right.
So addition reactions are a way to break that bond and add new things, creating all sorts of different molecules.
So it's like a building block reaction?
Exactly. We're going to unpack some key things today.
Like what?
Markovnikov selectivity is a big one.
Markovnikov? Sounds intimidating.
It just means that in some additions, the hydrogen likes to attach to the carbon that already has more hydrogens.
Okay, that's not so bad. What else?
Carbocation rearrangements are sneaky. These can shift and change the product.
Rearrangements? How does that even happen?
We will get to it. We'll also talk about halonium ion formation, which creates these interesting three-membered ring intermediates.
A ring? I didn't expect rings.
And finally, stereochemistry. How the atoms are arranged in 3D space really matters.
So it's not just what's added, but how it's added.
Precisely. It all affects the final product.
Okay, let's talk about hydrating alkanes. What happens when we add water to an alkane?
We get an alcohol, but you need a strong acid catalyst to get it to go.
Like sulfuric acid?
Exactly. The acid helps add a proton to one of the carbons in the double bond.
And that breaks the double bond?
It does, creating a carbocation. Then water attacks that carbocation.
Carbocation? What's that?
A positively charged carbon. It's really unstable and wants to react.
Okay, so water attacks the carbocation, then what?
Then you lose a proton and you've got your alcohol.
But which carbon gets the alcohol? Does it matter?
It totally matters. Markovnikov's rule tells us that the most substituted carbon gets the alcohol.
Most substituted? Meaning?
The carbon with the most other carbons attached to it.
More carbons, more stable carbocation.
So the reaction favors forming the more stable carbocation first.
Precisely. That's why you mostly get secondary or tertiary alcohols, not primary.
Give me an example. Like if I have propene.
Propene becomes isopropanol. The alcohol goes on the middle carbon, the one with two methyl groups attached.
So we were talking about hydration. What happens if instead of water, we add an alcohol?
Great question. It's actually pretty similar. The alcohol acts as the nucleophile instead of water.
So it attacks the carbocation?
Exactly. And under similar acidic conditions to hydration.
Okay, so acid catalyst needed.
Yep, to protonate the alkene and form that carbocation intermediate.
And we still get Markovnikov selectivity?
You bet. The alcohol adds to the more substituted carbon, the one that can better stabilize the positive charge.
So what's the final product then?
Instead of an alcohol, you get an ether, because you've added an OR group from the alcohol.
Ah, right. So like ROR?
Precisely. It's alcohol addition forming an ether instead of water addition forming an alcohol.
Okay, alcohol addition equals ether. Got it.
Yes, and this is a really useful way to synthesize ethers, especially if you want a specific substitution pattern.
Because of the Markovnikov selectivity.
Exactly. You can predict where the OR group will end up.
Okay, so now things get really interesting. What about when the carbocation just moves?
Carbocation rearrangements. It's like musical chairs for positive charges.
Musical chairs, I like that. How does it work?
Basically, a hydrogen atom, or sometimes a methyl group, shifts from one carbon to an adjacent carbon.
Wait, a whole hydrogen just jumps?
With its electrons. It's called a hydride shift.
And why does it do that?
Stability. The carbocation will shift to become more stable. Tertiary carbocations are the most stable, then secondary, then primary.
So it's all about finding the most stable spot.
Exactly. Like a little positive charge optimizing its location for maximum chill.
Give me an example.
If you have a secondary carbocation next to a quaternary carbon, a hydride shift can occur to create a more stable tertiary carbocation.
Wow. So you can end up with a completely different product than you'd expect?
Absolutely. And sometimes you can even have multiple shifts, leading to a mixture of isomeric products.
Isomeric, as in same formula, different structure.
Bingo. There's also resonance stabilization.
Resonance? Tell me more.
If the carbocation can be stabilized by resonance, it'll rearrange to make that happen. Think of it like the positive charge spreading out.
Okay, so these alkenes react with halogens, like bromine or chlorine, right?
Exactly. And that's kind of weird when you think about it.
Why is it weird?
Well, bromine isn't exactly super electron hungry on its own, but it can be induced to be electrophilic. Think of it like temporarily giving it a positive charge.
Temporarily? How?
The alkene's electrons kind of nudge bromine's electron cloud, creating a slight positive end. That positive end then gets attacked.
Okay, so it's like a temporary positive charge makes it reactive.
Precisely. And instead of a carbocation, like we saw before, we form a halonium ion.
A halonium ion? What's that?
It's a three-membered ring with the halogen, like bromine, holding onto both carbons of the original double bond.
So no carbocation intermediate?
Nope. This has major implications for the stereochemistry of the product, leading to what we call, whispering, anti-addition.
Anti-addition? What does that even mean?
It means the two bromines add to opposite faces of the original double bond. Think of it like one bromine attacking from the top and the other from the bottom.
Ah, that makes sense. Because the halonium ion blocks one side.
Exactly. It forces the second bromine to attack from the opposite side.
Okay, so we've been throwing around halonium ion a lot, but is there actual proof that these things exist?
Oh, absolutely. X-ray crystallography has directly imaged halonium ions. It's amazing.
Wait, really? They just saw one?
Pretty much.
It confirms the three-membered ring structure we've been talking about.
That's wild. So if the halonium ion is real, why do we only ever see anti-addition? What's stopping the nucleophile from attacking from the same side the halogen added to?
Steric hindrance is the main culprit. The halogen is bulky. It blocks that side.
So it's literally just too crowded.
Exactly. The nucleophile has a much easier time attacking from the opposite face.
Okay, that makes sense. But is there anything else going on besides just physical space?
Molecular orbital theory also plays a role. The backside attack lines up better with the anti-bonding orbital of the carbon-halogen bond.
Oh, right. Because that bond is breaking as the new one forms.
Yes, that backside attack is favored. So steric hindrance plus orbital alignment equals exclusive anti-addition.
Got it. So basically, the halonium ion is real, but it's also like super strategically defended against attacks from one side.
Perfect summary. It's a fortress against syn addition.
Okay, so now, what if we tweak halogen addition a little?
We get halohydrin formation. Think of it as halogen addition's cousin.
How so?
Well, instead of just a halogen, we throw water into the mix. It's like a battle of the nucleophiles.
Nucleophiles? Remind me.
They're just molecules that are attracted to positive charges and donate electrons. In this case, it's water versus a halogen ion.
Okay, water's competing. What happens?
The water actually wins in attaching to the carbon. But here's the cool part. It's very specific about where it attaches.
Specific how?
It favors the more substituted carbon.
More substituted meaning?
The carbon with more other carbons attached to it. And the addition happens in a trans manner, meaning the hydroxy group and the halogen end up on opposite sides.
Trans addition. Got it. So basically, halohydrin formation is halogen addition, but with water muscling in to add to the more substituted carbon in a trans fashion.
Exactly. It's all about who's the better nucleophile and where they prefer to attack.
Okay, so we covered a ton today. Let's recap some of those key ideas.
Definitely. We talked about Markovnikov's rule and how it predicts where the electrophile adds.
Right. The rich get richer. What else?
Carbocation rearrangements are super important to remember. They can shift to create more stable carbocations.
Like a game of carbocation musical chairs.
Exactly. Then we went over halonium ion formation, which leads to anti-addition.
Anti-addition, meaning they add to opposite sides?
Yes, because the bulky halonium ion blocks one face of the molecule.
And what about halohydrins?
Halohydrins form when water is present. You get an alcohol and a halogen on adjacent carbons.
Okay, so Markovnikov's rule, carbocation rearrangements, halonium ions, anti-addition, and halohydrins. Is that everything?
Those are the big ones we hit today. Understanding these mechanisms helps predict the products in stereochemistry.
Stereo what now?
Whether the products are on the same or opposite sides, like in anti-addition, it's all spatial arrangement.
Gotcha. So basically, knowing this stuff is key to predicting what you'll get in a reaction.
Absolutely. It gives you the tools to work out the mechanisms and figure out the products.
Awesome. Thanks for walking us through all of that. Super helpful.
All right. I think that wraps
Welcome
things
back.
up.
Rachel, how are you today?
I'm fantastic, Ben. Really ready to jump in.
So we keep talking about all these molecules. How do we actually change them?
That's where functionalization comes in. Specifically, alkene functionalization.
Alkene functionalization? What's that even mean?
Basically, it's how we take alkenes, those molecules with carbon-carbon double bonds, and turn them into something more complex, like adding different functional groups.
So like Legos for molecules?
Exactly. The double bond is a reactive spot. Think of it as a handle that we can grab onto.
And what kinds of reactions are we talking about?
Tons. Hydrogenation, where you add hydrogen. Halogenation, where you add halogens like chlorine or bromine. Hydration, adding water.
Wait, adding water to an alkene? That sounds wild.
It is. It's a fundamental way to make alcohols. And the cool part is,
all these reactions have specific stereochemical outcomes.
Stereo... what now?
Stereochemistry. It's the 3D arrangement of atoms in a molecule. These reactions can create specific arrangements.
So the reaction can be controlled to make certain shapes.
Precisely. We use that double bond, that pi bond, as a nucleophile. It's like an electron-rich site that attacks electron-poor sites.
So the pi bond is the key to everything.
Absolutely. It's the starting point for building all sorts of interesting and useful molecules.
So what happens when we want to make an epoxide?
That's where epoxidation comes in. We're basically turning an alkene into an epoxide.
Okay, but how does that actually work?
We typically use peroxycarboxylic acids. Think of it like adding an oxygen atom across the double bond.
So it just sticks right on?
Pretty much. It's a concerted mechanism. Everything happens in one step.
Concerted? What does that mean?
No intermediates, no rearrangements. The oxygen from the peroxy acid attaches to both carbons of the double bond simultaneously.
That sounds efficient.
It is. And it's a syn addition.
Syn? Like same-side syn?
Exactly. Both the new carbon-oxygen bonds form on the same face of the alkene.
So stereochemistry matters?
Big time. If your alkene has stereocenters, the epoxide will reflect that.
Meaning?
The relative stereochemistry is retained. If the substituents were cis, they'll still be cis on the epoxide.
Okay, cis stays cis. Got it. What about trans?
Trans stays trans. The spatial arrangement is preserved during the epoxidation.
So basically, we're adding oxygen to the alkene in a way that keeps the original structure intact?
Precisely. It's a stereospecific reaction.
Okay, so what about epoxides? How do those ring openings work?
Epoxides are cool because they're strained. That makes them reactive.
Strained how?
Ring strain. That 3-membered ring wants to pop open.
Like a coiled spring.
Exactly. Now, you can open them under acidic or basic conditions. But here's the fun part.
Tell me.
The reaction mechanism changes, and so does where the nucleophile attacks.
Wait, it attacks different places?
Yup. Under basic conditions, it attacks the less substituted carbon.
Why less substituted?
Sterics. It's easier to get to the less crowded carbon. But under acidic conditions...
It's the opposite.
You bet. The nucleophile attacks the more substituted carbon.
Okay, why the flip?
Acid protonates the epoxide oxygen. That makes the more substituted carbon want to leave more. It develops a positive charge.
So it's like partially carbocation-like?
Precisely. And one more thing. The addition is always anti.
Anti as in opposite sides?
Yep. The nucleophile attacks from the back, opposite the leaving group. Always.
Got it. So basically, epoxides are like tiny, strained rings that can be opened with acid or base, but the nucleophile attacks different carbons depending on the conditions, and it's always anti-addition.
You nailed it.
So what's this hydroboration oxidation thing all about?
It's a way to add water to an alkene, but with a twist.
A twist?
Yeah. It's anti-Markovnikov hydration, meaning the hydrogen adds to the more substituted carbon and the hydroxyl group to the less substituted one.
Wait, the opposite of what I'd expect?
Exactly. And it's syn addition. The hydrogen and hydroxyl add to the same face of the alkene.
Okay, but how does it actually work?
It starts with borane, BH3, or a borane derivative like BH3THF or dicyamyl borane.
Dicyamyl what?
Yeah, it's a bulky borane. Anyway, the borane adds to the alkene one hydrogen at a time until all 3 hydrogens on boron are used up.
So it's like a stepwise thing.
Precisely. Then you oxidize the carbon-boron bond with hydrogen peroxide and base to get the alcohol.
Sounds complicated. Can you give me a real-world example?
Sure. Take 1-methyl cyclohexene.
Hydroboration oxidation will give you 2-methyl-cyclohexanol with the hydroxyl group on the less substituted carbon and syn addition.
So you get a specific stereoisomer, too.
Totally. It's a stereospecific reaction.
Okay, so anti-Markovnikov and syn addition. Got it.
So we've got the boron attached to the carbon. What happens next?
Oxidation. This is where the magic happens. We swap the boron for an OH group. Basically, we're turning that BC bond into a COH bond.
Wait, really? Just like that?
Well, there's a bit of chemistry involved. We use hydrogen peroxide in a base, like sodium hydroxide. It's a reaction that's pretty clean.
Clean how?
It means we don't get a bunch of side products messing things up. But the coolest part is that the OH group ends up on the same side of the molecule where the boron was.
So the stereochemistry is retained.
Exactly. This is super useful. If you carefully control which side the boron attaches to, you also control where the alcohol ends up.
Okay, but why is that important?
Think about building complex molecules. You need to be able to put functional groups, like alcohols, exactly where you want them. Hydroboration oxidation is a fantastic way to do that with precise stereochemical control.
So basically, what you're saying is we can choose which side of the molecule gets the alcohol?
Precisely. It's like having a tiny molecular GPS. You navigate the boron to the exact spot, and then oxidation puts the OH group right there.
That's wild. That sounds like a chemist's dream.
It really is, and that's why hydroboration oxidation is such a powerful tool in organic synthesis.
Okay, so we know about adding water using acid, but what if we want the alcohol on the less substituted carbon?
That's where hydroboration oxidation comes in. It's like the anti-acid hydration. It puts the alcohol on the opposite carbon.
Opposite as in?
Anti-Markovnikov. The OH group ends up on the less substituted carbon in hydroboration oxidation.
So basically, we get to choose where the alcohol goes.
Exactly. If you want the more substituted alcohol, you use acid hydration. Less substituted, hydroboration oxidation.
Wait, it's really that simple?
Well, there's also stereochemistry to consider. Hydroboration oxidation is syn addition.
Syn addition meaning?
The H and OH add to the same side of the double bond. Acid hydration doesn't really have that level of control.
So hydroboration oxidation is more controlled.
Exactly. Regioselectivity and stereochemistry. It gives you more control over the final product.
Okay, so to recap, acid hydration gives us Markovnikov addition, and hydroboration oxidation gives us anti-Markovnikov and syn addition. Got it.
Precisely. Choosing the right method is key for getting the alcohol you want.
This is so cool.
Okay, so we can break double bonds using ozone, but what about just adding hydrogen?
Hydrogenation. That's a classic. We use molecular hydrogen, H2, to saturate those alkenes.
So like turn them into alkanes?
Exactly. But it needs a catalyst. Usually it's a metal like palladium on carbon.
Palladium? What's that do?
It basically grabs the hydrogen and the alkene and brings them together on its surface.
Like a dating app for molecules.
You could say that. The cool part is the two hydrogens add to the same side of the alkene.
Wait, what's that called again?
Syn addition. SYN.
So both hydrogens end up on the same face of the molecule.
Yep. Think of a cyclic alkene, like cyclohexene.
Okay, I'm picturing it.
Hydrogenate that and both hydrogens will add either on the top face or the bottom face.
So it's like predictable.
Very predictable and super useful for controlling the stereochemistry of the product.
Nice. Anything else we can do to alkanes?
Oh, yeah, plenty. Let's talk about adding water.
All right, I think we should stop there.
Welcome to the show.
Yeah, definitely.
Rachel, how are you doing today?
I'm doing fantastic, Ben. I'm super pumped to be here.
Okay, so we've looked at alkenes with just one double bond,
But what happens when we have more?
Then you're dealing with dienes or polyenes, basically molecules with multiple double bonds.
Dienes. Got it. Why are they so important?
Well, those pi bonds, those double bonds, they act as nucleophiles.
Like they're attacking stuff?
Exactly. And that opens up a whole world of reactions. We can classify dienes based on how those double bonds are arranged.
Like next to each other?
Or separated by single bonds, or further apart. We'll get into that. Plus, we'll talk about electrophilic addition to dienes.
Electrophilic addition, got it. Anything else?
Temperature effects on reactions, that's a big one. And then we can move on to alkynes, which have triple bonds.
Triple bonds, so even more reactive?
You bet. We'll cover their reactivity, hydration, and hydrogenation.
Hydration and hydrogenation?
Adding water and hydrogen. Basically everything you need to know about dienes and alkynes.
Okay, so dienes. What are the different types?
Well, they're classified by how close those double bonds are.
Gotcha.
First, we have isolated dienes.
Isolated? As in keep away from others?
Exactly. They have double bonds separated by more than one single bond.
Okay, so they're not directly next to each other.
Right. So those double bonds act independently, like separate little pi systems.
Interesting. And the other type?
Conjugated dienes. This is where the fun starts.
Ooh, fun.
Yeah. Conjugated dienes have alternating single and double bonds.
So they're right next to each other?
Almost. There is a single bond separating them.
And that makes a difference?
Huge difference. It allows for electron delocalization.
Delocalization? Is that like spreading out?
Yes. The electrons aren't stuck in one place. They can move across the whole conjugated system.
Whoa, cool. So it's all connected.
Yep. Single, double, all the way through. That's conjugation.
Okay, so what about when we have more than one double bond, but they're isolated? Like, not conjugated?
Good question. Isolated dienes react pretty much like individual alkenes.
So each double bond reacts separately?
Exactly. You just have to consider each pi system independently. And think about carbocation stability.
Carbocation stability still rules everything, huh?
Always. Let's say you react 2-methyl-1,4-pentadiene with HBr.
Okay, picture that in my head. The H will add to one of the double bonds, forming a carbocation.
Right, Markov-Nikov's rule applies. More substituted carbon gets the positive charge.
Bingo. The most stable carbocation determines the major product for that double bond's reaction.
And the other double bond just chills. Yep, it's unaffected. You'll get a mixture of products where HBr added across either the first or the second double bond, favoring the more stable carbocation in each case.
So basically, treat each double bond like it's all alone and follow the rules we already know.
Precisely. Analyze each independently, focus on carbocation stability, and you're golden.
Got it. But what happens when those double bonds aren't isolated?
Ooh, that's where things get really interesting. We get into conjugated systems.
So conjugated dienes, that's a mouthful. What makes them so special in reactions?
They have alternating single and double bonds. This creates a resonance-stabilized carbocation when they react.
Resonance, stabilization, got it. So how does that affect the products we get?
It leads to two possible addition products, 1,2 and 1,4 addition. Think of it as adding to the first and second carbon or the first and fourth.
Okay, but which one do you get?
It's temperature dependent. Lower temperatures favor the 1,2 product. It's formed faster.
Faster? Why?
It's kinetic control. The 1,2 product has a lower activation energy. At higher temperatures, the 1,4 product is favored.
And that's because it is more stable?
Exactly. Thermodynamic control. The 1,4 product is usually more stable due to alkene stability.
Alkene stability? What's that?
More substituted alkenes are more stable. So if the 1,4 product has a more substituted alkene, it wins out at higher temperatures.
So basically, temperature dictates which product is favored. Low temp, faster product. High temp, more stable product?
Precisely. And the key is that resonance-stabilized carbocation intermediate.
Okay, so alkynes, what makes them special?
They have these 2 pi systems, right? Orthogonal to each other.
Orthogonal, meaning?
At right angles. It changes their reactivity a lot.
How so?
Well, there's no conjugation like in dienes. Each pi system acts kind of independently.
Interesting. So how do you things add to them?
Let's talk about HX, addition. Hydrohalic acids.
Okay.
It's a concerted mechanism. The H and X add at the same time.
Concerted. Got it. What does that form?
A vinyl halide. Halide on an alkene.
And then it can add again?
Exactly. You can get a geminal dihalide.
Geminal? What does that mean?
2 halogens on the same carbon. And it follows Markovnikov's rule.
Meaning the halogen goes to the more substituted carbon, right?
Yep, the more stable carbocation intermediate.
Okay, that makes sense. So what happens when we try to hydrate alkynes?
We can actually do it in a couple of different ways. 2 main methods, acid-catalyzed hydration or hydroboration oxidation.
Okay, acid catalyzed. How does that work?
It adds water across the triple bond, but it initially forms an enol, which is an alcohol directly bonded to a double bond carbon.
An enol? Never heard of it.
They're not very stable. It quickly tautomerizes to a ketone.
Tautomerizes? What's that even mean?
Basically, it's an isomer that rapidly interconverts. In this case, a proton shifts, turning the enol into a ketone. So, acid-catalyzed hydration of alkynes gives you ketones.
Okay, so acid makes ketones. What about this other method?
Hydroboration oxidation is the alternative. It uses borane reagents followed by oxidation with hydrogen peroxide.
And that gives us?
Aldehydes, but there's a catch. It only really works well with terminal alkynes, where the triple bond is at the end of the carbon chain.
Why terminal alkynes only?
It's all about the regiochemistry. It adds anti-Markovnikov. The boron wants to attach to the less substituted carbon of the triple bond.
Anti-Markovnikov. Got it. So that's how you get aldehydes instead of ketones.
Precisely.
So we've reduced alkenes. What about alkynes?
Alkynes. Now we're talking. They can be reduced all the way to alkanes.
All the way?
Yep. With, say, palladium on carbon, PD/C, just like with alkenes.
Okay, same catalyst. Makes sense.
But the cool part is we can stop halfway and get an alkene.
Wait, really? How?
Lindlar's catalyst. It's a poisoned palladium catalyst.
Poisoned? Like literally?
Well, it's modified to only reduce the alkyne once. It gives you a cis alkene.
Cis only? Why?
Because both hydrogens add to the same side of the alkyne, syn addition. The alkyne sits on the catalyst surface and the hydrogens just add to the same face.
So basically, PD/C goes all the way to the alkane, and Lindlar's stops at this cis alkene.
Exactly. Total control. And the cool thing? Whispering. If you want the trans alkene, there's another trick.
Oh, I'm listening.
Sodium in liquid ammonia. It's a single electron reduction.
Whoa, it sounds intense.
It is. And it gives you the trans alkene. Stereochemistry control for both cis and trans alkenes from alkynes.
Okay, so we've covered how to predict the products, but what I'm hearing is there's a deeper why here, right?
Exactly. It's all about understanding the mechanism.
Mechanism?
Yeah, like with both HBr and water adding to alkenes, you get a carbocation intermediate.
A carbocation, so like a carbon with a positive charge.
Yep. And that same carbocation can lead to different products depending on what attacks it.
Wait, so the same intermediate can give you different final products?
Absolutely. If bromide attacks, you get one product. If water attacks, you get another. It's all about what's available.
So basically, the environment the reaction is in determines what happens next.
Exactly. That's why memorizing reactions is a bad idea. Whisper, understand the carbocation, understand the players, and you can predict almost anything.
That makes so much more sense than rote memorization.
It's a philosophy, really. Mechanisms first, memorization never.
I love that. It's like understand the why and the what takes care of itself.
Precisely.
Well, that's about wraps it up.
Welcome
Yeah,
to
I
the
think
show.
so.
Rachel, how
Thanks,
you doing
Rachel.
today?
I'm fantastic. So glad to be here.
Okay, let's talk about conjugation and aromaticity. What's the deal with conjugated systems?
They're molecules with alternating single and double bonds.
And why does that matter?
It creates overlapping p orbitals, leading to unique properties, like stabilization.
Stabilization?
Yeah, the electrons are delocalized, spreading the electron density. Think of it like spreading peanut butter on bread. It's more stable when spread.
Got it. So, how does this affect the molecule's behavior?
They absorb UV-vis light, undergo unique reactions, and can be aromatic.
Aromatic? Like they smell good?
Originally, yes, but in chemistry, it refers to special stability. It's determined by Huckel's rule.
Huckel's rule?
Yeah, a cyclic planar conjugated molecule with 4n+2 pi electrons is aromatic.
So basically, what you're saying is alternating double bonds can lead to weird and stable molecules sometimes.
Exactly. And that stability has massive implications for reactivity and function.
So, what's the deal with conjugated versus isolated pi bonds?
It's all about whether those pi bonds can talk to each other. Conjugated systems can, isolated ones can't.
Talk? What do you mean?
Think of it like a chain of dominoes. Conjugated pi bonds are like dominoes lined up perfectly. One falls, they all fall.
Okay, I'm following.
Isolated pi bonds, those are like dominoes with a brick wall between them. One falls, nothing happens to the others.
So, what's the brick wall in molecules?
sp3 carbons, those carbons with 4 single bonds, they interrupt the flow of electrons.
Wait, really? So, like one little sp3 carbon can just ruin the whole thing?
Absolutely. It breaks the chain of overlapping p orbitals that allow electrons to delocalize.
Delocalize.
Spread out. Think of it like this. Electrons in conjugated systems aren't stuck in one place. They can move around. It makes the molecule more stable.
So basically what you're saying is, if there's an sp3 carbon in between the double bonds, then it's not conjugated.
Exactly. It's isolated. No electron party happening there.
Got it. Dominoes versus brick walls makes perfect sense.
Okay, so how do we actually build these molecular orbitals?
Think of it like constructing a ladder. The lowest energy orbital has 0 nodes.
Nodes being where the wave function changes sign.
Exactly. Then each orbital above that has one more node than the last.
So it's like ground state, first excited state, second excited state, and so on.
Precisely. And the number of molecular orbitals is equal to the number of p orbitals you started with.
Got it. So for butadiene, that's 4 molecular orbitals.
Yep. Then you fill them with electrons, lowest energy first, like usual.
And the highest occupied molecular orbital is the HOMO, and the lowest unoccupied is the LUMO.
You nailed it. The HOMO and LUMO are super important because they dictate reactivity.
Wait, really?
Yeah.
How so?
The HOMO donates electrons, and the LUMO accepts them. So the energy gap between them tells you how easy it is to get the molecule to react.
So a smaller gap means it's more reactive.
Bingo. And that's how we predict which molecules will react and how. Now,
Okay, so what's the deal with bond lengths when we're talking about conjugated systems?
they're weird. Single bonds get shorter, double bonds get longer. It's all thanks to electron delocalization.
Wait, so they meet in the middle? Like they're trying to be the same length?
Pretty much. It's not a true single or double bond anymore. Partial double bond character. Everywhere.
Okay, and what about rotation? Does conjugation affect that?
Big time. Normal single bonds rotate freely, but with conjugation, there's a barrier.
A barrier? Like, it doesn't want to rotate?
Exactly. That partial double bond character makes it harder to twist. It prefers to stay flat, coplanar.
So, less rotation. What does this mean for the molecule itself?
Stability. Conjugation makes molecules more stable. Delocalized electrons are happy electrons.
Happier than localized ones?
Way happier. Think of it like spreading out the stress. The more you spread it, the less stress there is in any one place.
So basically, conjugation is like the molecule's chill pill?
Totally. Lower energy, more stable. That's the power of electron delocalization.
So how does this all connect to like visible color?
That's where UV-Vis spectroscopy comes in. It measures how molecules absorb ultraviolet and visible light.
Okay, so light goes in.
And based on what's absorbed, we can figure out the molecule's electronic structure.
Electronic structure? How?
Specifically, the energy difference between the highest occupied molecular orbital, or HOMO, and the lowest unoccupied molecular orbital, or LUMO.
Homo and Lumo? Seriously?
Yep. When a molecule absorbs light, it excites an electron from the HOMO to the LUMO.
And the color we see is what's not absorbed.
Exactly. If a molecule absorbs blue light, we see its complementary color, which is yellow or orange.
Whoa. So how does conjugation affect this?
More conjugation means a smaller HOMO-LUMO gap. Think of benzene versus something like beta-carotene.
Beta-carotene, like in carrots?
Exactly. The extended network of alternating single and double bonds lowers the energy needed for that electronic transition.
So more conjugation, lower energy, right?
Precisely. Lower energy corresponds to longer wavelengths, which shifts absorption towards the visible spectrum.
Making it colorful.
Bingo. Carrots are orange because beta-carotene absorbs blue-green light. Less conjugated molecules absorb in the UV range.
So what exactly is aromaticity anyway?
Think of it like super conjugation, but with extra stability.
Extra stability? How so?
Normal conjugated systems like butadiene have alternating single and double bonds.
Right.
Aromatic compounds are cyclic, flat, and have a specific number of pi electrons.
Specific number? Like how many?
Following what's called Huckel's rule, 4n plus 2, like benzene with 6 pi electrons.
Okay, but what makes them so stable?
The pi electrons are delocalized. They're spread out evenly around the ring.
So it's like everyone gets a piece of the pie.
Exactly. This delocalization lowers the overall energy of the molecule.
Is there any quantitative way to measure the stability?
Absolutely. Heats of hydrogenation are a great example. When you add hydrogen to unsaturated bonds, it releases energy.
Okay, I'm following.
Benzene releases significantly less energy upon hydrogenation than you'd predict based on just 3 double bonds.
Wait, really? Less energy?
Yeah, it's more stable, so adding hydrogen doesn't release as much energy.
Mind blown.
So, how do we actually know if something is aromatic?
There's a 4-part checklist we use.
Okay, lay it on me.
First, it has to be cyclic, a ring.
Makes sense.
Second, it's got to be planar, all atoms in the same plane.
Why planar?
For the p orbitals to align and overlap correctly to form that continuous ring of electron density.
Got it. What's next?
Third, it has to be fully conjugated.
Meaning?
Alternating single and double bonds all the way around the ring, allowing for continuous overlap.
Okay. Cyclic, planar, conjugated, and?
Huckel's rule. This is the big one.
Huckel's what now?
Huckel's rule states that the molecule must have 4n plus 2 pi electrons to be aromatic, where n is any non-negative integer.
So like 2, 6, 10, 14?
Exactly. Benzene, with its 6 pi electrons, is the classic example.
Benzene. Got it. Medium pause. Got it. Any other examples?
Carradine is another common one.
It looks like benzene, but one of the carbons is replaced by a nitrogen.
And that still counts as aromatic?
Absolutely. The nitrogen contributes to the aromatic system.
So, what's next for someone fascinated by aromaticity?
Oh, so much. We can talk about anti-aromatic systems.
Anti-aromatic?
Yeah, they are destabilized by having a ring of overlapping p orbitals and 4n electrons.
4n, not 4n plus 2.
Exactly. Cyclobutadiene is a classic example. Super unstable.
Wow. That's the opposite of stability.
Totally. And then there are heterocycles, rings with atoms other than carbon.
Like nitrogen or oxygen in the ring?
Yep. Pyridine, furan, things like that. These change the electronic properties. We can explore fused rings.
Fused rings?
Rings that share a side. Naphthalene, anthracene, it goes on.
Okay, so it gets more and more complex.
Oh, absolutely. And ions, too. Aromaticity isn't just for neutral molecules.
Ions, That's something else. So it's like a whole new world of rings and electrons?
It is. It's a deep dive into molecular behavior. Aromaticity is just the beginning.
Well, that's a lot to think about.
Yeah, for sure.
Cam, how you doing today?
Thanks for
I'm
having
doing
me.
great. Super excited to be.
So let's tackle aromaticity. What exactly is it?
It's a special stability in cyclic planar molecules.
Okay, cyclic meaning ring-shaped, right?
Exactly. Aromatic compounds show unique reactivity because of this stability.
So, what makes a molecule aromatic?
First, it must be cyclic and planar with conjugated pi bonds.
Conjugated? Explain that.
Alternating single and double bonds, creating a continuous system of overlapping p orbitals.
Okay, got it. Anything else?
Huckel's rule. The ring must have 4n plus 2 pi electrons.
Huckel's rule. So a specific number of pi electrons is key?
Absolutely. It's that magic number that gives them extra stability.
Okay, so if something is aromatic, what makes it that way?
Great question. There are 4 key requirements. First, it needs to be cyclic.
Cyclic, meaning a ring?
Exactly. Second, it has to be planar. All the atoms should be in the same plane.
Like flat.
Yep. Third, continuous p orbital overlap. That means the p orbitals on each atom in the ring need to overlap.
P orbitals? That sounds complicated.
Think of it as a cloud of electrons above and below the ring.
Okay, I think I get it.
Finally, Huckel's rule. It has to have a specific number of pi electrons.
Huckel's rule? What's that?
It states that a molecule is aromatic if it has 4n plus 2 pi electrons, where n is any non-negative integer.
So like 2, 6, 10?
Precisely. If it ticks all 4 boxes, it's aromatic.
So how do we figure out if a molecule is aromatic then?
That's where Huckel's rule comes in. It's all about counting pi electrons.
Pi electrons? What are those?
The electrons in pi bonds, double or triple bonds, basically. And lone pairs can count too, if they're involved in the ring.
Okay, count the pi electrons. Then what?
Huckel's rule says if the number of pi electrons fits the formula 4n plus 2, where n is any whole number, it's aromatic.
4n plus 2. So what, plug in numbers?
Exactly. If n equals 0, you get 2 pi electrons. N equals 1 gives you 6. N equals 2 gives you 10, and so on. If your molecule has that many pi electrons, it's aromatic.
And if it doesn't fit?
Then it could be anti-aromatic, which is unstable, or non-aromatic, which is neither stable nor unstable.
How do you tell the difference?
If it has 4n pi electrons, it's anti-aromatic.
So 4, 8, 12.
Yep. Otherwise, it's non-aromatic.
Okay, so we've talked about what makes something aromatic. What about anti-aromaticity? What is that?
Anti-aromatic compounds are cyclic, planar, have conjugated pi systems, but they have 4n pi electrons.
4n, not 4n plus 2?
Exactly.
This makes them highly unstable.
How unstable?
They'll often distort their geometry to avoid being anti-aromatic. They really don't want to be in that state.
Wow. So what about compounds that are just neither aromatic nor anti-aromatic?
Those are non-aromatic. They don't meet all the criteria. Maybe they're not cyclic or planar or have a fully conjugated system.
So it's like they're missing something essential.
Precisely. They're just regular compounds, not particularly stable or unstable because of aromaticity.
Okay, but how do we know when a lone pair on, say, nitrogen or oxygen in a ring actually participates in the aromatic system?
That's a great question. It boils down to orbital alignment.
Alignment?
Yeah. If the lone pair's orbital is aligned with the pi system, it contributes.
And if it's not?
Then it's basically just hanging out, not part of the aromatic party.
So how do you visualize that?
Think of it like this. If the lone pair orbital is parallel to the p orbitals, it can donate electrons and join the pi system. If it's perpendicular, it can't.
Okay, parallel good, perpendicular bad for contributing to the pi system. Got it.
Exactly. Like in pyridine, the nitrogen lone pair is perpendicular to the ring.
So it doesn't count towards aromaticity.
Bingo. But in pyro, it is aligned, so it donates.
So basically, orientation is everything for lone pair participation.
Precisely. It's all about that orbital overlap.
So we've talked about neutral aromatics. What about ions?
Oh, aromatic ions are super cool. Think about the tropylium ion.
Tropylium? Sounds exotic.
It is. It's a 7-membered ring with a positive charge. Super stable.
Wait, a positive charge makes it more stable?
In this case, yes. It has 6 pi electrons, so it follows Huckel's rule. It's aromatic.
Okay, so positive ions can be aromatic. What about negative ones?
Absolutely. The cyclopentadienyl anion is a classic example. A 5-membered ring with a negative charge.
And that's stable too?
Yep. Again, 6 pi electrons. Aromatic. And this impacts acidity, big time.
How so?
Aromaticity stabilizes the anion after deprotonation. This makes the corresponding acid much stronger.
So basically making an ion aromatic makes it easier to form.
Exactly. Stability is everything.
So how does molecular orbital theory explain aromaticity?
It shows how electrons fill these molecular orbitals. Cyclic, conjugated systems are key.
Like benzene?
Exactly. Benzene is super stable. All its bonding orbitals are filled.
Okay, so filled orbitals equal stability.
Yes, if it follows Huckel's rule. But systems like cyclobutadiene are different.
What happens there?
It has unpaired electrons and non-bonding orbitals, making it anti-aromatic and unstable.
Unpaired electrons make it unstable. Got it.
And some energy levels are degenerate, meaning they have the same energy.
Degenerate, so electrons fill them according to Hund's rule, right? To maximize spin?
Yes. This explains why certain cyclic systems are aromatic or anti-aromatic.
Okay, so how do chemists actually figure out if a molecule is going to be aromatic or anti-aromatic?
That's where frost circles come in handy. They're a visual tool to predict the relative energies of pi molecular orbitals in cyclic systems.
A visual tool. I like the sound of that. How do they work?
It's surprisingly simple. You draw a circle, then inscribe the cyclic molecule inside it with one vertex pointing directly down.
Okay, I'm picturing that.
Where each point of the polygon touches the circle represents the energy level of a pi molecular orbital.
Wait, really? So I just draw a shape in a circle?
And where the corners hit the circle tells you the orbital energies. The horizontal line in the middle of the circle is zero energy. Anything below is bonding. Anything above is anti-bonding.
That seems almost too easy. But how does that tell you about aromaticity?
Aromatic compounds will have all their bonding molecular orbitals filled, leading to stability.
And anti-aromatic ones?
They'll have unpaired electrons in those higher energy anti-bonding orbitals, making them unstable. Frost circles really let you visualize that.
Okay, so we've talked about aromaticity, But what about annulenes?
Annulenes are cyclic hydrocarbons with alternating single and double bonds.
So just rings with double bonds?
Pretty much. But aromaticity requires more than just that alternating pattern.
Like what?
Planarity. The molecule needs to be flat for those p orbitals to overlap correctly.
Ah, I see. So what happens when they aren't flat?
Then you lose aromaticity, even if Huckel's rule says it should be aromatic.
So Huckel's rule isn't the only thing.
Exactly. Steric hindrance, those big bulky groups bumping into each other, can force a molecule out of plane.
Wait, really? I didn't know that.
Yeah, it's a common issue with larger annulenes. They try to be flat, but the hydrogens get in the way.
So basically, size matters in multiple ways?
Yes, you need the right number of pi electrons, and it has to be able to stay flat.
Okay, so what happens when you start fusing these aromatic rings together?
That's where you get polycyclic aromatic hydrocarbons. Think naphthalene, anthracene, big fused systems.
So like multiple benzenes stuck together?
Exactly. And the aromaticity extends across the whole thing.
Wow. Does that affect their reactivity?
Definitely. You have resonance structures all over the place, spreading out the electron density.
So it's not just one benzene ring doing its thing anymore.
Nope. The whole fused system acts as a single aromatic entity. It really changes the properties.
That's wild. Are these polycyclic things common?
They're everywhere. Combustion byproducts, crude oil, even in space.
Okay, so we're talking rings here. But what happens when you swap out a carbon for something else?
That's when you get into heterocyclic aromatic compounds. Instead of just carbon, you have heteroatoms in the ring.
Heteroatoms? Like what?
Nitrogen, oxygen, sulfur, things like that.
So same rules apply?
Mostly. They still need to be planar, follow Huckel's rule for aromaticity.
Huckel's rule, right? The 4n plus 2 pi electrons thing.
Exactly. And the lone pairs on the heteroatoms have to align correctly to contribute to the aromatic system.
Lone pairs? So they can change the whole electron count?
Absolutely. They donate electron density, influencing reactivity. Think of pyridine with nitrogen in the ring, or furan with oxygen.
Okay, so different atoms in the ring change everything.
Completely. They bring new properties and reactivity.
Wow. Aromaticity is more involved than I thought. So let's recap. It's all about stability, right?
Exactly. Extra stability in cyclic planar molecules.
And to be aromatic, you need that ring of overlapping p orbitals and follow Huckel's rule, the 4n plus 2 pi electrons.
Yes, don't forget planar and continuous overlap. If it breaks any rule, it might be anti-aromatic or non-aromatic instead.
Okay, so count the pi electrons, check for planarity, see if it's cyclic with continuous overlap. Seems doable.
Mm-hmm.
Why is aromaticity important anyway?
It influences reactivity, color, even the shapes of molecules. Aromatic compounds are everywhere, especially in pharmaceuticals and material science.
So basically, aromaticity dictates how a lot of the world works at a molecular level. That's kind of mind-blowing.
Totally. And it's a fundamental concept in organic chemistry. Once you grasp it, a whole new world of understanding opens up.
All right. I think that about
everyone,
wraps it up.
Welcome to the show.
Yeah.
Cam, how are you doing today?
I'm fantastic, Rachel. So stoked to be here.
So what exactly is electrophilic aromatic substitution? I keep hearing about it in organic chemistry.
It's a reaction where we replace an atom on an aromatic ring with an electrophile.
Electrophile. That's something that loves electrons, right?
Exactly. It's electron seeking. And aromatic rings, well, they're stable structures like benzene.
Benzene. That's the 6-carbon ring with alternating double bonds?
That's the one. Electrophilic aromatic substitution, or EAS, is the main way to put different things onto that ring while keeping it stable.
So why is EAS so important?
Aromatic rings are in tons of molecules like drugs, dyes, plastics. EAS lets us build them.
It's like a fundamental building block reaction.
Precisely. Now, the mechanism is 2 steps.
Okay, walk me through it.
First, the electrophile attacks the benzene ring. This forms a carbocation intermediate.
Carbocation. That's a carbon with a positive charge, right?
You got it. But this intermediate isn't aromatic anymore. Aromaticity is temporarily lost.
And benzene really doesn't like that.
It hates it. That's why it prefers substitution over addition.
Wait, what's the difference in this case?
Addition would mean adding the electrophile and another atom, breaking more of those double bonds, and losing aromaticity for good.
Oh, so substitution keeps the ring intact by just swapping one thing for another.
Exactly. So in the second step, a base removes a proton from the carbon that originally had the hydrogen.
A proton. That's just a hydrogen with a positive charge.
Right. Removing the proton reforms the double bond and restores aromaticity.
Aha. So the ring gets its stability back.
Yes, and that's why EAS is so common. Benzene strongly prefers staying aromatic.
Okay, so basically what you're saying is EAS lets us stick new stuff on benzene rings while keeping them nice and stable.
Precisely. It's a super useful reaction.
Okay, so you've got this benzene ring. What happens next when the electrophile attacks?
It's a two-step process. First, the electrophile attacks the benzene ring.
Attacks how?
It forms a bond, creating this rhenium ion. Think of it like a carbocation, but on the benzene ring.
Okay, so positive charge on the ring. Then what?
That's the slow step, the rate-determining step. Then, a base comes along.
A base like?
Like the conjugate base of the acid catalyst you use to generate the electrophile. It grabs a proton.
Grabs a proton from where?
From the carbon that now has the electrophile. Removing that proton reforms the double bond.
Ah, restoring aromaticity.
Exactly. That second step is fast. It's all about getting back to that stable aromatic system.
So attack, then deprotonation, 2 steps. Does this mechanism hold true for all EAS reactions?
Yep, every single one. The electrophile might be different, the base might be different, but the core steps are the same.
Universal mechanism, got it. Why is the first step rate limiting?
Because you're breaking aromaticity. Benzene really doesn't want to lose that stability. It takes energy.
Makes sense. So anything that stabilizes that rhenium ion intermediate would speed things up, right?
Bingo. And anything that destabilizes it would slow it down.
Okay, that's key. What are some of the common electrophiles we see in EAS reactions?
That's the fun part. You can do all sorts of things. Halogenation, nitration, sulfonation.
Wait, walk me through those one by one.
Okay, so we've set the stage. Now, how do we actually, make these electrophiles?
That's where things get interesting. Each electrophilic aromatic substitution reaction has its own way.
Like what? Give me the highlights.
Halogenation is first, using chlorine or bromine and a Lewis acid catalyst.
Lewis acid? What's that do?
It helps to polarize the halogen molecule. Think of it like making it extra positive.
Ah, so it's a super halogen?
Exactly. Then you have nitration, which uses nitric acid and sulfuric acid.
Sulfuric acid too? Why?
It acts as a catalyst to make the nitronium ion, which is the actual electrophile that attacks the benzene ring.
So acid's making more positive stuff?
Pretty much. Then there's sulfonation using sulfur trioxide, often with sulfuric acid.
Sulfur trioxide sounds intense.
It is, but here's a cool twist. Sulfonation is actually reversible under certain conditions.
Wait, it goes backwards?
Yep. You can remove the sulfonic acid group with hot aqueous acid. It's like a molecular eraser.
No way. Why is that useful?
Sometimes you need to temporarily block a position on the benzene ring, do another reaction, then remove the block. Sulfonation is perfect for that.
That's like molecular origami.
I love that analogy. It really is. And the reaction conditions can also affect the reactions.
How so?
Temperature and concentration are important for controlling the reaction and prevent unwanted side reactions.
So it's like a delicate balance to get it just right.
A lot of chemistry is really. Each reaction has a sweet spot.
Okay, so Friedel-Crafts alkylation. What's the big deal?
It's a way to slap alkyl groups onto aromatic rings, creating carbon-carbon bonds.
Carbon-carbon bonds are super useful, right?
Exactly. Think of it like attaching building blocks to make bigger, more complex molecules.
So how does it actually work?
First, you need to generate a carbocation, which is a positively charged carbon ion.
Okay, and then?
That carbocation is attacked by the aromatic ring, forming a new carbon-carbon bond.
Sounds straightforward, but I've heard it's not always the best option.
It's got limitations, major ones. First, it doesn't work well with electron-deficient rings.
Electron deficient, meaning?
Rings that have electron withdrawing groups attached. They deactivate the ring.
So the reaction just doesn't happen.
Pretty much. And it also fails with rings that have amine groups directly attached.
Why not amines?
The amine reacts with the Lewis acid catalyst, which deactivates the catalyst.
Got it. What else?
Overalkylation is a big issue. Once you add one alkyl group, the ring becomes more reactive.
So it just keeps adding more and more?
Exactly. It's tough to stop the reaction after just one addition.
That sounds like a pain.
It is. And finally, carbocation rearrangements can occur.
Rearrangements?
Yeah, the carbocation can shift around, giving you a different product than you expected.
So it's unpredictable?
It can be. The carbocation will rearrange to form the most stable carbocation intermediate.
Okay, so electron-deficient rings, overalkylation, and rearrangements. Sounds like a minefield.
It can be. But when it works, it's a powerful tool.
So it's got its place, but you need to be aware of the pitfalls.
Precisely.
Okay, so we've seen how Frito-Craft's alkylation can get a little messy with those carbocation rearrangements. Is there a way around that?
Totally. That's where Frito-Craft's acylation comes in.
Acylation?
Exactly. Instead of adding an alkyl group directly, we add an acyl group, which is a carbonyl group next to an alkyl group. Think of it like a ketone attached to your benzene ring.
Okay, but how does that help with the rearrangement problem?
Acyl groups don't rearrange. The acylium ion, the positively charged intermediate in acylation, is stabilized by resonance. It's much more stable than a simple carbocation, so it doesn't go gallivanting around looking for a better spot.
Wait, really? So it just plops right on there?
Pretty much. You get a clean addition of the acyl group to the benzene ring.
Okay, I see that avoids the rearrangement, but I want an alkyl group on my benzene ring. I thought you were going to show me how to do that.
Patience, young Padawan. Once you have the acyl group on there, you can reduce the carbonyl to a methylene, a CH2 group.
Reduce it? How do you do that?
There are a couple of ways. One classic method is the Wolff-Kishner reduction, which uses hydrazine and a strong base at high temperatures.
Hydrazine? Strong base? Sounds intense.
It can be. There's also the Clemenson reduction, which uses zinc amalgam and hydrochloric acid.
Okay, so different ways to get the same result.
Exactly. You end up with the alkyl group you wanted on the benzene ring, and you avoided the carbocation rearrangement issues. It's like a chemical workaround.
That's clever. So basically, acylate first, then reduce. Got it. So we'll dive deeper into the specifics of Frito-Craft's acylation next time.
You bet. We'll talk about the mechanism, the catalysts, and some of the limitations. It's not perfect, but it's a really useful reaction to have in your toolbox.
Awesome. I'm looking forward to it. All right. I think that's a good place to stop. Then how are you today?
I'm doing fantastic, Rachel. Thanks.
Okay, so let's switch gears a bit. I've heard of Frito-Craft's acylation. What is that exactly?
It's a way to stick an acyl group onto an aromatic ring. Think of it like adding a specific chunk to a benzene ring.
An acyl group. What's the point of that?
It's super useful in organic chemistry for building more complex molecules. You're adding a carbonyl group, which then can be converted into tons of other functional groups.
So, like a building block.
Exactly. Now, it's related to Frito-Craft's alkylation, but with some key differences.
Oh yeah, I've heard of that one. What's the difference?
Well, in acylation, our electrophile is an acylium ion, which is more stable. Alkylation uses a carbocation, which is prone to rearrangements.
Rearrangements? Why is that bad?
You get a mix of products. Acylation is much cleaner. Also, acylation avoids polysubstitution.
Polysubstitution? Meaning?
Multiple acyl groups attaching. Acylation deactivates the ring, so only one usually adds.
Ah, so more control over the reaction.
got it. Okay, so we've made this acylium ion. What happens next?
This is where the magic happens. The acylium ion, being a super reactive electrophile.
Electrophile, right, electron-loving.
Exactly. It attacks the benzene ring.
Attacks? Like head-on?
Well, it forms a sigma complex. The acylium ion bonds to one of the carbons in the benzene ring.
And that breaks the aromaticity, doesn't it?
You got it. That positive charge is now spread out around the ring.
Ouch. So how does the ring become stable again?
That's the final step. A base, usually the aluminum chloride, comes along and grabs a proton from the carbon that's bonded to the acyl group.
Deprotonation. Nice vocab.
It restores the aromaticity, and voila, you've got your acylated benzene ring.
So basically, aluminum chloride helps break bonds, then reforms them, like molecular matchmaking.
I love that analogy. It's a catalyst, right? It speeds things up, but isn't consumed.
So acylation is only step one? What comes next?
Exactly. We need to get rid of that carbonyl group. That's where reduction comes in.
Reduction? Like chemically reducing it?
Precisely. And there are a couple of classic ways to do it. The Wolff-Kishner reduction or the Clemenson reduction.
Okay, Wolff-Kishner and Clemenson. What's the difference?
Wolff-Kishner uses hydrazine and a strong base, good for molecules that can handle harsh bases. Clemenson uses zinc amalgam and hydrochloric acid, better for acid-stable compounds.
So different reagents for different molecules. Got it. And either one gets rid of the carbonyl?
Yep. It converts the carbonyl group, C double bond O, into a methylene group, CH2. So you've effectively installed an alkyl group without rearrangement.
Nice. Give me an example.
Think of starting with benzene. First, acylate it with propanoyl chloride. Now you have a ketone attached. Then reduce with Wolff-Kishner or Clemenson. Boom, propylbenzene.
Wait, so no isopropyl benzene as a product?
Exactly, just the straight chain propyl group. That's the power of this two-step process.
Okay, that makes a lot of sense. So basically, acylation locks the carbon skeleton in place. So we've talked about acyl chlorides.
Yeah.
Are there other ways to get acyl groups onto molecules?
Definitely. Anhydrides are a great alternative. They're often easier to handle and less reactive than acyl chlorides.
Easier to handle how?
They don't produce HCl as a byproduct, for one, and they're less prone to reacting with water in the air.
Makes sense. Anything else we should know about acylations?
Well, there's one Friedel-Crafts reaction that's pretty unique, the Godderman-Koch reaction.
Godderman-Koch. Never heard of it.
It's the only Friedel-Crafts method to directly make aromatic aldehydes.
Oh, interesting. How does that work?
It uses carbon monoxide and hydrochloric acid to generate formyl chloride in situ, which then reacts with the aromatic ring.
Formyl chloride.
Yep.
I've never seen that before.
That's because it's unstable. That's why it has to be made right there in the reaction mixture.
So the formyl cation is generated in situ?
Exactly. And then it attacks the ring just like any other Friedel-Crafts acylation.
Okay, so these benzene rings can get pretty complicated with all the substitutions. Are there common names we should know?
Definitely. Instead of using systematic names all the time, some have these trivial names. Toluene, for example, that's methylbenzene.
So toluene is just benzene with a methyl group.
Exactly. Then there's aniline, which is animobenzene, and phenol, which is hydroxybenzene.
Aniline and phenol, got it. What about when there are two substituents?
That's where ortho, meta, and para come in. For dimethylbenzene, you have orthoxylene, metaxylene, and paraxylene.
So ortho means they're right next to each other.
Adjacent, yes. Meta means they're one carbon apart, and para means they're on opposite sides of the ring.
Okay, ortho, meta, para for 1,2, 1,3, and 1,4 di-substituted benzenes. Makes sense.
Right. Knowing those trivial names and the ortho-meta-para system really simplifies things.
Definitely. So to recap, toluene, aniline, phenol, and the xylenes. Got it.
You're set for basic aromatic nomenclature.
Okay, so we understand where things attach. But why do they attach there?
Great question.
It's all about directing effects. Some groups are ortho-para directors, meaning they favor substitution at those positions.
And others?
Meta directors, which favor the meta position. It comes down to whether they're electron donating or withdrawing.
Wait, how does that work?
Electron donating groups, or EDGs, are activating groups. They make the benzene ring more reactive and direct incoming substituents to ortho-para positions.
Okay, and the opposite?
Electron withdrawing groups, or EWGs, are deactivating groups. They make the ring less reactive, directing to meta.
So, basically, donating activates, withdrawing deactivates, and that dictates where the new stuff goes.
Exactly. Think of it like this. The ring wants what it doesn't have. Too many electrons, it'll direct away. Not enough, it'll direct towards.
Is there like a cheat sheet for this?
Totally. There's a table summarizing all common substituents. Whispering. The key takeaway. EDGs activate and direct ortho-para, while EWGs deactivate and direct meta. Memorize that and you're golden.
Okay, but what about the weird ones, like halogens?
Ah, yes, the oddballs. Halogens are deactivating, but they're ortho-para directing. How does that work?
Right? It's like they can't make up their minds.
Exactly. It's all about competing effects. They're electron withdrawing through induction.
Induction?
Think of it like they're electronegative bullies, pulling electron density towards themselves through sigma bonds, which deactivates the ring.
Okay, I get that part.
But they also have lone pairs they can donate through resonance, pushing electron density into the ortho-para positions.
So resonance wins the directing fight.
Yes, the resonance effect, donating electrons, is what directs. However, the inductive effect overall slows the reaction. It's a tug of war, and directing wins, but deactivation still happens.
So basically, they're slower, but they still aim for those ortho-para spots?
Precisely. Halogens are slower directors, but they are directors nonetheless.
Okay, so let's switch gears and talk about meta-directors. What exactly makes something a meta-director?
Think of it this way. Strong electron withdrawing groups, or EWGs, are usually meta-directors. Halogens are the big exception there.
Halogens are weird. So what's the deal with these EWGs that makes them meta-directing?
It's all about those polar pi bonds. Meta-directors have them directly attached to the aromatic ring.
Polar pi bonds attached to the ring. Why does that matter?
Because they create a positive charge on the ring through resonance. You can draw resonance structures that show how that positive charge ends up destabilizing ortho and para positions more than meta.
Wait, so the meta position is actually less destabilized? That's backwards.
Exactly. The incoming electrophile is going to prefer the position that is relatively more electron-rich. Meta it is.
So basically, meta-directors suck electron density away, making the meta position a little less awful than the other spots. Got it. Okay, so we covered a ton today. Let's do a quick recap.
Definitely. We started with Friedel-Crafts acylation.
Right, adding that acyl group to the benzene ring.
Exactly. Then, to get around the limitations of Friedel-Crafts alkylation, we talked about acylation reduction.
So you first acylate, then reduce to get the alkyl group.
Precisely. It avoids carbocation rearrangements that mess everything up.
Smart. And finally, directing effects. Ortho, para, meta directors. That's crucial.
Yep, knowing where the next substituent will add.
Especially that weird halogen exception. Deactivating, but ortho, para directing.
Right. Lone pairs win out over deactivation in that case. Subtle, but important.
So basically, understanding these mechanisms and substituent effects lets you predict aromatic reaction outcomes.
Absolutely. It's like having a roadmap for organic synthesis. Nail these and you're golden.
Got it. It sounds like these are building blocks for more complex reactions.
100%. These reactions are fundamental.
All right. I think that about does it.
Podcast listeners, welcome
sure.
back.
Thanks, Ben.
Rachel, how are you doing today?
I'm doing awesome, Ben. Super excited to be here.
Okay, but sulfanilamide, how do you actually make it?
Synthesis.
That's where the magic happens. And honestly, it's a beautiful example of electrophilic aromatic substitution.
Electrophilic what now?
Think of it as controlled chaos on a benzene ring. We're adding things, but precisely where we want them.
Controlled how?
That's the art. We use directing groups already on the ring to guide where the next piece attaches.
Like a chemical GPS?
Exactly. And sometimes we need protecting groups to block reactions at certain spots temporarily.
Protecting groups, got it. So it sounds like a complex puzzle.
A puzzle where you really don't want over substitution, adding too many things to the ring. Then you have the wrong product entirely.
Okay, over substitution, bad.
Right. And the final key, retrosynthesis. Thinking backward from sulfanilamide to simpler starting materials.
Wait, you plan the whole thing backwards?
Precisely. It's like reverse engineering a recipe, and that's how all of these pieces come together.
Okay, so we've talked about directing effects, but what happens when these activating groups are too strong?
That's where things get tricky. Think of amino groups. They're super activating.
How strong are we talking?
They basically throw a party on the benzene ring, inviting every electrophile in town.
Electrophile party? I like that. So what's the problem with a party?
Over substitution. You end up with multiple bromines or whatever stuck all over the ring.
And that's bad because...
Lower yields, for one. Plus, separating those over-substituted products is a nightmare.
So it messes up the reaction and makes purification a pain.
Exactly. Let's take aniline as an example. If you react it directly, you get a mess.
A mess of multi-substituted stuff?
Yep. You'll get products with bromine at every available spot. Not what you want if you're aiming for a specific substitution.
Okay, so how do you tame these crazy activators?
The trick is to temporarily reduce its power. Protection, basically.
Protect the amino group?
Exactly. Convert it into something less activating. An amide, for example. Then, after the electrophilic substitution, you remove the protecting group.
So it's like putting the amino group in timeout.
Precisely. Keeps things under control.
Okay, but what if you can't directly control the location of the reaction?
That's where functional group into conversion comes in handy.
Functional group what now?
Basically, you temporarily change a functional group to control reactivity.
Like a disguise for molecules?
Exactly. Take aniline, for example. It's super reactive.
Yeah, it'll react all over the place, right?
Right. But if we first react it with acetyl chloride...
To form acetanilide?
Precisely. That acetyl group tones down the activating effect of the amine.
So it's less reactive.
Much less. It allows for clean monobromination at the para position.
And then you just remove the acetyl group?
Yep. Deprotection gives you the desired product cleanly.
So it's a protecting group strategy in a way.
Exactly. Temporarily modifying the group to control where the reaction happens.
That's a clever workaround.
It's all about manipulating reactivity to get the desired outcome.
Okay, but what happens when we have multiple directing groups messing everything up?
That's where things get interesting. Predicting the outcome gets trickier, but it's still manageable.
So how do we even start?
First, look at the activating or deactivating strength. Stronger activating groups usually win.
Win how?
They direct the incoming group to their preferred positions more effectively.
Okay, activating groups are like the quarterbacks calling the shots?
Exactly. But it's not just about strength.
There's more?
You need to consider the directing effects of all groups present. Ortho, para, meta. Where are they each trying to send the new group?
So it's like a tug of war?
Yes, and steric hindrance plays a role. If a spot is too crowded, the incoming group won't go there no matter what the directing groups say.
So even the strongest group can be blocked?
Absolutely. Think of it like trying to park a car in a tiny space. It just won't happen.
What if the directing effects conflict and aren't so obvious? Like if you have a para-director fighting a meta-director?
Then you start looking at the strength of each group and consider the steric factors.
Sometimes you might get a mixture of products.
A mixture? That sounds messy.
It can be, but that's chemistry. It is not always perfectly clean and predictable. Understanding these directing effects and steric hindrance really helps you make educated guesses about the major products.
Okay, so how does this actually work when chemists are, making real stuff?
That's where synthesis and retrosynthesis come in.
Retrosynthesis?
Yeah, it's basically reverse engineering a molecule. You start with your target molecule.
The thing you want to make.
Exactly. And you work backwards, step by step, breaking it down into simpler and simpler starting materials.
Like unbuilding it.
Precisely. You identify the last bond you want to form.
The very last step.
Right. And then you figure out what two pieces you need to connect to make that bond.
Okay, and then you keep going backwards.
Yep. Each step is like asking, what could I react together to get this intermediate?
So it's all about planning the most efficient route.
Exactly. And thinking about compatibility. You can't just throw anything together and expect it to work.
So it's like a puzzle, but with explosive chemicals.
Sometimes, yeah. But the goal is to find the safest, cheapest, and most effective way to build the molecule you need.
Okay, let's make this real. Nitroisopropyl benzene. Break it down for us.
Right. So we want to make that. Retrosynthetically, you might think to add the nitro group last.
Makes sense.
But if you do that, you're going to have a bad time.
Why is that?
The isopropyl group is an activating ortho-para-directing group. But it's bulky. You'll get a mix of products.
A mess.
Exactly. So better to nitrate first.
And then add the isopropyl?
Yes. The nitro group is meta-directing. It blocks the other positions.
Ah, strategic blocking.
Precisely. Then you can add the isopropyl group and it goes where you want it.
So basically the order you do things matters way more than I thought.
Totally. Retrosynthesis isn't just about what reactions to use, but when to use them. Thinking backward prevents problems before they happen.
That's some serious chess-level planning. Okay, so when we talk about EAS, what are the main electrophiles we're dealing with?
Right, the usual suspects. Things like nitronium, acylium, halogens.
Nitronium? What generates that?
That's usually from concentrated nitric acid and sulfuric acid together.
Classic combo. And acylium, that's for acylation, right?
Exactly. Acyl chlorides or anhydride with the Lewis acid catalyst like aluminum chloride.
Aluminum chloride, got it. What about just adding a halogen?
You need a Lewis acid there too, something like iron trihalide to polarize the halogen bond.
So the iron helps rip it apart.
Essentially, yeah. Think of it activating the halogen to make it a better electrophile.
Okay, and what about sulfonation? That always seemed a bit different.
That uses sulfur trioxide, often generated in situ from concentrated sulfuric acid.
Sulfur trioxide, okay. So those are the big ones. Nitration, acylation, halogenation, sulfonation.
Yep. Knowing how to make those electrophiles is half the battle.
Definitely. It's like having the right tool for the job. So electrophilic aromatic substitution isn't just a textbook thing.
Absolutely not. It's used to make tons of useful compounds. Sulfonylite is a great example.
Sulfanilamide? What's that?
It's a sulfa drug, one of the first antibiotics.
No way!
Totally. And electrophilic aromatic substitution is key to making it.
How so?
Well, you start with benzene and do a series of electrophilic aromatic substitutions.
Like add different things onto the benzene ring?
Exactly. You add a sulfonamide group, then an amino group.
And that creates sulfanilamide.
Yep. It's not a simple one-step reaction, but electrophilic aromatic substitution is essential.
So it's used to make a life-saving drug. That's intense.
It really shows how fundamental this reaction is to industrial processes.
Are there other big applications of it in industry?
Tons. Making dyes, plastics, pharmaceuticals, all rely on electrophilic aromatic substitution.
So it's kind of like a building block reaction for organic synthesis.
Precisely. It's a cornerstone of modern chemical manufacturing.
Well, Rachel, that's a great overview.
Yeah, I think so.
Thanks, Rachel.
Thanks for having me.